طيب السلام عليكم ورحمة الله وبركاته، أسعد الله مساءكم جميعًا بكل خير، وحياكم الله في البرنامج التدريبي مقدمة عن الرقائق الإلكترونية من التصميم إلى التصنيع والاختبار Semiconductor Chips from design to manufacturing and testing. نستهدف في هذا البرنامج التدريبي تعزيز ثقافة فهم أشباه الموصلات أو الSemiconductor Chips وأيضًا إعطاء فكرة عامة عن صناعة الرقائق الإلكترونية وأشباه الموصلات، والدور اللي تلعبه الرقائق الإلكترونية في حياتنا اليومية. مستوى الدورة مبتدئ، فنتوقع إنه محتوى الدورة يكون سلس للمتخصص وغير المتخصص كذلك. طيب، اليوم بنبدأ كمقدمة بدايةً عن الsemiconductors. بعدها نتكلم عن الsemiconductor chips أو الرقائق الإلكترونية، بعدها بنستعرض بعض الحقائق أو الfacts about semiconductors، وبعدها Saudi Semiconductor Program والبرنامج السعودي لأشباه الموصلات. فنبدأ بدايةً بعد توكل على الله في المقدمة الintroduction. طبعًا أشباه الموصلات هي عنصر أساسي في حياتنا الحديثة وعالمنا الحديث. الsemiconductor هي الأساس أو الcore لكثير من تطبيقاتنا في حياتنا اليومية، ابتداءً من الهواتف الجوالة إلى السيارات إلى غيرها من التطبيقات. نتكلم هنا عن مراحل مختلفة في أشباه الموصلات من التصميم والتصنيع والاختبار. الهدف من المراحل المختلفة هذه اللي كلها تدخل ضمن سلسلة القيمة لأشباه الموصلات، إنه يكون عندنا reliable يعني chips لتطبيقات في مجالات مختلفة، على سبيل المثال في الذكاء الاصطناعي، في الIoT، في الhigh performance computing وغيرها من التطبيقات، سواء كانت بسيطة أو حتى معقدة، يعني من السمارت فون، الAI، الcomputing، الmonitoring، الcars وغيرها كلها تدخل صناعة الرقائق الإلكترونية كصناعة داعمة لهالصناعات المهمة في حياتنا اليومية. آآ السؤال هو وش هي أشباه الموصلات؟ أو ماذا نعني بأشباه الموصلات؟ Semiconductors من اسمها have electrical properties between conductors and insulators. يعني هي لها خصائص كهربائية، هذه المواد لها خصائص كهربائية بين الموصلة والعازلة. يتم التحكم في مقدرتها التوصيلية عن طريق إضافة شوائب إلى هذه المواد أو مواد إضافية داخل هذه المواد. من أشهر مواد الأشباه الموصلات هي السيليكون، لذلك لو نعرف مثلًا وادي السيليكون أو السيليكون فالي في كاليفورنيا، الهدف من الشركات اللي هناك كلها ضمن نطاق أشباه الموصلات وتطبيقات أشباه الموصلات المختلفة. لو تلاحظون اسمها سيليكون فالي، فالسيليكون أو مادة السيليكون اللي يعني يعتبر الساند عنصر أساسي لها، هي المادة الأكثر استخدامًا في تطبيقات أو كمادة لأشباه الموصلات. ليش أشباه الموصلات يعني مهمة ومختلفة؟ again it can be both conductor and insulator، يعني تقدر تكون موصلة أو عازلة، وهذا الشيء يسمح لنا في تصميم دوائر إلكترونية معقدة مثل المايكروشيبس، لأنه نقدر نتحكم في التوصيلية وفي العزل based على التيار أو غيره. طبعًا نقدر نستخدمها as miniaturized، يعني مصغّرة في حجم أقل من حجم الشعرة أو المايكرو. الهدف إنه يكون عندي millions في transistors on a tiny chip، عدد كبير من الترانزستورات في chip صغيرة في حجم مثلًا رأس الأصبع على سبيل المثال that can empower different applications. وبلا شك إنه أشباه الموصلات هي يعني عنصر أساسي في الابتكار من الخلايا الشمسية للLEDs إلى الإلكترونيات المختلفة. طيب، أشباه الموصلات it's a trillion dollar industry، صناعة ضخمة جدًا، والprojection للسوق أشباه الموصلات حول العالم يتوقع أن يوصل $1 trillion by 2030، وفي growth كبير جدًا في أشباه الموصلات كصناعة على سبيل المثال المعدل الgrowth السنوي يتراوح بناءً على التطبيق، وتطبيقات أشباه المواصلات تختلف بناءً على الاحتياج، على سبيل المثال في الcomputing، في الcommunication أو الاتصالات، في الautomotives، في تطبيقات الconsumer electronics اللي هي تطبيقات إلكترونيات اللي يستخدمونها الناس في حياتهم اليومية. طيب، طبعًا لو نذكر COVID-19 يعني خلق demand عالي في فترة COVID-19، والdemand أو الطلب العالي للرقائق الإلكترونية كان مرتبط باحتياج العالم للرقائق الإلكترونية لتطبيقات مختلفة. في نفس الوقت ما كان فيه يعني رقائق إلكترونية تفي بالاحتياج. على سبيل المثال يعني اللي يشتري سيارة في عام 2020 يمكن كان فيها مواصفات إلكترونية أو sensors أقل من السيارة اللي قبلها بسنتين من نفس الموديل يعني. كذلك يعني أحيانًا لمّا الواحد يطلب سيارة أو يشتري سيارة ينتظر وقت طويل بسبب أزمة رقائق إلكترونية اللي حدثت بسبب الطلب العالي للرقائق الإلكترونية مع ضعف تلبية الطلب بسبب الإغلاق واللي حدث في أثناء COVID-19. هذا يعني خلق awareness عالي للsemiconductors، وبعدها انطلقت كثير من المبادرات الوطنية مثل CHIP Act في يعني الUnited States. الهدف من هالمبادرات الوطنية سواء في الصين، في أمريكا، والاستثمار العالي اللي صار لتلبية الطلب المتزايد على الرقائق الإلكترونية وأجهزة أشباه الموصلات. باتكلم بشكل مختصر عن Semiconductor Chips. وش نقصد بالchips؟ الchips هذه هي electronic component، يعني عنصر أو جهاز إلكتروني مبني على الsemiconductors، مبني على مادة semiconductor على سبيل المثال السيليكون. وit can be as يعني as it can be considered as the brain of electronic devices، يعني كأنه العقل اللي يعني يتحكم في مختلف العمليات داخل الأجهزة الإلكترونية. بتكلم عن بعض الإكزامبلز للسيمايكوندكتور شيبس مثل المايكرو بروسيسورز الموجودة في أجهزة الكمبيوتر، في السمارت فونز، في الآي أو تي وغيرها. الميموري تشيبس نعرفها كلنا مثل الرام والفلاش وغيرها، الأنالوج تشيبس، وأيضا الباور مانجمنت تشيبس. هذه كلها تطبيقات مختلفة لأشباه الموصلات، وتحديدًا الرقائق الإلكترونية في حياتنا اليومية. طبعًا الرقائق الإلكترونية يمكن نسأل ليش هي مهمة؟ لأنها هي المشغل أو المحرك الأساسي لكثير من التطبيقات زي ما تكلمنا قبل شوي. على سبيل المثال مثلًا الAI، ال5G، كلها تعتمد اعتماد كبير على الرقائق الإلكترونية، وهذا يعني يعطينا انطباع لكثير من التطبيقات أنها تبنى على رقائق إلكترونية. بالتالي الرقائق الإلكترونية صار تطويرها حاجة ماسة لمختلف يعني مختلف الشركات ومختلف البلدان. طيب، لما نتكلم عن Semiconductor Chips، مين اللي يعني يصنع هالشيبس؟ الشيبس طبعًا تمر في مراحل مختلفة ابتداءً من التصميم. التصميم بحد ذاته يمثل أكثر من 50% من القيمة الحقيقية للشيب. طبعًا التصميم يعني يعتبر يعني المركز التصميم الرئيسي أو أغلب شركات التصميم متواجدة في أمريكا، لكن التصنيع في آسيا، لذلك ما في دولة واحدة مهيمنة على عملية التصميم والتصنيع للرقائق الإلكترونية. Again التصميم يكون غالبًا في أمريكا، والتصميم هو اللي له قيمة كبيرة في ناحية الرقائق الإلكترونية كتكلفة أو كقيمة عائد من الadded value. وأيضًا التصنيع يتم في شركات في مثلًا آسيا including TSMC في تايوان، Global Foundries وسامسونج وغيرها. لو تلاحظون المساحة الكبيرة للشركات التصميم مثل انفيديا، لأنه السوق حقها جدًا عالي، العائد من التصميم أعلى من العائد من التصنيع. طيب، في تحديات في هالصناعة منها الchip shortage، النقص الhigh demand والsupply chain تحدي كبير، وفي geopolitical issues اللي هي المشاكل الجيوسياسية مثل يعني المشاكل اللي تكون بين الولايات المتحدة والصين في موضوع الحظر وغيرها للرقائق الإلكترونية، وأيضًا تحديات في تصنيع الرقائق الإلكترونية الصغيرة. طبعًا في قانون اسمه Moore Law. القانون هذا يعني من سنوات طويلة يعني يفترض إنه كل سنة تصغر أو يتم مضاعفة حجم الترانزستورات في الchip الواحدة، بالتالي إحنا عندنا demand وحاجة لتصغير الرقائق الإلكترونية هذه. الآن الmarket فيه 3 نانومتر، وفي research كبير على 2 نانومتر وال1 نانومتر. نتكلم عن النود أو الحجم للchips أو للموصلية داخل الchips. طيب إيش الfuture trend للsemiconductor؟ أنا كتبت 2 هنا من بينها الAI driven chips وكذلك 2 نانومتر and beyond for chip technology. again التصغير شيء مطلوب في الchips، لذلك 2 نانومتر أحد النقاط المهمة في التصنيع. والآن إنتل على سبيل المثال عندهم تصنيع في 1.8 نانومتر في أريزونا. طيب خلينا نتكلم عن بعض النقاط المهمة. إنه again يعني ليش السيميكوندكتور مهمة؟ It's hard to imagine a world without semiconductor. كثير من التطبيقات شوفونها قدامكم مرتبطة بالsemiconductors. So none of these devices in the picture can work without semiconductor chips. من التابلت، السمارت فون، للتي في، للديجيتال كاميرا، للمايكروويف، كل هالتطبيقات مرتبطة ارتباط مباشر بالsemiconductor chips. So خلينا نبدأ
Dr. Salman?
Yes.
Dr. Salman, I think your slides are not moving. Can you please check?
Okay. Which slide now?
We are just seeing the first slide.
Oh, okay.
They are not displaying on the screen.
Okay,
yeah, now we can see. Thank you.
Now
we can see now.
Okay. So we have أكثر من fact عن السيمايكوندكتور. أعتذر إنه ما كنا نعرف إنه السلايدات ما كانت واضحة لكم، لكن ما فاتكم شيء. we have facts يعني about semiconductor. على سبيل المثال السيمايكوندكتور يمكن من أهم الحقائق إنها reshaping the world، يعني تعيد تشكيل العالم من ناحية يعني تقنية، ومن ناحية سياسية، ومن ناحية من ناحية اقتصادية كذلك. So السيمايكوندكتور powering the world، يعني هي اللي powering the world عن طريق الباور الكترونكس وغيرها. كذلك يعني كثير من التطبيقات في الفورث اندستريال ريفوليوشن اللي هو الثورة الصناعية الرابعة مرتبطة بأشباه الموصلات. advancing the world على سبيل المثال ال AI technology تعتمد على الشيبس اللي في السيمايكوندكتور. So if we have semiconductor chips, then we have AI technology. If we don't have semiconductor chips, we will not have AI technology. نتكلم مش فقط كchips but also for data center وغيرها، لمراكز بيانات وغيرها. طيب. So فيه شيء نسمع عنه اسمه الحرب الباردة في أشباه الموصلات، وهذه حرب باردة بين US الولايات المتحدة والصين طبعًا، وصار عليها بعض القيود وبعض الsanctions أو بعض الحظر للرقائق الإلكترونية. الهدف أو ليش الحرب الباردة هذه بين الصين وبين أمريكا، والحظر والتحديات هذه كلها لأهمية الرقائق الإلكترونية. يعني لولا أهمية الرقائق الإلكترونية كان ما صار في خلافات كثيرة على مستوى يعني دول كبيرة مثل الولايات المتحدة والصين. فهذا يعطينا انطباع على أهمية السيمايكوندكتور شيبس. So أحد الأشياء اللي أيضًا مهمة، أو أحد الحقائق المهمة اللي هي المايكروشيبس، يعني هي محرك أساسي للاقتصاد العالمي. نتكلم عن البروجكشن 1.5 تريليون by 2035. كنت أتكلم قبل شوي عن 1 تريليون دولار by 2030. الرقم هذا ضخم جدًا، ونتوقع أنه يزداد وتزايد كبير جدًا بسبب الهاي ديماند للإلكترونيك ديفايسز. أيضًا تقريبًا 25% من الجلوبال كونسامشن أو الاستهلاك العالمي للرقائق الإلكترونية within يعني أمريكا والصين. So هذا يعطي انطباع أيضًا على أهمية أو الحاجة الماسة لتطوير هذه الرقائق الإلكترونية. طبيعة Semiconductor شوي معقدة، لأنها تمر في مراحل مختلفة، بدايةً من التصميم، بعدها المواد، بعدها التصنيع الأولي، بعدها التصنيع النهائي، بعدها الtesting. فطبيعة يعني الnature حقتها شوي complex، لذلك ما في دولة في العالم يعني عندها الصناعة هذه بشكل كامل، من التصميم، المواد، التصنيع، التغليف، التعبئة، الاختبار. لذلك لو تلاحظون زي ما تكلمت قبل شوي إن الصناعة موزعة ضمن مراكز قوى مختلفة. على سبيل المثال الولايات المتحدة متميزة جدًا في التصميم وشركات التصميم including Apple وغيرها. أيضًا الصين متميزة في التغليف والتعبئة. تايوان متميزة في التصنيع، شركة TSMC أكبر شركة صناعة أشباه الموصلات. آآ عشان نفهم أهمية أشباه الموصلات نشوف المثال حق تايوان. تايوان في 1987 يعني كانت هي الولادة الحقيقية لشركة TSMC. لو تلاحظون في الصورة اللي فوق 1980 والصورة اللي تحت 2020. الاقتصاد التايواني معتمد بشكل كبير جدًا على صناعة الرقائق الإلكترونية، تحديدًا على TSMC وغيرها من الشركات. لو تلاحظون أكثر من 30% تقريبًا من الGDP من الGDP أو الاقتصاد في البلد معتمد على صناعة الرقائق الإلكترونية TSMC وغيرها من الشركات الضخمة. يعني شركة واحدة بدأت في 1987 وهي أكبر شركة الآن لتصنيع الرقائق الإلكترونية حول العالم. الآن الشركة هذه يعني تضخ وغيرها من الشركات أكثر من 30% من أو تتحكم بأكثر من 30% من اقتصاد دولة كاملة. هذا يعطينا انطباع ومؤشر على أهمية هذه الصناعة وأثرها الاقتصادي. أيضًا Semiconductor Driven Innovation زي ما قلنا الsemiconductor تدخل في تطبيقات مختلفة، يعني من الAI إلى الelectronics إلى السيارات إلى غيرها. لذلك الضخ أو الspending الaverage R&D spending أو الضخ في الresearch للsemiconductor في عام 2020 كنسبة يعتبر الثاني بعد الأدوية أو بعد صناعة الدواء. فصناعة أشباه الموصلات كR&D تعتبر ثاني نسبة يضخ عليها مقارنة بالصناعات الأخرى المختلفة. والسبب إنه تدخل في صناعات كصناعة داعمة لصناعات كثيرة. على سبيل المثال هواوي، شركة هواوي الشركة الصينية عندها التزام بأكثر من 22 بليون دولار في الR&D في 2020. هذا الرقم الضخم يعني أثره صرنا نشوفه اليوم عن طريق تطويرهم تقنيات جدًا متقدمة وريادتهم للfuture technologies including ال6G. طيب السيميكوندكتور أيضًا مهمة للnational security. لذلك كل دولة تحب إن يكون عندها يعني قوة في أشباه الموصلات. على سبيل المثال China aiming to lead chip manufacturing by 2030. الآن لو تلاحظون تايوان هي اللي تقود هذه الصناعة. China عندها هدف أنها تقود الصناعة by 2030. والهدف هذا بسبب إنه هذه الصناعة لها ارتباط أيضًا في الnational security. طيب الريادة التقنية لأشباه الموصلات يعني شيء أحد الحقائق اللي يعني لا جدال فيها، بسبب إنه زي ما تفضلنا قبل شوي وقلنا إنه صناعة أشباه الموصلات ترتبط كصناعة داعمة لتقنيات وصناعات حديثة مثل الAI الذكاء الاصطناعي، مثل الIoT إنترنت الأشياء، smart cities المدن الذكية، كلها تبنى بشكل كبير على الرقائق الإلكترونية، وكيف نقدر نصنع رقائق إلكترونية بperformance عالي لخدمة هذه التطبيقات، كذلك في الطاقة والtelecommunication وغيرها. طيب أيضًا الحقيقة إنه بناء على دراسة ماكنزي كأحد بيوت الاستشارات العالمية، يتوقعون الgrowth يكون أو النمو يكون بين 6 إلى 8% per year للindustry هذه. لذلك لو نلاحظ الdemand is high الsupply ما يوصل للمطلوب إلى الآن. في demand عالي جدًا في semiconductor. ولذلك كثير من الدول اتجهت بشكل كبير لهذه الصناعة، خصوصًا زي ما قلنا بعد COVID-19. طيب Semiconductor Chips زي ما قلنا قبل شوي It's powering ال AI تقنيات الذكاء الاصطناعي اللي نشوفها اليوم. لو تلاحظون مثلا خلال الأسبوعين الأخيرة بس الهزة الاقتصادية الكبيرة اللي صارت لشركات سيماي كوندكتر في أمريكا بسبب ظهور يعني أحد الشركات أو أحد التطبيقات الصينية في ال AI واللي استخدمت يعني رقائق إلكترونية AI مبنية على الفكرة اللي موجودة اوريدي عند انفيديا، لكن اختصروها ووفروا عدد رقائق أقل تؤدي نفس الغرض. بالتالي اللي صار كثير من أسهم انفيديا وغيرها من الشركات including for example Cadence اللي هي شركة تصميم، فنزلت الأسهم بشكل كبير بعد ظهور هذا التطبيق الصيني اللي يرتبط بشكل كبير بالاي اي. فالسبب هذا انه يعطينا انطباع انه السيمي كوندكتور تشيبس والاي اي مرتبطه ارتباط كبير ببعض، وايضا كلهم مرتبطين ارتباط كبير بالاقتصاد. فالتقنيه تؤثر بشكل كبير في الاقتصاد العالمي. الفيوتشر كومبيوتينج اللي نسميه كوانتم كومبيوتينج يبنى كذلك على رقائق الكترونيه واشباه الموصلات. لذلك كثير يعني من المعاهد الابحاث ومراكز الابحاث في العالم بدات الان تبحث في تطوير الكوانتم كومبيوتينج باستخدام السماي كوندكتور. لو تلاحظون ايضا الاي في السيارات الكهربائيه مرتبطه كذلك ارتباط وثيق بالسيمي كوندكتور. على سبيل المثال في السياره الواحده ما بين يعني 1400 تو من 1400 الى 3000 تشيبس بير السياره الواحده. لذلك ما راح يكون في EVs لو ما كان في سيمي كوندكتور شيبس. طيب ايضا بالنسبه للرينيبل انرجي طبعا السيمي كوندكتور شيب enable production of 99% power تحويل كهربائي 99%. وكذلك كثير من السيمي كوندكتور شيبس contribute يعني مبالغ ضخمه للسولار بانل عن طريق او الويند توربينز عن طريق تطوير هذه الرقائق لهذه التطبيقات. مش فقط في الطاقه او السيارات، كذلك في الميديكال ايميجينج. لما الواحد الله يبعد عنا عنكم الشر يكون في زياره المستشفى تقنيات مثل الاكس راي، السي تي سكان، الام ار ايز والالترا ساوند كلها اساسا بيست على السيماي كوندكتور شيبس. فهذا يعطينا انطباع على أهمية هذه الصناعة في مختلف مناحي الحياة. كذلك brain sensing for example الله يبعد عنا عنكم الشر مثلا الناس اللي عندهم إصابات في الباركنسون ديزيز أو غيرها من الأمراض العصبية، يتم استخدام رقائق إلكترونية بحجم المايكرو تسوي ستيميوليشن للمراكز الدماغ اللي تتأثر بالباركنسون وتعالجها. لذلك في تقنيات مثل الديب برين ستيميوليشن يتم فيها استخدام هذه الرقائق الإلكترونية الصغيرة داخل الدماغ لمعالجة الباركنسون. والشيء هذا يعني أنعمل في البحث وأنعمل في المستشفيات، ولاحظوا أنه فعلا يمكن معالجة أو تخفيف أثر الباركنسون عن طريق التحفيز الكهربائي لأنسجة معينة أو خلايا معينة بالدماغ بواسطة الرقائق الإلكترونية. أيضا الترانزستورز زي ما تكلمنا في بداية الحديث اليوم في Moore's law, so we need to يعني shrink down the size of the microchips to be في الرينج حق 3 نانومتر or below. So started من 3 مايكرون تقريبا قبل يمكن 25 سنة. اليوم 3 نانومتر وأقل من 3 نانومتر في الهدف من يكون عندي عدد رقائق إلكترونية كثير في مساحة صغيرة فيعطيني performance عالي. again آسيا تهيمن على المانيفاكتشرينج، نتكلم عن 65% من التصنيع يكون في تايوان، و16% على سبيل المثال في 15% في كوريا، وفي شركات في الديزاين أمريكية مثل أبل، AMD وانفيديا وغيرها. طيب أكثر من 1000 شيب في السيارة العادية، ما نتكلم عن الإيفيز، نتكلم عن السيارات الجازولين كارز، يعني فيها تشيبس ما تقل عن 1000 شيب ما بين الكنترولرز، ما بين اللي موجودة في الشاشة، ما بين اللي موجودة في السيستم الABS الكثير من الإلكترونيكس هذه بيس على Semiconductor Chips، فتقريبا 1000 أو أكثر من 1000 Semiconductor Chips في السيارة الواحدة. فما نتخيل سيارة بدون Semiconductor Chips. With that being said، مع كل ما قلنا في continuous demand to fulfill talent shortage، في talent shortage، في نقص في المواهب المتخصصة في هذا المجال على مستوى العالم. فعلى مستوى العالم في احتياج ل there is a need for talents semiconductors to fulfill the need، لأنه في need كبير لتعزيز هذه الصناعة على مستوى العالم والوصول إلى الديماند من ناحية رقائق إلكترونية، تصنيع هذه التطبيقات اللي ذكرناها وغيرها الكثير من التطبيقات. طيب، تكلم بشكل أخير عن السعودي سيمي كوندكتور بروجرام أو البرنامج السعودي لأشباه الموصلات، وهذا الموقع للبرنامج السعودي لأشباه الموصلات تقدرون تكتبونه للوصول إلى يعني الديزاين تولز اللي موجودة في البرنامج السعودي لأشباه الموصلات، للكوميونتي، الإيميلات، الإعلانات كلها توصلكم، وكذلك يمكنكم التواصل مع البرنامج عن طريق الإيميل ssp@cax.gov.sa. طبعا البرنامج السعودي لأشباه الموصلات تم إطلاقه في عام 2022 كمبادرة وطنية لتوطين ودعم صناعة الرقائق الإلكترونية وأشباه الموصلات في المملكة، ودعم ال R&D Local R&D Semiconductors في المملكة. ولو تلاحظون إنشاء في 2022 جاء كردة فعل سريعة على النقص والاحتياج العالمي للمتخصصين في السيمي كوندكتورز. طبعا ال SSP يستهدف أكثر من محور، من أهمها improve research quality عن طريق إتاحة المالتي بروجكت ويفر، إتاحة مساحة لتصميم رقائق إلكترونية ضمن ويفر كبير، لأنه صناعة الرقائق الإلكترونية مكلفة. ففي ممارسة عالمية اسمها MPW أو Multi Project Wafer، الهدف منها هي أنه يتاح تشير الويفر والرقائق الإلكترونية، الويفر الكبير السيليكون مع different project داخل الويفر، بالتالي تقليل التكلفة على الريسيرشر بدل ما يدفع تكلفة ويفر كامل. كذلك developing human capital أو human capabilities، القدرات الوطنية البشرية في أشباه الموصلات، واللاين ال R&D activities مع national strategies. طبعا لما نتكلم عن Semiconductor Chip Design and Manufacturing نتكلم عن دور ال SSP في دعم الديزاين عن طريق الديزاين تولز وال IPs، وكذلك عن طريق الفابريكيشن سواء داخل المدينة في مختبرات الغرف النقية أو الكاكس كلين روم within كاكس، أو يعني مع شركائنا الخارجيين. كذلك في موضوع الباكجينج والتستنج للسيمي كوندكتور شيبس. تم تصنيع رقائق إلكترونية كثيرة من يعني ساهم فيها متدربين ضمن البرنامج السعودي لأشباه الموصلات. تم تصنيعها سواء في كاكس ولا في TSMC شركة تايوانية وغيرها لتطبيقات مختلفة، على سبيل المثال الريسيفر، الباينري فيس شيفت كينج ريسيفر، على سبيل المثال ال SOI بروسيس للميمز، الوايد باند جاب باور شيب وغيرها من التطبيقات اللي يعني كلها مفيدة ويمكن استخدامها في الابليكيشنز المختلفة ذكرناها قبل شوي. طبعا في التريننج we have two different training models being the hands-on training اللي هو عن طريق إتاحة يعني التدريب على تصنيع لرقائق إلكترونية، أو عن طريق التدريب الافتراضي في مجالات تشمل الاي سي ديزاين او تصميم الرقائق الالكترونيه، والميمز اللي هي المايكرو الكتروميكانيكال سيستم، مجال استشعار الكهروميكانيكيه الدقيقه. يستهدف هنا الفرونت اند اللي هو جزء الديزاين بشكل كبير، وهذا هدف الاس اس بي توفير او اتاحه هالبرامج وهالبرامج التدريبيه وبرامج التصميم نفسها، والفرصة يعني يكون في تالنت متخصصين في السيمي كوندكتور في المملكة. أنا بترك المجال الآن to Mr. our engineer Vibal Sharma to continue the presentation with the semiconductor industry and the need for talents in semiconductors. So Engineer Vibal, the floor is yours. Host of the
Thank you,
show.
thank you, Dr. Salman. Uh, so I hope my screen is visible. Can you confirm?
Yes, it's visible.
Okay, thank you. Okay, so good evening, everyone. I think Dr. Salman gave a very good overview of like what is the importance of semiconductors. I think you got a good idea. Maybe you are also well versed about what all are the developments going in global world. There is so much talk about semiconductors. I think semiconductor, as they say, is a new oil. You cannot live without semiconductors. So everybody has to have some kind of a capability. Every nation has to develop their own ecosystem around it. And the purpose of this small training program is to give you all a basic fundamental view of what is semiconductor, how this industry looks like, because on a top level overview, we see just like semiconductor can be a single industry, but it's not. There are very complex moving parts in it. There are different domains. In order to get a successful design realizable into a product, it takes a lot of steps and lot of people need to play a role. So there are a lot of opportunities for anybody who wants to enter to this industry. And it's not like there is only fabrication. I think you must have heard about like the foundry or fab is a very important part of a semiconductor industry. That is, but it's not like because foundry needs some designs because somebody has to design that 5G chip or the chips going into your Apple iPhone or Samsung phones or on your TV's car. Somebody has to design those chips, and then only a foundry can take over that and then try to fabricate that design. So it's not like foundry is only moving part of this industry. There are several others. So during the course of this lecture and further, we will be seeing like what all are the moving elements of this industry and where you people, I believe you all are very young engineers and maybe some of you are studying. So there is a long roadway ahead of you where you can try to build your careers. You can dream about entering into this industry. And I know from the fact like Saudi government is taking a lot of steps to build a local ecosystem and they want to develop a skilled manpower. So I think you all have a very bright future if you want to enter into this industry. And our purpose as part of this training is to give you a motivation and also give you some background so that you get motivated. Ultimately, you need to understand what is the importance of this industry. You should feel attracted, like I want to build my career into it. So that is our motivation. Okay, so let us start. Okay, so over the course of these next 4 days, this will be the our plan. So today I will be covering basic overview of semiconductor industries. So tomorrow we will be having little extended session where I will be giving a brief overview of what is analog IC design flow. Ultimately, our focus is as part of this training, I will be giving you an overview of the complete semiconductor industry, but focus is to give you an idea like what is the IC design like because ultimately, as I told you, somebody has to design those chips and ICs. So how that process looks like, how that flow moves on. So that will be the part of tomorrow's lecture, and I will also be giving you a demo. Ultimately, in order to do a design, we need to use some kind of a tools, some software. There are sophisticated softwares which are required to design an IC. So tomorrow I will be covering that brief flow, how that flow looks like. And the fourth lecture will be on introduction to semiconductor fab. And then last one will be because fabrication is not the end of the things. After fabrication, there are several other steps. These are called post-fabrication IC development steps. Ultimately, the wafer needs to be cut into dies. Those dies need to be assembled, packaged, and then also need to test, validate your design. So all those are post-fabrication IC development stages that I will be covering on the last day. Okay, so we do not want like we just want to give you some lectures and then you do not have anything follow up with us. So we have arranged a system where we have made a channel on Slack. So you all can join that Slack through this online form, which I will be sharing the chat at the end of this lecture. uh, you on those Slack channel, if anything needs to be shared, if you have any follow-up queries regarding the lecture, etc., then you can please post your queries there, and I will try to answer them as much as possible. Okay, so let us start with today's lecture. So I think all of us understand what is the current status of the semiconductors and the world in overall. We all understand the semiconductors are very important. But let us go a little behind. Let us go 100 years ago when all this started. So at that time there were no semiconductors. So basic development, the fundamental technology development which was taking place was like, for example, in order to understand the importance of semiconductors or electronics industry, I wanted to compare it with a parallel industry, and that industry was automobile industries. So as can be seen, this is the picture of a first automobile, or a, you can say, a moving vehicle. It was basically developed in 1885, and this, you can see, it is a very preliminary car, but it was a very significant leap for the humankind, because what it gave us was, it gave us an option to for transportation and mobility. We can quickly move from one place to another. Before that, we used to have bullock carts and horse carts, etc., so they were very slow moving vehicles. So it was a significant development. In a way, we can say it started a revolution in automobile or mobility, and this was the origination of automobile industry. Obviously, once it came up, it had a profound impact on the infrastructure, because once you have a means of moving fast, you can transport people, goods, etc. And also it led to the development of big commercial areas and cities, etc., and also gave a boost to economy. So whatever development which we see now, I think the fundamental building block of that was kept by the evolution of automobile industry. And obviously it led to rise of urbanization and also expansion. So this is one aspect of an early engine of innovation, that is automobiles. So similarly, at similar time period, maybe 20 years after that, there was another revolution. So this is our first vacuum tube diode. So this was what gave the humans control over electricity. So you must be knowing, like, electricity was first invented and we got a power to control things. But ultimately, the if whenever a current is flowing through anything, you need to control it. Basically, if you want to make decisions, like if you want to send a signal, you want to control the flow of electrons. So this is a vacuum tube device which was invented by John Fleming in 1904. So in a way, this set up the foundation of electronics industry, the modern electronics industry. So this is, I think, both these inventions were very close, nearby to each other. There was a difference of 20 years between them. And it is the invention of these vacuum tubes which later on, like a century later, gave, or maybe like let us say 50 or 60 years later, it gave rise to all the modern electronic. First, starting with early radios, basic radios used to receive wireless transmission, and then led to computers. And then 1980s saw the revolution of personal computers, PC, when everybody got access to desktop PCs on their uh, places. And then followed up with internet, which altogether transformed the world. And now, in last one decade, or maybe 15, 16 years since, we have got access to a very powerful device in our hands, which has as much or more power than the early computers and all the machineries which are available to the human beings. So the idea of this slide is to just to give you like where this all this revolution originated. There was an automobile industry which started at a similar timeline, and then there was an electronics industry which started with the invention of this triode. So let us see how the world looks like with respect to these two industries now. Okay, so just to give you an idea, I have taken example of this car. So this is like a normal standard modern car, Toyota Prius model 2024, and it has a typical mileage of 57 miles per gallon or 24 kilometer per liter. So generally, for any whenever we want to compare or like benchmark any technology, we have some parameters. Like we generally ask like what is the mileage of this car, what is the range of this car, etc., etc. And this is how a modern transistor looks like. This is a modern FinFET transistor. This is a picture, and these are the scales of it. So you see where we started from, like almost 100 years back. This was the early stage of innovation, and now this is how these modern devices look like. But can you imagine, like, if automobile industry has made a similar progress as the electronics industry has made, like evolution of this electronic control device, which was a vacuum tube device, to this one, the modern FinFETs relies in semiconductor technology. If the automobile industry would have made similar progress as the electronics industry has made, so comparing the benchmarks, the mileage of a modern car should have been this. Can you just imagine? The idea of showing this number, oh, I understand this is not a realistic number, but the idea is like how much progress the electronics industry has made from the vacuum tube diodes 100 years ago, from where the all the origination of electronics and modern technology started, to these FinFETs, which are powering all our modern devices. But automobile industry, all I agree, like they have also made a significant progress. But if you put the numbers, so it shows you like all both these industries and revolutions have changed the face of modern world. But the emphasis is like semiconductors have the kind of progress they have made and the impact which they have made in our daily lives. I think Dr. Salman in his presentation gave very good and very lot of examples, right from medical to automobiles, EVs, and also the strategic sector, etc., etc. So this is what the impact of semiconductors is in our modern life. One more example which I want to give, and this is like a recent example. So let us not go 100 years back. Let us just compare last 40 years or 4 decades. So 4 decades ago, we used to have these kind of desktops when Apple and HP, all other these modern companies came up with their own version of PCs, personal computers. And this is what a modern Apple Mac laptop looks like. So just see like how much progress has been made. The CPU speed used to be 6 megahertz, now it is 5.8 gigahertz. So almost 100K times improvement in the speeds of the modern computers. Similarly, memory, the amount of memory, the data that can be stored, or RAM, which is basically used to do the processing. So that has increased almost 200K. Then the storage, the all the PCs or computers have hard disks in them. I'm giving example of a typical laptop, not some supercomputer, etc. So again, 200K times improvement. And then the price. The most important thing is like even though we are seeing the factors of improvement in millions and 100K times factors, but the prices of these devices have reduced. So don't you feel it is very strange? Which other product or equipment or any service which humans use in our daily life, the price of that products gets decreased even in 40-year time frame. But we know like anything, the mobiles which we used to buy maybe a decade ago and the one which we are buying now, they have 100 times more processing power and all the features, etc. But the prices have almost remained same, or in some cases they have reduced. So this is like the emphasis is like what is the reason behind this. So obviously I think you are getting my point. I want to emphasize like the semiconductors are playing a big role, why these kind of improvements are there. Again, so as I was comparing automobile industries with electronics industry, so again I'm taking an example of a automobile, a car. This is a 1982 model Ford Mustang, and this is a 2024, and these are the some comparative figures. And you can see the mileages, they have improved almost 1.4 times. The speeds are 2.32 times faster. Horsepower is 5 times. Price is almost 5 times. It has increased. So again, my point of putting these examples or slides is to give you what impact the semiconductors have made in our daily lives. The products which we are getting today, they are not only million times better or powerful or feature rich, but they are coming almost at same price, or in some cases the prices are reducing. So just if you think about it, if you take out all these luxuries which the semiconductors have introduced in our daily life, if you take your mobiles or laptops, or you take the feature-rich cars from your life and your refrigerator, AC, everything, you just imagine like what kind of life we will be having. So I think we should be thankful to the people who are the forefathers of this semiconductor industry. They have contributed to it, and this the fruits of their innovation and their hard work which we are reaping today. Okay, one more example. So this example just came out of my curiosity because there was a requirement. I was looking for a ceiling fan. So I was amazed like what a modern ceiling fan looks like. A ceiling fan is a very basic device to give you a moving air. But can you imagine what kind of features they have built it now in a modern ceiling fan? Wi-Fi, Bluetooth connectivity. You can connect your mobile to your ceiling fan, you can play music, change the lights, etc. There are smartphone app controls, voice control. You can control your ceiling fan using the Alexa and all the voice control softwares. They are very high efficient because they are using BLDCs motors. These are very efficient motors. Then I talked about lighting, etc., remote control, scheduling, automation. So just imagine the purpose of a fan is just to give you a moving air when it is in hot climate. But there are so many features now built into it. And what is the factor behind it? Again, the point comes out to be semiconductors. If we do not have these semiconductors or ICs built into it, all these features cannot be put into a simple ceiling fan. And this is not a example of a only ceiling fan. You imagine any other device in your household. If you have a lighting or any other refrigerators, even the simple sound speakers, etc. All these are now enabled with the modern wonders of semiconductors and giving you the flexibility of all these features. You can connect them through Wi-Fi, Bluetooth, voice control, everything. So again, point is, if the semiconductors would not have been introduced in our lives, so we would have missed all these luxuries in today's world. Okay, so I think I gave you enough examples to emphasize my point. Like semiconductors have revolutionized our world and our day-to-day life. And I think going further, as we are seeing revolution in AI and quantum computing and all other things, you must be hearing about large language models, ChatGPT, DeepSeek, etc., etc. We just cannot imagine like what the world will look like maybe 10 years away. But okay, now let us move little bit back and just understand what are semiconductors. So basically, there are if you divide all the materials which you see around you, I think they can basically be divided into three categories. We have conductors, we have insulators, and there is a category of materials in between which are called semiconductor. So we understand what are conductor. Conductors are materials like if you try to connect a source of electrons to it, moving electrons, they will pass the electricity through them. So there are metals like gold, copper, iron, aluminum, etc. All these materials which are available in earth, you mine them and then you made metal conductors using them. They can be used as conductors. So but point is like if you try to flow current through them, it will just pass through it. You have no way to control it because you must be seeing there are transmission lines through which a wire electricity comes to your homes. So if you switch on the current through that electricity wire, it will simply flow it. You have no ways to control it. So these are conductors. And then the opposite category is insulators, the materials like rubber, plastic, etc., etc. So you understand if you try to pass a current through them, if you connect a live metal electricity wire to them, there will be no current passing through them. So these are another category of material. But ultimately, if you want to basically send some signal or some information through a way, a continuous current flowing through a conductor or no current flowing through an insulator does not serve your purpose. So we need another category of material where the flow of control current can be controlled. So there comes into picture the new category of material called semiconductor. So the beauty of semiconductors is like they can allow the flow of control current through them, and they can also stop the flow of control, current through them, and that depends on the kind of doping or the impurities which can be introduced into them. So based on the doping concentration or the kind of doping you do in semiconductor material, doping is like in if I try to explain in layman term, like you are mixing something into a semiconductor material, and the kind of materials which are called semiconductors are like silicon, germanium. So in a periodic table, there are more than 100 elements. You must have gone through that. So conductors are one class of insulators are another, and then there is semiconductors. So silicon, germanium, gallium, arsenide, these are compound semiconductors. So these are different categories of materials which can be used as semiconductor based on what kind of doping is done and how much is the quantity of doping in them. So by controlling the doping concentration to the semiconductor material, the flow of control current can be controlled. And why they are important? Because obviously, whatever things or features which I discussed about, whatever the like, in order to do a Bluetooth, or you need to connect your device wirelessly to some other equipment, you need some kind of signals to be passed, and those signals are generated and processed inside the semiconductor material based integrated circuits. So we will be going discussing that also in maybe tomorrow's lectures, how the integrated circuit looks like. But the overall idea of today's lecture is just to give you a basic overview. Just remember, like just similar to conductors, insulators, which have their own role to play in our daily lives and the different kind of products which we use, semiconductors have another significant role. And a unique thing about semiconductor materials are like we do not see them in our usual life. Okay, we are using a mobile phone or we are using our cars, etc. And those semiconductor material based ICs or chips are embedded in those products, but we do not see usually with our naked eyes in our daily lives. Whereas other materials, all the conductor insulators, I think we are seeing the being them being in use in our daily lives. So in a way, that also puts some impact on why most people are not aware about the beauty or the potential of semiconductor, what kind of role they play in our lives. Okay, so semiconductor is a class of material, but inside semiconductors, there is a particular device which is called a transistor. So the transistor is the engine behind the semiconductors, which basically drives all the electronics. So all the ICs or chips or electronic circuits which we are talk about, whether we talk about analog, digital, RF, Wi-Fi, etc. So there is a device called transistor, and as you can see in this picture, there is a basic architecture of that device. There is three terminals in it: drain, gate, source, and the flow of current as shown through this flow of arrows. The current through source to drain or drain to source based on whether it's N type or P type MOSFET can be controlled using this gate terminal. So this property of a transistor to control the current flow through its terminals is what makes it a basic fundamental block which defines all the growth in semiconductor industry. So you must have heard about like this is a technology called 180 nanometer node, 130 nanometer, 65, and nowadays world is moving to 753 nanometer. So what is that nanometer? So basically a transistor looks like this, and there is a certain amount of a distance between the source and drain terminals, and there is a gate in between it. So this is called a channel. So this channel is what the distance of this channel is what define the technology node of any CMOS technology. So if this channel is 28 nanometer, basically in this technology or in this fab, the transistors with channel length of 28 nanometer can be fabricated. Then you say like this technology is 28 nanometer. If this length is 7 nanometer, then it is called 7 nanometer technology. So this is a basic parameter which defines the semiconductor technology node. And why is it important? So basically, the smaller the channel length of a transistor, the faster it becomes, the less power it consumes, the smaller area it takes. So all those are the features which basically defines the processing powers. For example, the modern GPUs, which we listen about in our daily lives, like the NVIDIA, AMD, Intel, whatever developments they are doing at the leading edge nodes, less than 10 nanometers, 7, 5, 3 nanometer, because they need very high speeds, processing power, etc. So that's why our technology node or a channel length of a transistor is important. So this is a basic cross-sectional area of a transistor, a MOSFET transistor, and this is how this symbol looks like. Ultimately, when we want to design something using this transistor, we need its properties or models in form of a symbol which can be used to do designing. I'm now going back to design flow, which we'll look in tomorrow's lecture. And this is how a transistor symbol looks like. And this is just to give you an example of how a circuit looks like. So this is an example of an audio amplifier, the audio which you listen from your mobiles or your speakers, etc. So there is a certain kind of a circuit behind it, and there are different kind of transistors used in that circuit. Like this is a MOSFET transistor, these are BJTs, these are resistor, etc., etc. All these elements combine, and then they do a certain kind of function which is required from it. For example, in this case, we need to amplify the signal and send it to drive a speaker. So this is how a transistor, which defines your technology, can be used in an electronic circuit. Okay, so just to give you an analogy of what this is again a simple layman term, what a transistor is and what basic functionality it do. You must have seen we use different kind of taps or faucets in our home. So what is the purpose of a tap or a faucet? We have a lever on the top of it, or there are valves, and by controlling the spin of a wall, the how much we rotate it, we can control the flow of current. So you can just imagine the transistor is similar kind of a device. By changing the voltage over this gate terminal, the amount of current which can flow from source to drain, and again that current defines some kind of a signal processing, whether it is an analog and digital domain. So a transistor can be imagined as a similar to a water valve or a faucet used in your homes. So this is how a transistor can be thought of. And again, in order to, for example, we know whatever water we are getting in our homes through different pipelines. So there is a water source. It can be an ocean or a lake or a water body. Our water is pumped from that source, and then through different mechanisms, there are a lot of valves used. So basically, the idea is like if you want to get water in your home, you need to uh, control it through the different kind of walls, etc. There in between, and then a final water comes to you. Similarly, if you want to, in electronics or signal processing formats, if you want to send a signal, if you whether you want to amplify it, you want to filter it, you want to send it is in a digital format, analog, or you want to transmit wireless, there there is a transistor in between, or maybe there are several transistors. If it is an analog circuit, there may be few hundred transistors. If it is a digital circuit, there may be millions of transistors. So basically, the role of a transistor is to process a signal. It basically processes this signal in analog, digital, whatever domain. Performs various functions on that signal. It can be like amplification, filtering. Maybe there is kind of some kind of digital signal processing happening on that signal. And finally, it goes outside and performs its function. So again, the idea is to give you a basic overview what is a transistor and how what is important. Basically, you can say the transistor is the engine of a modern semiconductor industry. Any integrated circuit, it will have millions or billions of transistors. They have their own specific role to play in it, and accordingly, a chip functions based on what kind of properties of their transistors are used. Okay, so I think in earlier slide we saw like what kind of impact this overall semiconductor industry has played, what kind of advancements it has made. But again, that is a very top level overview. In order to understand a little bit, if we want to go a little bit deep and want to understand what exactly is happening in semiconductor industry, we have to see what kind of advancements had happened in transistors over the time. So I think the first transistors were developed in 1950s. I don't remember, I think 57 or somewhere. And so the benchmark taken is like by the 1965, the semiconductor industries had developed a little bit, and the transistor size at that time was 10 micrometer. By size I mean to say the channel length. So because this is one parameter which defines all the other properties of a transistor. So in 1965, the transistor's channel length which we used to have was around 10 micrometer, and in 2024 or recently the kind of channel length which we are talking about is 2 nanometer. So in last almost 35 plus 60 years, 5,000 times improvement has happened in channel length. So by improvement, I mean by reducing the channel length, the speed of your transistors have increased many folds, and also the area has reduced and the power dissipation has reduced. Okay, so in 1965, the amount of number of transistors which used to be placed on any the all the kind of state of the art chip at that time was around 2300. And in modern times, today's time, the I think this number is for the Apple chips, the chips used in the Apple like latest Apple iPhone. So the number of chips are transistors are 58 billion. Just imagine how much improvement has there. The factor has been 25 million times. So these much number of transistors per chip has increased over last 60 years. Again, the switching speed, the speeds basically the speed at which all the when I talk about switching speed, basically I'm talking about the digital chips like the CPUs and GPUs. They used to process their signals at 1 megahertz in 1965, and in modern times they are working at 5 gigahertz frequencies, so 5,000 times improvement. And all this improvement which we are seeing in number of transistors, switching speed, size, but just see how much improvement has been made in power dissipation. Uh, because ultimately, whenever the chips are functioning, they need some power. But we do not want that power to be too much. Ultimately, we understand like if more power is consumed, that is not good for our overall product. We want our products to be as efficient as possible. Obviously, we want our mobile phones to be charged once in a day and it should last more than 24 hours. That is what we expect. We do not want to be charging them every 4 hours or 6 hours. So ultimately, if, with all this improvement, the power efficiency has increased a lot. So the power used to dissipate in single transistor of 1 watt at in 19 like 60 years back. But in modern transistors, since they are very small, they do not require too much static currents. So the power dissipation is just 0.01 microwatt. So all this improvement has come with benefit of reduced power dissipation also, almost 100 k times. And this is the integration density. By it, I means like how many transistors can be integrated on 1 centimeter square of chip area. So 60 years back, in 1 centimeter square area of a silicon or whatever semiconductor material was used, was 1,000 transistors can be put on 1 centimeter square area. But in today's chips, almost 10 billion transistors can be integrated on the 1 centimeter square area. So the improvement is almost 10 million times. And this is because the channel lengths have reduced, the area of the transistors have reduced. And okay, so just to let it go a little bit further, why this improvement has happened? So all this improvement has happened because the manufacturing process or the foundries or the fabs, you must have heard about TSMC, Intel, Global Foundry. They have improved their fabrication processes so much. The equipments developed by all the equipment manufacturer, which we'll be seeing in our upcoming slide. So this improvement has happened because of the effort of all the manufacturing teams, the real people who work in the foundries, the kind of effort or the improvements they have made, innovations they have made. This effort has been made by them. And based on the kind of devices which the foundries provide to the designers, engineers, based on that, they build their chips. Because ultimately, foundry should be capable of fabricating or building these kind of dimension of chips. Then only a designer can use that transistors, the data or information provided by foundry in form of PDKs to do their designs. So I think we should all be grateful to all the people who work in foundries, the kind of innovations they have made. Because if these innovations in manufacturing would not have been made, we could not hold all these modern marvels of products which we are using in our daily lives. Okay, so this is a very interesting development which happened sometimes in 1965. So this is called Moore's law. I think some of you might have heard about it. So what is Moore's law? It is basically a prediction which was made by Gordon Moore, who was a co-founder of Intel in 1965. Because at that time, what was happening is like they were observing like the amount of transistors which they were able to fabricate on a piece of silicon. It was improving drastically. So Mr. Moore, he observed like in every 2 years, he was able to approximately double the number of transistors which were they were able to fabricate. So what I mean by that is we saw this integration density. So what he was observing was after every 2 years, the number of transistors which can be fabricated in per unit area, like centimeter square, it could double. Like if in 1961 these were 1,000 transistors per centimeter square, in 1963 they could fabricate 2,000. Again in 1965 they could do 4,000. So every 2 years, the number of transistors they were able to fabricate on a silicon area, it was getting doubled. And why it was happening? Because of the improvement in manufacturing processes which the engineers and scientists were developing at that time. So based on that, he made a prediction. Like he told, like this kind of improvement will keep on going. Like after in every 2 years, or ultimately he gave a number of 18 months. Or like in every 1.5 years, the number of transistors which can be accommodated or fabricated on a silicon area will get doubled. And this kind of prediction kind of become a Moore's law. And what happened was like this became kind of a driving light for the industry. So the semiconductor industry took this law or prediction very seriously, and they made all their efforts like to keep following this development. They wanted like after every 2 years, their number of transistors which they can put on a silicon area gets doubled, and that's why we are seeing these kind of improvements. You must have observed like every maybe like Apple is releasing their new iPhone every year. They are trying to put a new feature every year. What is the reason behind that? It is because of this, because the fabrication, the wherever they are getting their chips fabricated, they are able to put the double the number of transistors. By putting the more number of transistors means like they can put more features on that chip. So that is kind of what Moore's law is, and this law ran for very long number of years, almost 6 decades. This industry was basically able to follow this law. They were able to make the improvements, whatever they are making. But in last few years, it has little bit slowed down. But still, people are trying to make the improvements in their chips or in their fabrication processes by other means. Like they are trying to evolve new packaging methods or the other methods like integrating multiple dies on inside a single package. So, but the idea is like this law played a very big role in driving our industry because it gave you the people or the industry leaders roadmap. Like this is what we need to follow, as can be seen in this. Uh, as can be this in curve, like this started in 1960s and up to 2010, we can see like the prediction is linearly following this Moore's law prediction. So, but over the, as I told, our last few years, it has slowed down, but still people are trying to make up for that loss. Okay, one interesting example which I want to share with you is like this is a very popular uh, Nokia mobile phone in 2004, Nokia 6600. It was, I think, 2 decades back, it was rage among youngsters and all the people because it had a very good camera in it and all that. So this model was developed in 2004, and again in 2024 Nokia relaunched a similar version of this phone, and it gave it a same model number, that is Nokia 6600 5G, but all with all the modern features, but the form factor they kept same. But now just imagine this 2004 model costed $400, and this model with 5G and all the modern features in 2024 it costed $290. So can you just imagine, like even after 2 decades, a product with many more features in it and lot of sophistication in it, but it is costing almost like $100 less than it. So the emphasis of putting this point is like there is I cannot imagine any other industry which can give you a product 2 decades down the line and with many more features and still lot cheaper than what it was 2 decades back. And so this is a modern marvel of semiconductor industry. This happened because all the chips inside it, which were used to build this chip, the number of transistors which were put in a similar kind of area in last 2 decades might have increased multi-fold times. And all those chips, the costing, the processing power have increased lot, but costing has reduced. Basically because now the more number of chips or transistors can be accommodated in the same area, and all the manufacturing processes have improved so much. So this is what a semiconductor revolution has done to our lives. Like we are reaping a lot more benefits in our modern times, which we could not have imagined like 2 decades back. Okay, so I think we heard about all the benefits and all the developments which have happened and how it has impacted our day-to-day lives. But just now, this slide covers you a basic overview of how a semiconductor IC development cycle looks like. So this doesn't go into too many details, but it gives you a top level overview. If just to understand like what exactly happens with a semiconductor, how this kind of piece of element which is mined from some mines in from the earth gets converted into this kind of a chip, and this chip then gets built into your smartphones or laptop, etc. So this is how a silicon crystal looks like. Basically silicon is nothing like it is sand. So almost 70% of earth's surface consists of a sand, but the kind of sand or silicon which is used to manufacturing semiconductor materials, it is a very high purity silicon we required. So there is a specific mines in US. I do not remember its name right now. I think spruce pine something. So that area has a very high purity silicon available. So this silicon is mined from there. Now this silicon is now again converted into this kind of silicon ingots. So this is a cylindrical kind of structure which is basically built from this silicon crystal by melting it and several other processes used. And this kind of cylindrical kind of structure is extracted from silicon crystals. And then from this cylindrical structure, these kind of a silicon wafers are basically diced. So as you can see, this it has a long length. So maybe from this single structure of a silicon ingot, several silicon wafers are getting extracted. And now these are the silicon wafers over which a manufacturing of a IC or integrated circuit takes place. But before, and these are the wafers which are processed inside a foundry. There are several other processes which goes over the silicon wafers. I think that is not part of our domain because fabrication in itself is a very deep and complex subject. But these are the wafers, and in order to build something relevant, ultimately we want to build something. So we want to build an integrated circuit on these wafers. So somebody has to design those circuits. Somebody has to decide what kind of structure gets built, where the transistor will be, where the resistor will be, how will they be connected, what will be the doping needs to be done on which part of the wafer. So all this is basically work of a designer. So there are design teams. These are electronic or electrical engineers. They know their field. They understand how a transistor works, what happens, how to connect different structures or elements like transistor, resistor, capacitor to generate a certain kind of a signal. So all that is part of a IC design. We also call it VLSI design, very large scale integration. So these are the dedicated teams or engineers whose only task is to design the circuits. Okay, so just to give you an example, we want to have a For example, every year Apple comes with a new iPhone, so they have a faster processor in it, M13, M15, something something. So who are the people who design those chips? So these are the design teams. They design those chips. This is just a layout. This is how structure will get imprinted on these wafers. So and these are imprinted through masks. So this is a design process. Then a designer sends its design to a foundry, a fab. Let us say it is a TSMC or Intel or wherever you want to fabricate your design. And then inside a fab, several processes, fabrication processes, lithography, etching, metallization, all those, they are very complex, hundreds and thousands of processes. And a typical time period taken to basically generate a processed wafer inside a foundry, it can vary from 2 to 4 months, depending on the fab and the technology node on which they are working. So this design gets imprinted on this wafer through all the sophisticated machinery available in a fab. So this is our final processed wafer. A single wafer consists of same design, basically replicated several times over this wafer. For example, we have a single design of a chip. It so there are thousand such chips getting imprinted on a same wafer using masks. But now we want to separate them because this is a single wafer. This cannot be directly used inside a product. It consists of several chips. So we need to extract those chips. It is something similar to if you can imagine a pizza base. So you cannot eat whole pizza at once. You need to basically cut it and then extract the piece from a base and then eat it. So something similar you can imagine. This is a single wafer, then the dyes are extracted. So there is again a separate process. There are basically dicing machines. There are diamond cutters and laser cutters which are used to basically cut this wafer and extract different dyes, as can be seen in this picture. So this is a dye which has been extracted, and this dye consists of this design which was designed by a designer. Now this is what is called an integrated circuit, but this is a circuit which is integrated by using maybe hundreds or millions of transistors and other elements like resistors, capacitor, inductors. And then this dye cannot be directly used as such inside a final product like a smartphone or a laptop or a mobile. You need to basically put it inside a package. So this is a package which consists of basically cavity inside it, in this cavity this dye is placed. It is pasted using special chemicals, and then from this dye the metal wires are connected to the periphery of the package, and at the side of the package there are metal pins. So this is what is how a final package IC looks like, and this is what is used inside your products. This IC then gets soldered on a PCB or whatever a base material is, and then that PCB is finally used to build a final product. So this is just a summary of how a semiconductor IC development looks like. This is a very brief overview. Uh, just remember, like each of these processes behind them, there a lot of effort takes place. There are several other specialized processes which are taking behind them, and the idea is to give you a brief overview, but our main focus of this lecture series or this training is to show you how this role of IC design is. We will go into little bit detail of IC design, which I will be covering in next few lectures. Okay, so this is just now we saw like how semiconductor development looks like, what are the different steps and processes. And here I just want to give you a brief idea of how where the world is moving. I think Dr. Salman in his introductory slides also give you an idea like what all the different developments are happening in world. So on the left side, these are top 5 industries as of now. These are the biggest industries where like lot of economic activities are happening like e-commerce, online retail, oil and gas, I think, which like Saudi Arabia is leader in, and then life, health insurance, commercial real estate, pension funds. So these are the driving industries of modern world. So these are very big industries, and but these are the growth rates. You can just see how much growth is happening. So these are almost single digit growths, and although e-commerce and retail we see double-digit growth. But I think again, we understand why that is happening, because everything is going online now. And these are the industries which have the highest growth rates as of now. You can see these are all double-digit growth rates. E-commerce, online retail, again, told you, like, because everything is going online now. Then green energy, we know like the world is trying to reduce its dependence on oil and gas, and they want to use renewable energies, solar, wind, etc. And lot of electronics is used behind that. To convert a solar energy into an electrical energy, you need to basically convert the solar energy into electrical using solar cells, and then whatever current is generated, you need to store into batteries, you need to convert DC current into AC energy. So behind it, lot of semiconductors are involved, and this industry like right now it maybe is less than $1 trillion, but you can see the growth rates. AI and machine learning, I think I need not go much into detail into it, because we hear it every day. Like, so much development is happening in AI field nowadays, and the growth rates are expected to be like more than 20%. Cybersecurity, the more digitalized the world goes on, the more there is the need of to protect our data and to protect our systems. So that is again a very high growth rate industry. And augmented reality. So we want to put everything into cyberspace and use to connect it through VR and AR equipments. So again, that, so the idea is like the whatever industries are growing at very high pace and which will basically replace these legacy industries, all of these are dependent on electronics and again semiconductors. So my idea is to just to give you an idea, like in maybe 30-40 years back, our parents or our elders, they wanted to work into some kind of a mechanical or labor intensive industries, because that was what was growing at that time. But in modern world, we see what kind of industries are leading the charge. So these industries were become very big, and since they all use semiconductors, we can indirectly make an inference like what will be the growth rate of semiconductors. So that is what I want to emphasize, like semiconductors and global growth is correlated. You cannot imagine like the world to grow further and semiconductor industry will not. Maybe it will go with double rate with what the global GDP growth rates will be going forward. Okay, so this slide shows you what are the I think in the beginning I told you, like semiconductor industry we think of as a single monolithic industry, but it is not. There are various subparts of it, and this slide captures very well like what all are the subparts and what all these are some of the big names in this industry. I think some of them you might be knowing. I will quickly go through them, and I will be covering them in future next slides also. So there are design IPs. So these companies do not own anything. Like physically, they do not own any fab or any manufacturing. Their USP is in designing. They design, they put their ideas on the softwares, and then they design those circuits, and then they send it to somebody else to do the fabrication. So these are the design IP companies like ARM. Then EDA companies, in order to do designs, we need sophisticated softwares. Just like in order to work on a laptop, we need an OS, and Windows is from Microsoft is the leader in it. Similarly, if you want to build chips, you want to design something, you need EDA softwares from these big companies, Cadence, Synopsys, Mentor Graphics, Keysight. Then equipment. So these are the companies who provide equipments which are used inside the foundries, fabs. These are the various leaders in that industries: Applied Material, Lam Research, ASML. These equipments are used to run different kind of processes: lithography, etching, metallization, all those different kind of steps. Then raw materials. So inside a foundry, as we know, wafer is one raw material, but in order to do processing on a wafer, different kind of chemicals are required. We need to do the etching, we need to deposit photoresist, then need to etch that photoresist, we need to use masks and a lot of sophisticated chemicals and high purity gases are used, and these are very toxic elements which are used. So there are specialized companies which develop those raw materials and provide to foundries to do the processing. Then fabless design. So these are the companies uh, who actually design the chips. So design IP companies, they just they basically build an architecture or top level structure of how what circuit will look like or do. But these are the design companies, fabless design companies, who basically convert those IPs, or they develop their own IPs and then convert those ideas into actual fabricatable chips or designs. They generate GDS or final tape out files and then send those files to foundries. So you must have heard about NVIDIA. NVIDIA is popular because their GPUs are in high demand nowadays. Qualcomm, all the 5G chips or all the communication chips are mostly from Qualcomm. Apple, they build their own processors and they have a very tight hold on all the hardware and software of their devices. AMD, again, they are popular for CPUs and also now they are coming up in GPUs. Similarly, MediaTek, they are competitor to Qualcomm, building processor chips for mobile phones. Marvell, Xilinx. So these are all the fabless companies who their basically aim is only to do the design. They do not do any fabrication. They will do the design. They own the ownership of their design, and they will simply pass on their designs to foundries like TSMC, Global Foundries, UMC. They will do the fabrication of their chips, but ultimately the IP or the designs will be held by these fabless design companies. Okay, so now next comes the foundries. So these are the big daddies of semiconductor industry, and they are also the most capital and resource intensive part of the semiconductor industry, and this is what is in limelight nowadays. We all hear about how important TSMC has become in last 5 6 years after COVID, because they own the leading edge technologies. This TSMC is the only foundry which can do like 2 nanometer or 3 nanometer kind of chips. Even Intel is not able to compete with them. So basically all the big high-end chips from Apple, Qualcomm, Nvidia, they get fabricated in TSMC. Then Global Foundry, they have their own niche. I think they do fabrication around 14 nanometer nodes, and their USP is in basically analog intensive RF kind of power electronic, those kind of chips. Then UMC, this is again I think a big foundry in Taiwan. So the role of foundry is to fabricate those chips which are sent by design companies, fabless design companies. Once the wafers are fabricated, then they need to be diced, packaged, assembly, everything. So there are dedicated companies who do that part. These are called ATMP companies: assembly, testing, marking, and packaging. So these are the foundries pass on the wafers to these companies, and rest of the thing to convert the wafer into a final package chip will be done by these companies. And ultimately the chip will be owned by fabless companies, because their name will be imprinted on those chips, and everything, the rights of these chips which are compiled by these ATMP company will be sent back to fabless company, and then they will market and send it to the final customers. Okay, so another class of partners of this semiconductor industries are integrated device manufacturer. So as I talked about, these are fabless companies. They only do design, they only do foundry fabrication, and they only do ATMP. But there are another companies who do all these things by themselves, like the Texas Instrument, Intel, Micron, NXP. So these companies, they do their own designs, and they again then they have their own foundries or fabs where they send their own designs, and then they have their own ATMP units. So all these companies, they have a complete control of all the design, manufacturing, and ATMP part. So these are called integrated device manufacturers because they hold the complete supply chain in their own control. They do not want to send their designs to some other manufacturer, and so they are called IDMs, integrated device manufacturers. So this is just overview, and again, so here I talk about little bit in detail about these all the things which I have covered in previous slides. So IP design, as I mentioned, they design their own intellectual property IPs. And then those IPs are passed on to fabless IC design companies. Using those IPs and their own designs or IPs, they build their products. These are built using the tools from EDA companies like Cadence, Synopsys, etc. Then there are equipment companies who supply complex or sophisticated equipment to foundries. Then there are raw materials which are used for processing of wafers, different kind of chemicals and gases. Foundries are the big daddies of semiconductor industry, big who basically take designs from fabless companies and then manufacture them into final process wafers. Then another class of manufacturers are IDMs, which have a complete control on their manufacturing from design to final package chips. And then there are ATMP. ATMP are associated with foundries who pass on wafers to ATMP, and then they do all the other assembly, testing, packaging, or and then send those back to the original design, that is design companies like fabless companies. So this is these as you can see in the starting I mentioned, like semiconductor industry is not one single industry. There are several players in it, and they have their own dedicated role and part to play. And you can now understand, maybe some of the listeners might be from different domains. You might be from chemical background, you might be from mechanical, electrical, different kind of domains. So you understand, like all the different scientific domains or technology engineering branches, they play a role in semiconductor industry. So based on your specialty, you can just explore further on it, like which where you feel like you have specialized skills, or you whatever studies you are doing, they fit into the specific part of a semiconductor industry, and then try to build your specialization and try to build your career in that domain. Okay, so here I have mentioned different kind of domains in semiconductor industry as discovered in previous slide, and what kind of the career opportunities are. And then some skills, these are some important skills which are required in that particular domain. For example, IP design. So there are roles of IP designers. There are people who design those IPs, and then designers pass on those IPs to verification engineers, and those they verify. So what kind of skills are required? You need to understand about what is the VLSI design. If you are into analog or digital, you have to be good at your domain. You need to understand the concepts of analog IC, digital IC, mixed signal, RF, whatever the kind of IP design company or target. And then VHDL, EDA tools, obviously you need to know. And then system design. These are some skills. Similarly, fabless design. So fabless designs are like for the IPs designed by IP designers. These IPs are used by these chip designers, and they then use those IPs and their own design sometimes to build a complete chip. So IP designers, they do not build a complete chip, they just build the designs. The chip designers are these people, they do the final designing, and again they need these kind of a skills. You need to understand IC design flows, EDA tools, what is spice simulation, circuit simulation, various kind of CAD tools. And then there are EDA companies. These are the companies which build the softwares like Cadence, Synopsys, Mentor Graphics. And these people's, the chip designers and IP designers, they use the tools from these EDA vendors. So here you need a kind of EDA developers. So I think for this you need to have some understanding of semiconductor design, and also you should be good at software skills. So you need to basically code all the semiconductor related ideas or requirements into software to build those EDA software. So the skills are these software development, circuit design, optimization, algorithm, etc. So basically this is more towards software. But again, if you have some interest in semiconductors, you have some knowledge, and also you are good in software, you can fit into these roles. Then equipment industries, so they are equipment engineers, process engineers. So based on the specific tool manufacturers you are targeting, you need to understand about the processes which those tools work on, like lithography, etching, different clean room procedures, equipment maintenance, etc. So these are the roles which are suited to this equipment manufacturers like Lam Research, ASML, KLA, Applied Materials. Then raw materials, so basically material scientists and process engineers, or if you have a chemical background also, then I think these kind of industries suit your roles. So you need to understand about material science and silicon production, quality control. Then foundries, obviously foundries, they have the basically process engineers, production managers, and also the equipment engineers who take care of the equipment engineers. You should understand about the semiconductor fabrication, like what kind of processes you are running inside a fab. You need to understand about yield management. Basically, the very important concept in foundries is to control the yield. Like you want to get maximum number of good wafers and dies from a foundry. And then obviously clean room procedures you should know about. So integrated device manufacturer, I think similar kind of skills are required from as similar to foundries. But then they, since they also do some design work and also the ATMP, so those kind of skills are also basically IDMs have a role plays for all these kind of engineers because they have a complete control in-house of in-house manufacturing. And then ATMP, there are testing engineers and packaging engineers, and they should have possess these kind of skills. Like they should understand what are the different kind of testing and measurement equipments. They should understand those equipment, their settings, how to use them. And then packaging, there are different kind of concepts used in packaging, quality control, etc. So all these are the different kind of industries, and I have mapped what kind of roles different engineers or skill people play in them and what kind of skills are required. So maybe this can give you some idea what kind of skill you possess, and then accordingly you can think about building your career if you are really motivated into entering this industry. Okay, so I think going forward, we will be, as part of the next few lectures, we will be focusing on specifically on IC design and that to analog IC design. So I want to emphasize little bit more on to it, like what is IC design and different types of IC design and what kind of role they play. So basically, IC design, they are divided mainly into three domains: analog ICs, digital IC, and mixed signal IC. So let us start with analog IC. So basically, these are the engineers which work on circuits which are processing continuous signals. Like signal can be in form of voltage or current, and these are continuous signal. These are not digital signal like 1010. So you are having some kind of a waveform you are getting from some other place like a sensor or some light source or something from wirelessly you are getting it inside your mobile phone. Then you need to process that signal. You need to amplify, filter, or do some kind of other processing on that signal. So these are the kind of activities which analog IC designers do to build analog ICs. And what kind of circuits they build? They build circuits like amplifiers, voltage regulators, oscillators, PLL, ADC, DAC, RF circuits. And what are their milestones? Well, basically, what kind of features they focus on? They want to build circuits which are low power, high speed, noise reduction. They want to reduce noise and implement all these features in those kind of circuits. And one critical role of IC designers are to do simulations, and the main simulation tool which is used is SPICE for analog simulations. So they should be good at that. And then layout. Once the simulation is done, circuit is designed, that circuit needs to be converted into a layout. Layout is basically what gets generated into a mask, and then that mask basically imprints the layers on silicon wafer. So this layout activity is also sometimes role of analog IC designers. Sometimes, so these domains are divided. There can be a analog designer who only does front-end design, simulation, schematic, and then there are back-end designers who only do layout. And then if you are a front-end designer, you need to collaborate with your layout team and verification team, because ultimately everybody has to play its part in order to make your design successful. And then another important role is like if you're working for a fabless IC design company, you have to interact with foundries from where you will get your design manufactured or fabricated. You need to understand their PDKs. You have to collaborate with them if there are some specific requirements. So all those are responsibilities of analog IC designers. So these are some of the skills which are required. You should be good in knowledge of transistors, so especially MOSFETs, BJTs, and different kind of analog topologies for these circuits, like what kind of amplifiers, is it a op-amp, common source amplifier, regulators, different kind of oscillators like ring oscillator, VCO, PLLs, what kind of ADC you are doing, pipeline ADC, SAR ADC, etc., etc. So all these are domains which you should be knowing about. And I think if you are trying to build your specialization in specific field, like you want to do only data converter, then you should try to build your mastery in that domain. Then need to know working with all the EDA tools. So EDA tools are also from different vendors, like there can be uh, like flow from Cadence called Virtuoso, Synopsys Custom. So based on what kind of a PDK you are using and what kind of EDA tools your company or place you are working is providing, you need to be experienced in one set of a tool. That is also very important part, because ultimately in order to put your skills or ideas on a design, you need to understand the tools, because without that, even if you are good in theoretical knowledge but you do not know how to operate the EDA tools, then it won't be like complete fulfillment of your role. Again, you need to be, as I mentioned, need to be good in using tools, circuit analysis, layout techniques. These are all the topics which you should be good at. And this is also sometimes useful for an analog designer. You should understand how a fabrication takes place, and you basically, there are different kind of impacts, especially for analog circuits like mismatch and other things. You need to understand like what role a particular process can play on the quality of your design, whether it can affect the performance of your design. So it is good if you understand the fabrication. It is not a must, but if you have a good understanding, it will help you in your design space. So similarly, digital IC designers. So digital IC design is altogether a different flow. The process used here is different. So basically, digital IC designers work on circuit which process binary signals. By binary, I means there is no continuous signals like waveforms. So everything is converted into binary signals 0, 1, and then based on processing of those signals, the digital designer build different kind of digital circuits like processors, memories, FPGA, and AI accelerators. So these are the altogether different domain. Ultimately, why we move to digital is because digital is more efficient. Here you need not worry about noise and amplification, filtering, etc. You are basically converting your signals into digital domain, and all the processing you are doing in digital domain, which is relatively easy to handle and also less power intensive. So they are, so it's not like analog is not relevant, because ultimately all the physical world exists in analog. All the signals which are generated are like physical signals, the sound, the light, or kind of acceleration, etc. All these signals are physical signals. These are captured by sensors. These sensors do the processing and then converted into digital domain, and then a digital IC plays its role to do further processing. So they have, each of them have their own roles. And what are the responsibilities of digital design? They build logic circuits, data paths, control units. They use RTL coding like Verilog, VHDL system Verilog to build on the codes of their designs, and then they do verification of their design using simulation tools. And their main concern of digital designer is to optimize the power, performance, and area. So they want to design, because digital designs are very big, they use millions and billions of transistors. So you can imagine if there are billion transistors and what kind of power they will take. So they want to optimize the power. They want to, by performance, I mean they want to increase the processing speed of their circuits or designs. And then also they want to put all that design or that number of transistor used to build that design in as small as easy as possible, because we are talking about millions and billions of transistors, so they do not want to build very big designs. And then there are some timing constraints and physical design requirements that also they need to handle. So the kind of skills which are required, they should be good in RTL coding. Ultimately, the digital design starts with an RTL. You need to write an RTL code for your design. The languages used are Verilog, VHDL system Verilog. So this is, I think, if you want to start with, this is the starting point for digital design. Then there are different kind of simulation tool which compile those RTLs codes. These are the different tool names here. Then based on the ITL you coding of your design, you convert it into, you synthesize into logic gates, and there you need to do the timing closure, clock tree synthesis, power optimization. These are the different basically implementations you need to do on your synthesized design. And then again, digital design, they have their own tool chains, different kind of a tool sets from analog design. So I think the leader in digital design is Synopsys. So they have a tool flow called Design Compiler. Then Cadence has Genus, and then this Open Road is an open source tool if you want to do anything on open source area tools. So again, digital designers need to be well versed about their own set of tools. And then comes the role of mixed signal design. So mixed signal designers, so nowadays, and most of the things, they are not only analog or only digital. So they consist of both analog and digital designs. So there comes the role of mixed signal IC designers. So they take both the analog designs and digital designs and then try to integrate them together. So they work on both kind of circuits like ADC, DAC, SerDes, power management ICs, communication interfaces. They take these designs from analog or digital designers, they integrate them, they understand like what kind of interfaces are required, and then try to realize those designs. So again, responsibilities, they need to understand and work with these kind of designs, which are interface for analog and digital circuits, ADCs, DACs, SerDes, clock generators, power management ICs. And one important role is because they are working both analog and digital domains, they should ensure the integrity. What does it like the signals which are passing from analog to digital or digital to analog domain? They should not lose their basically properties. So that integration should be maintained. They need to ensure this kind of thing. Uh, Mixed signal simulations need to be performed. Different kind of approach needs to be taken for mixed signal simulations. Now interfaces are required. These are like USB, MIPI, etc. These are digital interfaces through which our digital data is transferred from one chip to another on a PCB. And then again, they need to be in sync with fabrication engineers or a foundry because mixed signals design is a little bit complex. So they should be talking to the fab engineers or the PDK engineers to understand what are the capabilities of a foundry or a fab and accordingly optimize their design. So what kind of skills are required? Again, they need strong skills both in analog and digital domain. Again, they need to understand with these are the system simulation tools like Verilog AMA, System Verilog, MATLAB modeling. These are the top level simulation tools where you place both the analog and digital blocks and try to do the simulations. They should understand of these concepts, signal integrity, jitter analysis, mixed signal simulations. These are basic things which are required to be known by a mixed signal designer. And again, EDA tools. I think this point is coming again and again. So you must understand, like even if you possess all these knowledge, all these skills, you should be well versed with that EDA flows, EDA tools, because then only you can implement your concepts or designs into actual ICs. Okay, so I think these are few concluding slides. Based on whatever things we have discussed, again, I think we started with automobiles and we tried to saw like where the evolution of this industry took place, how automobiles and electronics industry in form of vacuum tubes started together. But now where all the semiconductors, these are the modern form of vacuum tubes, which have replaced the functionality of vacuum tubes plays roles. So we can see communication industries, there are transistors which are used to build various kind of wireless ICs, electronic switches, which are used to transmit signals from our mobiles or wireless devices. Then there are mobile networks. Behind a mobile, there are like base stations. There are sophisticated like up conversion and down conversion equipments available there. They are all require semiconductors. These are basically all these communication. They consist of mostly analog and mixed signal and RF kind of a chips. Then satellites, they provide all the global communication and navigation. You must have heard about Starlink nowadays. They are trying to provide direct mobile internet to directly to our mobiles. So we will not be dependent on our maybe service providers. You can get access to internet anywhere around the world using the modern satellite communication. And all these things kind of keep you connected all day and everywhere. So I think it's very rare if you are moving to any part of the world nowadays that you are not connected. So the communication uh, basically enabled by semiconductors provide all these benefits to the users today. Similarly, for computing, obviously we know all the machines, the laptops, PCs, etc. They consist of microprocessors enabled by leading edge nodes. And then AI, this is I think this is dominating all the headlines in last 2 to 3 years. And I think every day we are hearing one thing or another, and they are again enabled by high-end GPUs, mostly provided by NVIDIA nowadays. Then there are supercomputers. They are another kind of class of a computers which are basically required for very high complex computation and other requirements. They again use several processors or complex structure of microprocessors. And then again, we all know about personal devices which we are using, mobile phone, other things, etc., or the smart watches, etc., which we are using. Healthcare, as Dr. Salman discussed in his introductory slides, it is again, I think, if you ask me, it has revolutionized the human. We cannot imagine what kind of roles these all the medical imaging and all the diagnostic things plays in our lives. And in upcoming days, people are, I think, the company called Neuralink from Elon Musk, they are trying to put chips in your brains. So basically, you will be the people who are not like they are kind of paralyzed, they are not used able to use their hands or legs. They will be able to move their chip. Basically, those chips can take the signal from outside and they can basically enable them to use their limbs which they have not been able to use due to some kind of a muscle issues or something. So these kind of revolutions we could not have imagined, like maybe even last 10, 20 years back. So all these are enabled by semiconductors. And again, industry, there are, we know every industry is now automated. Earlier, any industry, there used to be a lot of manpower involved, lot of physical labor need to be used there. But now everything is being automated. There are robots or there are sophisticated machines which are controlled by at back of their flow by semiconductors. There are, I think, there are just operators there who need to run some commands or just press some switches, and everything is automated nowadays. So that is also enabled by semiconductors. IoT, so most of other devices, I talked about Alexa and the Google Assistant, etc. So these are all IoT devices, which I think everything we are trying to connect from one device to another. I talked about a simple ceiling fan. So it again is IoT enabled. So all those features are getting enabled by semiconductors. Again, smart factories, agriculture, the semiconductors are playing nowadays roles in them also. Transportation, we know the world is moving toward EVs, electric vehicles from ICE vehicles, and electric vehicles, I think they are all enabled by semiconductor. You cannot imagine an EV without a semiconductor, and there's lot of more and more semiconductor is being demanded, especially in power domain and the compound semiconductor technologies like gallium nitride, silicon carbide. So they are basically driving the revolution in electric vehicles, because there we are talking about high voltages, 800, 3000 volt, 1500 volt, etc. And CMOS or silicon is again, it is good for all the low voltage operations like analog digital chips. But for high power and high voltage, high current, I think there are different kind of materials coming up, compound semiconductors, and those are the materials which are driving the EV revolution. And then we talked about solar energy also. We want a efficient world, green world. So I think the dependency of oil and gas is reducing, and more solar energy is being used. But again, to convert solar energy into an electrical, basically store in batteries, save it as a DC power, and then convert it into an AC, because ultimately everything in our homes are working on AC. So again, lot of semiconductors are required. And again, as with EVs, most of this energy revolution or green energy products which are coming up, they use compound semiconductors, because again, we are talking about high voltages here. And then the last and one more very important thing we discuss is security and space. So defense, we know nowadays, whatever wars are fought or whatever equipments are used, these are not manpower intensive. You need not, there are no more big armies which are fighting the wars. We see like how, what kind of there are missiles being fired from long ranges, and there are fighter jets which are dropping bombs from long distances. So how all this is getting enabled? Because all these ammunition which are being used are smart ammunition. So they have inbuilt seekers and there are radars in it, and you can use the GPS positionings in them. You can feed the coordinate of your target, and those bombs will fly from long spaces without harming the fighter jet or a fighter pilot who is dropping those bombs, and they will struck their target accurately. And what is enabling them? Ultimately, the positioning, GPS positioning, or the radars or seekers which are built in those missiles or ammunition are all semiconductors. And then radars are they used, I think mostly radars are built on compound semiconductors like GaN, kind of semiconductor materials. Satellites, space exploration, I think without semiconductor, it won't be possible to send with the kind of space missions which the world or the leading world agencies are sending nowadays, because a lot of processing and information is involved in it. So all that requires backup of semiconductors. Okay, I think that's all from my side for today. I hope I was able to give you a good overview of semiconductor industry, and the idea was to motivate some of you who think passionately about this industry. There's a lot of scope and lot of things are coming up. I think this is going to be a long drawn developments which will be happening in semiconductor industry. And I think the kingdom is putting lot of efforts. And I think as Dr. Salman mentioned, there's a dedicated SSP programs going on. I think you should try to take benefit out of them and try to get as much exposure as possible, so that whenever this industry prospers and grows in your nearby domain, you are well equipped to enter it. Okay, thank you very much. Dr. Salman, uh, if you anybody has any question, can we can discuss it on a chat. You can please type your question in chat in English. I will try to answer them as much as possible. Okay, so there are some questions coming on. In the slide, in the slide I saw design IP. What is IP? So basically, IP is an abbreviation for intellectual property. In case of semiconductor design, we talk about a design. Design is kind of a software file. We call it an IP, because whoever creates those designs, it is an IP for that company or that person. So they keep and hold on that IP because it is their own design. It takes a lot of effort. So IP is something which needs to be protected. Why is it a circle and not a square? Wouldn't a square cover much more area? I believe you are talking about a wafer. Basically, it is much easier to hold the equipments which are inside a fab. It is much easier for them to hold a circular wafer. I think there is some thing related to that because otherwise, if you make it a square, it is little bit difficult to process the wafers inside a fab. That's why a wafer is kept circular. So somebody is asking if my background is physics, what's the best career opportunity? So I think that's a good question. If you are from a physics background, I think you should try to build in semiconductor device physics. So there are uh, device engineers or process engineers in foundries who basically understand about all the uh, how basically a doping of a circuit is done, what kind of fabrication processes are done, how the electron hole concentration is defined, everything, all the things which are inside a device, a transistor or other semiconductor devices. These are the things which are handled by process engineers who are basically from physics domain. So I think that would be a good career option for you. Okay, I think I am sharing this link. If you want to join a Slack channel, please join it. You can send your request to joining the Slack channel through this office form. And if anybody has any query, we can discuss those queries over Slack also offline. So somebody is asking, is there any opportunities in this domain right now? I think there are a lot of opportunities coming up as I talked about different industries, but then the entry barrier to this industry is a little bit high. So you have to basically develop a focus on a specific domain, whether you want to enter into a design domain or a fab domain or a packaging testing domain. Try to focus on that particular domain and develop some skills. I think a lot of opportunities are coming up, and it is a sunshine industry and a long uh, path forward for development. I think the kingdom is also putting a lot of efforts to build the manpower there. So I think just keep hook up to the industries which are working. Okay, so somebody is telling this form is not currently not accepting responses. Okay, so let me work on the. Please note down this link. I will try to rectify this link, and I think it should be enabled. So please copy this link and keep it with you, and to join the Slack which I have shared on this chat box. Okay, then I think thank you very much. If anybody has any questions, who they can please join the Slack link which I have shared. I will, if any issues with this link, I will try to rectify it. Please be tuned for that. Again, I'm again sharing this link. And if any slides, etc. needs to be shared, we will share it through Slack only. So please be tuned to that Slack. Try to join it. Thank you very much, and we will meet tomorrow at same time for our second lecture and third lecture. Thank you. Bye. Have a nice day. I think we can start now. So welcome everyone and good evening. So yesterday we started with our first lecture. It was kind of a brief overview or a top level perspective of the complete semiconductor industry. So the motivation is to give you an encouragement to like basically share with you what kind of developments are happening in semiconductor industry and how it has become important. So also compared it with one other basically trending industry in world, that is automotive industry, and we saw like what kind of developments and progress has been made in both the industries and how much influence and how much more ahead the semiconductor industry has gone ahead. And most of the today's progress and what all are the sunshine industries or the economic driving activities of modern world, they are all being driven by semiconductor. So I think, and I also shared with you some of the career opportunities, what are the different domains in semiconductor industry. It is not a single monolithic domain. There are several aspects of it. We saw like what is semiconductor design, IC design, fabrication, testing, packaging. Then there are device physics engineers, etc., etc. So if anybody has any interest in specific domain, I think they can find a way to enter this industry. So our main task of holding these lectures is to basically encourage you and motivate you. But now I think it's difficult to capture everything, all the domains in detail. So I'm not an expert on fabrication. So my core competency is in IC design. So I think, and one good thing about IC design is I think the entry barrier is little low from infrastructure point of view. For example, if you want to become an IC designer, you just need to have your skills. You need to have some knowledge about the domain which you want to enter, and then you should know to use the softwares, the EDA tools which are required to do the design work. So in a way, it is that's why the people who build those circuits or who design, they are called designers. Like if you have to design something, they are fashion designers, they are building designers, they are infrastructure designers. So those are the people who have some concepts in their mind and they put those things in the real world. So similarly, the work of an IC designer is to, based on the knowledge he has of the electrical circuits and electronic circuits, and all the skills he has on EDA tools and all the background of semiconductor knowledge, whatever he has, he builds the complete circuit. So like there are people who build those GPUs, CPUs, or 5G chips and communication chips, etc. So there are big teams behind these things. These people collaborate together, these designers sit together, they basically share their concepts, their ideas, and then implement their ideas using the EDA softwares. So that is basically what our IC design industry looks like, and this is the basically work of what IC designer does. So in today's lecture, there are two lectures today. First, I will be covering the theoretical aspect, like what an IC design flow looks like, and we will be talking about analog, specifically analog IC design flow. And then in the second part, we will have a practical demo. I will show you like how these softwares look like, what are the different activities which needs to be followed, what are the different steps which are required in IC design flow. So I will be giving you an overview so that you can get some kind of an understanding and idea like what is actually IC design activity and or flow. Okay, so this is basically the schedule we are following during these lectures. Okay, so first let us start with VLSI. I think if you are in electronics industry, you must have come across this term. So what is VLSI? So the full form is very large scale integration. So as I discussed with you yesterday, in the semiconductors industry basically originated in 1950s, and in couple of years or maybe a decade down the line, the Moore's law developed, and then people got to know like the kind of transistors or the elements which we are able to put on a silicon or semiconductor material is increasing exponentially. So they started putting the terms based on the number of devices which can be integrated on a semiconductor substrate. So they started with SSI, that is small scale integration. So what it means is like they were able to put or integrate approximately 1 to 10 number of transistors. So that was very beginning of this industry. So at that time, the things were not very mature, but still it was a significant development for them because before that everything was discrete. So people used to build their electrical or electronic circuit using vacuum tubes. They were bulky tubes, etc. So but the development or the rise of semiconductors gave them a big leverage to do more development. So they started with SSI, that was small scale integration, like the devices could be put was less than 10. Then MSI, medium scale integration. So the number of transistors as the per the prediction made by Moore's law, it increased to 500. Then LSI, large scale integration, like 20,000. And then came the term VLSI, that is 20,000 to 1 million transistors. So, and then ULSI. So this is what the currently industry is moving on. But somehow this term become very popular, that is VLSI, because in by 1980s, people got to understand the potential of this technology. So what exactly is means by this integration things, like which what is VLSI? So basically we all know like semiconductor, they can hold large number of transistors, but ultimately there are some technology behind it. So there are some techniques or some kind of steps which need to be followed in order to put those number of transistors on a semiconductor material or silicon die. So do all those techniques together, they form VLSI. So this refers both to your design side, like you should have those number of tools or capable tools or techniques by which you can try to put these number of like million transistors on a silicon surface or the die area of maybe 1 mm square or maybe 5 mm square, that those small die areas. And then also the fabrication side. So the fabrication technology should support the designers, or it can be other way also. Like designers should follow the ways or techniques which are followed in foundry. So altogether, this formed a base of a technology, that is VLSI, that is very large scale integration, by which the engineers or scientists, they were able to put large number of transistors on a silicon area. And as I discussed yesterday, what is the benefit of that? Because the more the number of transistors you can put on silicon, then the more functionality it can do. For example, earlier there used to be a separate chip for analog, digital, for Wi-Fi, Bluetooth, for signal processing, for interfacing, etc. So every functionality used to have different IC inside a complete box or a system. But nowadays, with the evolving techniques, what everything is getting integrated on a single substrate or a single silicon die area. So that is the power of VLSI. Like you are able to increase the functionality and the number of transistors that can be integrated on a semiconductor materials. And again, one more thing, when we are talking about VLSI, it automatically refers to semiconductor, because I think you understand when you cannot put maybe 1 million or even more than 1,000 transistors on a discrete substrate or kind of a PCB. If you try to build a complex GPU, or let us say a small kind of even memory kind of a IC, if you want to build on a PCB or using discrete transistor, it's not possible or feasible. So automatically, whenever you talk about VLSI, it refers to semiconductors. And basically, semiconductors are the foundation of VLSI technology. Without semiconductors, the power of integration which is available, it is not possible to the designers or the engineers. And obviously, VLSI explores the semiconductor properties. As you know, it is only possible with semiconductors that you can put those large amount of transistor on a single chip. And what it enables is you can build very high dense circuits on a small piece of silicon. And obviously, it leads to large enhancement in the performance, like what all features I discussed. And you all must be knowing the kind of things which we expect from our electronic devices nowadays. We want them to be very fast. We want the display to be very good. The quality of picture should be very good, and the volume or audio should be very good. So ultimately, whatever things the customers are demanding, these things has to be enabled inside that equipment or a device, let us say mobile phone or a laptop. And what enables that are the VLSI techniques which are used to build those chips on a silicon material or semiconductor material. And obviously, as I discussed, all these chips or circuits which we are using in all the kind of different equipments which are being used in daily life, like microprocessors, memory chips, communication, etc., etc., they are all possible because of VLSI circuits and also the semiconductor properties or the devices which are available in semiconductor technology. Okay, but when we are talking about VLSI, so we also should basically compare it with what was earlier available or it is still available to us, that is discrete electronics. So the power of VLSI is like you are able to do a high level of integration. You can integrate thousands to millions and nowadays even billion transistors on a single piece of a silicon material. But with discrete electronics, it's not possible because you are trying to build whatever circuit or whatever functionality you want to do using discrete devices. Those can be transistors, resistors, capacitor, inductor. And there is a limit beyond which you cannot put everything on a PCB substrate, as can be seen on the right hand side. So this die shows you the kind of integration which has taken place. So just maybe it could have maybe more than 1,000 transistors on it, or maybe I can, by look at it, there are maybe more than 10 to 15 inductors on it and different kind of things available. And the area of this die could be easily around 5 mm square. But similarly, on the other side, if you want to try to build some kind of a discrete setup, if you want to realize those functionality using individual chips or individual passive components or active components, then this is the kind of a structure you get on a PCB. And this PCB can easily be in centimeters kind of a range or area requirement. So you cannot compare the kind of integration which VLSI circuits or technology provides vis-a-vis the PCB uh, technology or circuit. So size and compactness I discussed. So the area which holds these number of elements are is not possible with PCB. And obviously performance. So performance is directly proportional to the number of transistors which you can integrate on a piece of a silicon. And we know like the number of transistors which can be put are in the domain range of millions and billions. So obviously the performance or the features which are available with VLSI circuits are much more powerful. If you try to realize similar functionality using a discrete electronics or a PCB, um, ideally you will not be able to achieve that kind of functionality with a PC. Even if you are able to achieve the kind of space it will occupy and the kind of power it will take and the ultimate cost of that PCB or the bill of material of that PCB will be much more than what is possible with VLSI circuits. But one more thing is like the manufacturing process of VLSI circuits are obviously complex. So in order to build these kind of a circuit, you need sophisticated fabs, and there are hundred of steps and everything which is involved to build this kind of integrated circuits. So it is obviously very complex and also costly. Whereas for discrete, you just need to procure different components from different vendors and then make a PCB, different layer PCB, and then put solders all those components on a PCB. So relatively manufacturing of a discrete electronic circuit is a bit easier. And what kind of applications for ultimately it's not like everything needs to be integrated on a silicon die. So there are some application which can be realized using PCB. So what are those which are less complex applications, simple circuits, or if you want to do some kind of a educational project, so all those things can be realized using PCB. But if you want to build a microprocessor or a dense memory chip, or you want to build some IC for smartphone or high-tech devices, obviously you have to move to VLSI circuits. It's not possible to do that on a using discrete component. One more thing is ultimately whatever chip you are building, you will integrate it on a PCB, but you cannot try to basically replicate all the functionality which is inside that chip using discrete component on a PCB. That is like whole idea behind this slide. Okay, so when we talk about VLSI or semiconductor technologies, so it's not a single, like you must have heard like silicon is the material which is used for building microelectronic circuits or VLSI circuit. It's not like only silicon is used. So there are different kind of substrates. There are inert substrates like thick and thin film, and there are glass-based substrate or sapphire-based substrates. Even on that, some kind of basic circuits are built. But what gives the advantage or the basically the superior experience to the VLSI circuits are the active substrates. So when we talk about active substrate, it directly comes to the semiconductor materials. So semiconductor materials can be like substrate materials like silicon, germanium, etc. And then there can be compound semiconductors also, which are basically these are the materials which are made you combining two different elements. Like in this case, gallium and arsenide are used, and then there are gallium nitride, silicon carbide. Those are the other kind of semiconductor materials which are built using combining two different elements. And these are also called 3-5 semiconductor compound semiconductor materials. But what is most prominent in world is silicon. And in silicon also, we obviously, so there is a silicon material, but on that material different kind of transistors can be built. So the most popular one is the MOSFETs, and then there are bipolar transistors, the BJTs, and nowadays the leading edge nodes, like those are like the nodes beyond 22 or 20 nanometers, they are using another kind of transistor which is called FinFETs. But still, the most popular transistors used in world is MOSFET, and MOSFET transistor can also be of two types, NMOS and PMOS. But then if you are able to put both these transistors on a single substrate, then that technology is called CMOS, complementary MOS. And this is the most prominent technology, whatever things I have highlighted, which is used whenever you are talking about semiconductor industry, like more than 90 to 95% of development is happening in this field, that is using silicon, MOSFET, and CMOS technology. So as mentioned here, silicon is a primary semiconductor material used in IC technology. Approximately 99% of all the ICs which are manufactured in world are made using silicon. The rest of them are made using other materials like gallium arsenide, gallium nitride, silicon carbide, etc. And in silicon also, most of the approximately 90 to 90% of silicon wafers, whatever circuits or transistors are built on those wafers are built using CMOS technology. So that's why I have highlighted here to just to give you an emphasize like the dominant technology or the transistors which are used today in modern world for building most ICs are CMOS and silicon material. Okay, so now we have some idea about what are the different kind of materials, what are the different kind of technologies which are used to build ICs. Now let us go a little bit into detail and be specific, like how IC is designed basically. What are the different steps which are followed in order to realize an IC? So, and I'm talking about analog specifically for analog IC design flow. But if you think about digital IC design or mixed signal IC, most I think there is some difference between them, but typical flow remains similar. There are different steps which needs to be followed in order to validate digital design, or the way it is designed is like you need to use RTL coding in order to basically define your design. But more or less the process remains same. So let us start. Before starting to design an IC, you need to have some idea like what actually you want to design. If whether you are designing a circuit which is a kind of a digital oriented CPU or a GPU or a memory circuit or a logic circuit, or you are building a circuit which is like uh, which needs to process a signal from a sensor which is primarily of analog domain, or you're building a circuit or a chip for a 5G or 4G technology. So ultimately this needs to be defined. Design concept, you should have a design concept, and it comes from the market research. Basically designer or whichever company you're working on which is investing in you and trying to build a new IC, they will give you an idea like we want to build this circuit specific. And then after design concept, you need to basically define that design. By definition, I mean to say the specifications of that circuit or block with whatever you're designing, these needs to be well defined and freezed, because based on those specifications you will follow the next steps, like whatever things you need to implement, those are defined for these specifications. So this needs to be defined. And in next step, it starts with the implementation. By implementation we start like okay, when you have defined a specification, you also need to finalize the architecture. For example, if you are building some kind of an amplifier, whether it is an operational amplifier, single stage amplifier, whether it is a Miller op amp, cascode op amp, or whatever architecture you need to define, that also needs to be defined here. And once the architecture is defined, now you start the actual design work. It starts with the implementation. By implementation, I mean to say like whatever architecture you have chosen, you start implementing that architecture using a EDA software. You start building a schematic of that architecture inside a tool and use for particular technology for which you are targeting your design. So once the schematic is designed or implemented in a software, next step is to simulate. So ultimately you need to validate your design, whatever you are building and whichever technology you are using, you need to simulate your design to check whether the desired specification which you had defined here, are they being achieved or not. So that is done by a simulation part. So all these steps define basically determine the electrical design of your circuit or block, and this is also called a front-end design stage. So once you have finalized your design after simulation, like this is the final circuit which needs to be fabricated, then next stage moves to the physical design. By physical design means you need to convert that design, that circuit into physical layers or masks, which will ultimately get fabricated on a semiconductor material or a silicon. So that stage is called physical layout design. That is also done by a layout design team, or sometimes in analog domain, a single designer also does all these steps. So once a layout is done, so because we are talking about circuits which consist of hundreds or thousands of transistors or different kind of passive element, so we need to be assured like whatever physical layout we are doing, whether it is matching to the simulated schematic or not, whatever sizes we have finalized or whatever connections are made, whether these are being followed while doing the layout. So there are physical verification steps. These are called DRC and LVS. So DRC means design rule check. So basically, a foundry has its own technology which defines what kind of layers need to be used, what will be the spacing between those layers, what will be the like length of a particular layer, metal layer, etc., etc. So all these are the physical rules which are provided by foundry, and these rules need to be followed while doing a physical layout. So these are called design rules, and a physical verification needs to be done whether all those rules are being met while doing a layout. So this is called DRC. And another kind of verification is LVS. So layout versus schematic is the full form of LVS. So whatever layout you have generated here, whether this layout matches electrically to this schematic which you had implemented here, so that is done using LVS. So whatever layout you are done, you extract the netlist from that layout, and that netlist is basically compared with the schematic netlist, so that you can validate whether the layout and schematic are electrically same or not. And once LVS is done, the next step is parasitic extraction. So whatever design we have done here, it is a virtual design, kind of an ideal design. So there are no metal layers involved between for the connections which are made between different components in a schematic. But once you replicate that schematic into a physical layout, and by physical layout means different kind of layers which are used to build our transistors or other devices, or the metal layers which are used to connect those devices on a silicon substrate. So all those elements appear here. But obviously, when you have physical elements which are placed closer to each other, or or there are metals used to connect different components, so some kind of resistors or capacitive or inductive properties comes into play. So those are parasitic elements which were not part of actual design when we had implemented it in schematic, but now they appear in layout. So those elements need to be extracted from the layout, and once it is done, again a simulation is run to validate whether even after parasitics, my design is working or not. If it is not, then you have to do some kind of iteration and improve your design. But once you are okay with parasitic extracted results, then a final work or task of a IC designer is complete. So this stage is called physical design, or also a backend design. So after this, we need to send our design for fabrication, and that is done by passing on our design files to a fabrication unit or a fab through a GDS file. So there is an industry standard format for in for sharing the layout of design with foundry, in that is called GDS. So that GDS file is sent to the fabrication unit, and this process sharing of GDS to foundry is also called a tape out. So whenever we talk about tape out means like we are sending, completing our design and sending it to foundry for following up the fabrication. So fabrication, once fabrication is done, then the wafers comes out of the foundry, and then these steps need to be followed. There is assembly, packaging. So first of all, that wafer needs to be cut. I think I shared that thing with, showed you in yesterday's presentation. Those dies needs to be assembled inside a package. The package needs to be completed, and then packaged IC needs to be tested and verified whether everything is working fine as per the specifications which were defined initially. And once it is verified, it is sent to the product manufacturer. For example, if Apple is manufacturing their IC processor for their mobile phone. Then after testing and verified, it is sent to be assembled inside their latest iPhone, and then finally you get that product for the customer's use. So this is a brief overview. I think I have tried to cover, try to just to give you an overall idea what all steps are taken place. But as far as IC designer is concerned, or if you want to build your career in specifically into IC design, so these are the two stages which needs to be followed: electrical design and physical design. These are the main tasks and activities which an IC designer does, and rest of the things are done by different teams and different locations and different kind of manufacturing units, like fabrication and other testing and product development. So these are the activities or tasks of a design engineer, IC design engineer. Okay, so I think I have made separate slide for each of these steps, but I think I have already covered them. We start with design concept. We define our design by it means like we finalize our specifications and architecture of our circuit. We implement it in a schematic tool, and then we simulate it, design to validate whether it is working or not. Then layout is done, verification is done, and parasitic extraction is done. So these all steps we have covered. And once IC layout is finalized, this is what I was talking about. The obviously photo mask needs to be generated, and that photo mask is generated using this GDS file, which is basically transferred or designed by an IC layout team. That all the layer information which is required in order to fabricate your design is passed through GDS file for photo mask manufacturing, and then those photo masks are used inside a foundry to fabricate the designs. Once the fabrication is done, so as mentioned, typically a fabrication takes place from maybe 1 to 3 months, and it all depends on what is the complexity of the design and what is the technology node on which that design is being manufactured, and also on the scale of the foundry. It's a lot. There are a lot of factors which depends the fabrication time, but it generally is anyway from 1 to 3 months. After that, process wafers that comes out of foundry, and then they are all the ATMP activities take place. Okay, so this is the same picture which I have repeated here. So I have highlighted these two stages, and this is what comprises of VLSI or IC design. So when you specifically talk about I want to do IC design, so these are the things which needs to be followed. And in this IC design also, these stages are separated. Like there are teams which do only electrical design, they only do schematic design and simulation and architecture finalization. Those are called front-end design engineers. And there is a team sometimes who only do IC layout, because IC layout is a very complex and intensive activity. So a lot of effort and time is involved in it. So there are sometimes dedicated engineers in industry who only do IC layout. And once layout is done, it is passed on to the verification team, which does all the verification tasks. So this is what is mean by IC design or VLSI design activity. And then fab and foundry, they have their own teams, and it again involves a lot of other activities which I talked about yesterday, and then ATMP. So basically, uh, uh, if I leave behind other aspects of semiconductor industry like chemical and other things, or this, infrastructure things, so these are the main activities which are required from which are involved in basically converting a design concept to a final product or IC. Okay, so just to give you an idea of what are post-fabrication things which I mentioned here, these things. So this is what happens when a final wafer comes out of a foundry. So there are multiple number of maybe 100 to 1000 chips on this single wafer. So these chips need to be extracted from this wafer. So this wafer is basically diced, or you can say cut using the diamond cutter or laser cutters in a separate setup, and then these dies are extracted from this wafer. Once dye is extracted, it is assembled inside a package. So this is basically a dip kind of a package. There is a cavity in center of this package where this die is placed. And then in order to make electrical connections to the pins, so there are bond wires. These bond wires are used to make connection from die, silicon die, to the basically landing pads on this package, and these landing pads are connected to these electrical pins. So this is how your signal transfers to silicon die inside the package. And this is I think this is a zoomed out picture of which shows you like this is the die, these are the bond wires, and these are the outside pins, package pin. And these bond wires generally they are made of aluminum material or gold, because they are high conductive materials, and these processes are well established to build bond wires using these materials. So these are the common materials used for building these bond wires. These are very small and thin bond wires, around 1 mil diameter. 1 mil is around 25 micrometers. These are the kind of dimensions we are talking about for these bond wires. So once the bonding is done, then this package needs to be sealed from the top, because you cannot keep it exposed. So an encapsulation is done. It is covered from the top, and then our final package IC looks like this. So these all activities, and again these are not everything is involved here, but these are the major activities which are involved after post fabrication. And this is what is mean by ATMP activities and post fabrication activities for a IC. Okay, so we talked about all the design steps, all the activities, but ultimately, any IC, in order to realize it physically, it has to be fabricated inside a foundry or a fab. And for based on that fab or that technology, a particular IC is designed. So in our case, for an example, because all that this information is available publicly. So again, one more point I want to emphasize is like you must be knowing like all the foundries, like all the big names or even the small foundries like TSMC, UMC, Global Foundry, Intel, whatever fabrication technology they are using to build the IC, it is very secretive. They do not share it with anyone, and also they want to basically save their information or whatever IP knowledge they have built to build their transistors very within themselves. They do not want all these things to come out. So, but ultimately, if a designer wants to design IC using a technology from a particular foundry for a particular node, he needs to get some information from the foundry. So that information is basically shared with a designer in form of an PDK. And in order to get that PDK, kind of agreement needs to be signed with the foundry, which is called NDA. But for this particular technology, that is Skywater is a foundry, US-based foundry, and this 130 nanometer technology, all the information has been made available by them in public domain. So that's why I'm taking reference of this technology. But if you talk about any other technology like TSMC, UMC, all that information is available with the design engineer, but you cannot share it in a public domain, because you need to sign an NDA with a foundry that you will keep that information with yourself. If you try to share it with anybody else, then they can obviously take some legal action. So that's the point, is to emphasize like how secretive this semiconductor technology is. All the processes, all the recipes which the fabs use to build these IC, they are very, very complex, and nobody wants to share it with others. They want to keep them as safe as possible. So in order to build IC, we need some kind of information, some kind of a data designer needs. So these are in form of design rules, which I talked about, like There are different layers, what kind of dimensions or spacing are used between those layers in order to build ICs. Then there are layers. Different layers are used to replicate different processing steps. Like if you are trying to build a MOSFET, you need to build a drain region, source region, gate region, well region. You need to build metal. So all these layers or elements which are used to realize or build a physical transistor or any other component on a semiconductor material that is mostly silicon. So all that information is encoded in form of layers. So this layer information is also provided by a foundry. Okay, so I think some of you might be having some questions, so please keep on putting them in Q&A box. So maybe at the end of this lecture, I will try to answer them as much possible. So please keep sending your queries in the Q&A box. Okay, so if anybody wants to see what all the information inside a PDK, so this is the link which is provided by the Skywater Foundry. If you want to see, go in more detail, please, you can follow this link and see the information. And as I mentioned, Sky 130 PDK, which is open source and it works with the open source EDA tools also. And PDK is process design kit. So PDK is a main interface between a design team or design engineer and a fab. So a designer needs only the PDK information from a foundry in order to build his design. Inside a PDK, all the things, all the electrical or technical information or the tool related files which are needed by a designer, everything is available. So it is the responsibility of a foundry to build a PDK, and then that PDK is shared with a design engineer, and based on that PDK, he builds on his designs. Okay. So this is just to give you an idea how if you are building any transistor on silicon surface, so this is how a cross-sectional area looks like. So this is the example of Skywater 130 nanometer. So this is the area below you, the surface of a silicon. So these are the anvil region, diffusion region, where the actual transistors are built. The drain or gate or drain and source regions or the bulk regions are built. All the NMOS, PMOS are built using these layers. And over that, this is a polysilicon gate, the layer which you use to build a gate of a MOSFET. And then over that are these different layers. These are the metal layers. These metal layers are used to connect one transistor from another. So you can imagine on a single piece of a silicon, there might be thousands or maybe millions of transistors. So if you want to connect a one transistor and its terminal to another transistor, you cannot do it using one or two layers. So more the complex your circuit is, the more number of layers are used. And these layers are connected with one another using this via region. So these vias are openings with which one metal layer is connected to another. So basically, this is how a stacked, if once a final fabrication happens, all the layers are built on a silicon wafer. This is how a cross-sectional area looks like if you try to cut it. And these are the different metal layers, and these are the different thicknesses of these metal layers. So you can see these are all in micrometer ranges. And these metal layers are realized using aluminum material. Okay, so this is how basically the front end layers or the layers which are used to build the transistors in any CMOS technology looks like. So this is your substrate PSUM. This is the wafer. In this wafer, you build a deep anvil. In deep anvil, then there you build an isolated P well, and there are anvil, other regions, and diffusions and end taps. So these all layers which I am showing here, these are used to build our transistors, NMOS, PMOS, and their gate region, etc. And these things are what information is needed by a designer from a foundry. And this all this information is present or available in PDK. And this all these different regions are defined using different layers, different colored layers. So everything is encoded inside a PDK. So that's what I think. If you remember yesterday, I talked about like a design engineer, he has to have some knowledge of a fabrication. If he has that knowledge, his tasks become very easier because he should understand like what kind of transistors he is working on, what are the different layers, how they look like, which region needs to be connected to which region. So all that this information. So it's not like designer needs to think only electrically about everything. So he has to have some background or some knowledge of how a process of fabricating a transistors and or other devices looks like inside a foundry. So that's the purpose of putting it here. So these are called front end layers, and this metallization layers which are on the top of these front end layers are called the back end layers. Okay, so once you understand about a technology, you have a PDK, you have your own knowledge about your electrical circuit. For example, if you are building some kind of an operational amplifier, you understand the nitty-gritties of an operational amplifier, its properties, etc., etc. Then next step is how do you implement your ideas or your skills onto actual design? And there comes the role of EDA. EDA is electronic design automation. So these are softwares, dedicated softwares, which are used to build those designs and all the steps which I mentioned in this slide here. So these steps need to be implemented by specific tools or softwares, and these softwares are since they are used for electronic design, these are called EDA tools or EDA softwares. And there are different kind of EDA tools. So there are software which are used to do PCB design also. But when we are talking about semiconductor design, VLSI design, or IC design, there are specific set of tools. And the big names, big vendors which build those tools are kind of Cadence, Synopsys, Mentor Graphics, Keysight. So these are the dedicated companies who build those kind of tools. And without these tools, you cannot build these ICs, your designs. And if those designs are not built, everything which we are using nowadays, from right from smartphone to semiconductors, everything supercomputers, these things cannot be built. So basically, you can say these are the EDA softwares are the building materials or building kind of you can say it as a raw material which is required in order to complete the final design or fabrication of your concepts into final ICs. And those ICs are then used inside product. So without EDA tools, these are not possible. A lot of steps you can understand. We are talking about transistors which are in billions and billions numbers. So these things cannot be done manually. So a lot of the steps or activities which are built inside these EDA software, they are automated, and obviously they basically reduce the complexity of effort which needs to be put by a designer, and also saves a lot of time for a designer. If he tries to do those tests manually, it would be a very difficult, or you can say it is not possible to do that. So what are the different aspects of EDA? They are used to design electronic circuits, VLSI circuits, then simulate it, then verify the steps like DRC and LVS, and in manufacturing also. So in manufacturing also, like mask making, etc., there are specific set of EDA tools which are used for the mask manufacturing. And inside Foundry also, some kind of softwares are used in order to run different processes. So I think EDA tools or EDA software, they play a role everywhere. But if you are an IC designer, you need to focus specifically on building skills on the domain which you are focusing on. Like if you are trying to do front end design, schematic and simulation, you need to focus on building skills in those EDA softwares. If you are trying to do layout, you need to be well versed or build skills on a layout software. If you are doing verification, then you need to understand everything about using those softwares to clear your verification steps like DRC and LVS. So now you can see how complex the IC design becomes. Like apart from the technical knowledge about the circuits and electrical and electronics concepts, you also need to build skills on the EDA software. And these are not very simple. Let me tell you, like these are it requires some time and some effort to learn these softwares and to integrate your skills with these softwares to finally complete your design. So they have some kind of a learning curve behind them. Okay, so for our case, we whatever we are discussing are open source EDA tools. As I mentioned, open source PDK provided by Sky 130 nanometer foundry, and then open source EDA tools. These are available in public domain. These are free softwares. So one thing about IC design is like it is not a very cheap process activity. IC design is a very complex and very costly activity. And fabrication again is a separate thing, but then it has its own cost involved. But designing an IC is in itself is a big activity and cost consuming. So just to give you some idea, the kind of GPUs which NVIDIA is developing. So I think the tentative numbers of engineers which are working behind those GPUs are like 500 to 1,000. These are the number of engineers which are working day and night to build those GPUs, and the cost of development of a single GPU can be anywhere from around $1 to $2 billion. So this is I'm talking about state of the art thing. But even if you try to build like a normal IC ASIC, which is like of analog nature, so the cost involved can be around like 500K US dollar to 1 billion US dollars. And it involves the cost of the manpower and also the EDA tools. EDA tools are very costly. So their cost, I think they form the maximum cost of an IC development cycle. So that's why these open source EDA tools are kind of new development which is happening in IC design field. So there are teams which are building these open source EDA tools. So all the steps which are required to do an analog IC design, they can be realized using these open source tools. So in our case, because we are using as part of the training program which are run by SSP, we are using these tools to do the designs. So we have a good experience with them. That's why I'm referring these to build these lecture slides. So for schematic design, a tool called Xscheme is used. Then circuit layout, a tool called Magic. For DRC, a Magic itself has this step to do the DRC check. For LVS, there's a software tool called NetGen, and then parasitic extraction and IC tape out can again be done by Magic. So basically, in order to do a complete analog IC design, there are three softwares, open source software which are available, and these softwares are integrated with this open source PDK Skywater 130 nanometer. So similarly, if you want to talk about commercial EDA, like from Cadence or Synopsys, they have their own tools. But again, as I told you, these are very costly, and you need to have a very good plan. And basically, you should know like how to use those tools, and so that whatever cost you are putting to buy or purchase those licenses, you are able to recover at the end of the day. For example, in case of Cadence for schematic design, there is a software called a schematic editor, Virtuoso schematic editor. For layout, they have Virtuoso layout editor. For DRC, Cadence has a tool called I think PVS. For LVS, again PVS is used. For parasitic extraction, there is a tool called Quantus, and tape out is again done by Virtuoso layout editor. So similarly, Synopsys they have their own set of tools. But one important thing about these softwares is like whatever PDK you are getting from a foundry, it should be compatible to the kind of software which you have. For example, not all foundries, especially the foundries which are small, they do not provide PDK for every EDA tool vendor because they want to save their development costs. So, for example, if you have a Cadence set of tools, commercial set of tools with you, but a foundry is providing a PDK with Synopsys, so that does not make sense. So, so it is a very important point. For example, if before starting your design, you should basically consult with the foundry. You should be in sync with them, like what kind of a PDK they provide, in which tool sets they are compatible with. Then only you should go ahead with purchasing or buying those tools, accessing those tools. Okay, so if once you have used those software, the EDA tools, I think that will be the part of our next lecture. Once this completes, I will be giving a demo of how these tools, open source tools, are used to build those design. Once the design is done, then you need to send it for a fabrication. So there are two modes of fabrication. Like, for example, I told you fabrication is in itself is a very costly process. Whatever design you have built, it has to be converted into. Uh, okay, I think somebody wants to ask a question, but I will suggest you please put your queries in Q&A box so that I can reply it at the end of this lecture. Please put your whatever queries you have, please put it in a Q&A box. So once a design is done, for example, if you are building a new design, you are not sure whether you are building it for the first time, and you are not sure whether it will be successful or not, or you would just want to build a prototype. But the cost of mask making is very costly. So, but similarly, just like you, there might be other customers who are doing building prototype or just testing. So what happens is in a single mask, so all the different design teams which have built their design, they put all their designs in a single mask. So what happens is whatever the cost of that mask is, it is shared between multiple customers, and also the area on the wafer is shared between multiple customers. So all the processing cost or the cost of that prototype wafer is shared between different customers. So that model is called multi-product wafer. So basically multiple customer designs are put on a same mask, and but then you do not get a opportunity to customize your designs because there is a limits to the multi-product wafers put on by foundry. But another thing is it is very cost effective. Basically, especially if you are a small company, you do not have a lot of resources and you do not want to take a risk of doing a production run. So you try to first check your design, put it in a MPW wafer and validate your design, and then you give it for the mass production. And the second model is dedicated wafer fabrication. So once your design is validated, you are sure like everything is working fine, or if something is not working, you are doing some kind of iteration on your design, you are improving your design, and now you're sure like whatever gets fabricated, it will definitely work. So then, and but obviously, when you are building an IC, you are not building it for small quantities like 10 or 100. Those ICs are used everywhere. Every smartphone available in the world has those ICs, or every electronic or electrical or whatever vehicles you are using, everything has multiple of those ICs. So the quantities which are required maybe in millions or billions. So again, for that, a dedicated wafer fabrication run is done. So a customer tells like I want maybe 1,000 or let us say 1 million dies of a particular design. So all the designs on that wafer will be for that same customer. So this will be a kind of a custom fabrication, dedicated fabrication. And once you are running a dedicated fabrication, a customer has a lot more control. He can discuss with the foundry if he needs some kind of a customization. And obviously, this thing can be afforded by only the big players, the big companies who have their ICs which have huge demand or huge quantity. Only those people can afford the dedicated wafer. So the idea is like there are two kind of fabrication runs. If you need small quantities prototypes, then you do multi-product wafer. If you need large number of quantities for a production, then a dedicated fabrication run is done. Okay, so in our case, for open source designs which we are building through SSP, we are using this Chip Ignite MPW shuttle. So this is run by a startup company called eFabless, where they have a dedicated area available. In that dedicated space, designs from different customers are integrated, and those designs are then sent for fabrication in Skywater 130 nanometer. So this is an example of MPW shuttle, how it looks like. So this basically masks, it contains designs from maybe around 50 customers. So this cost of this mask is being divided between 50 customers. So obviously at the end of the day, you will be getting only small quantities. You will not be getting huge numbers. For that, you need to go to dedicated wafer fabrication. Okay, so for our case for open source IC development, the shuttle is like this. We are building our design, and then there is a harness chip. This is called caravan. Our design is integrated into this caravan chip. This is how our final chip looks like. And then this chip is basically mounted into a test board. So this test board is pre-designed and pre-programmed. It has dedicated pins through which you can access your design on this chip and the can test your specific design. So this is part of open source IC development ecosystem, and this is the process which we are currently using to build design from SSP participants. And this is one of the example of how a final IC layout looks like, which is being built in open source tools. This is, I think, around 3.3 mm by 3.2 mm die area, and there are some test structures built on it. There is some small amplifiers, ring oscillator, operational amplifier, band gap reference. So just to give you an idea, like how a final die layout looks like. So this was a die which was designed by us, and then this is how a final fabricated die looks like, silicon die. This die was basically assembled inside this package chip IC. This IC was mounted on this test board, and these are the external pins to this test board through which we are trying to test our different circuits. These circuits like a common source amplifier, these individual circuits or IP blocks which are designed on this chip. So this is how a complete IC development, which we are following in open source ecosystem, is being used to basically train the participants which are enrolling to SSP programs. And this is how our final development of an IC looks like. Okay, I think that's all from my side for this first lecture. So if anybody has any questions, let me go to the Q&A box. If you have any more queries, we will discuss those queries. Please keep sending your queries. So somebody has asked, is there a company in Saudi Arabia specialized in design or fabricating these semiconductor material? So I think I'm not sure about it, but I think you can contact Academy or SSP team. They might be able to give you a better answer. I think the contact details are available on this slide. So please contact with them about the possibilities available in Kingdom. Another question is the design will be apply on the mask reticle or some apply on the equipment itself? So uh, this question is asked by Quade. So Quade, what happens is whatever designs you have done, the layout you have done, it is in form of a software. Like all these files are present in a software. Now this design is being, whatever software files are available, these files are converted into a mask or reticle by dedicated photo mask unit. So there is a specific uh, agency, or you can say a manufacturing unit, which converts your design into reticle or mask. And then that mask is used to basically imprint the design on a silicon wafer through photolithography. Basically, you put a light on pass light through that mask on a silicon wafer, and there is a photoresist on that silicon wafer, and wherever the light it is exposed, that material can be etched away, and then you can do the doping on your silicon wafer. So for whatever layer you are trying to build, like if you are trying to build a drain source area, you will do a doping for that particular element on that silicon wafer. If you are trying to build a gate, so ultimately, basically, masks are used to imprint the light on a silicon wafer and to expose the area of a wafer where you want to build a specific structure. So somebody has asked, so what is the university that teach this technology and what is the major name? So I think you need to contact Academy or SSP for this particular query. They will be better able to answer this. So Abdullah has asked, is there any relation between cyber security and semiconductor? So I think uh, cybersecurity field has arisen because of semiconductor. Ultimately, what you mean by cybersecurity is you want to basically protect your whatever networks are or whatever hardware is from like viruses or some bad elements like hackers, etc. Ultimately, all the electronic equipment which you are trying to save are built using a semiconductor. Ultimately, those semiconductors inside them they run softwares. So you want to protect your uh, whatever space where you are working in, but ultimately you need to program those semiconductor. Obviously, you must be using some kind of a software or program to control those semiconductor materials. But there is a big relation between cyber security and semiconductor. If you do not have semiconductor, there is no need for cyber security, because then you will not have all these networking equipment and all the electronic equipment which you are trying to protect. Is design of the test board done by the IC designer or provided by the foundry? If so, does this mean we would need an EDA tool for the test board separately? So this is a good question. So IC, once the IC design is done, it is fabricated. The design that fabricated uh, wafer comes back, then that design on that wafer is tested in a separate place, and this task is done by a separate engineers. These are called testing engineers. Ultimately, testing engineers should also understand what actually their design is on that wafer. For that, they need information or input from IC designer. So most of the testing is done by test engineers, but they need IC designers also. They need input from them. Sometimes IC designer sits with the test engineers to tell him like this kind of signal you should apply. This is the output you should see. So although main hard heavy lifting is not done by IC designer, but his presence or his inputs are definitely required. And for testing also, if it is a small design, if you just need to measure some small pins or signals, then you need not use any software for that. But if there is a very complex digital design and there are a lot of number of pins on several number of dies you need to measure, then there are some kind of AT software which are used, automating testing equipment softwares. They are used specifically used for uh, basically testing your designs. So another question is, as an FPGA engineer, what other skills I need to be able to design ASICs? Also, does SSP provide training for such skills? So as an FPGA engineer, I think if you are an FPGA engineer, you must be well versed with RTL. You must be understanding Verilog or VHDL. But that is just like you are doing a programming. If you want to build an ASIC, then you need to basically synthesize your code to a fabricatable design. By that I means like whatever RTL code you have written, you need to convert it into a silicon design. For that, you need to get a PDK from a foundry, which will consist of all the logic cells, like the gates in case of a digital design. You will compile your RTL code into those logic gates, you will synthesize them, then you will check the timing, etc. And then you need to also do the layout, basically AP automatic placement and routing of your design. So all those are the extra skills which an FPGA engineer will require in order to design the ASICs. But if you understand the starting point, that is RTL coding, I think other steps will be a little bit easier for you to understand. Uh, Obviously, you need some kind of a practice or some kind of a guidance to do that. As per as training skills, I think you need to check with SSP for that, whether they provide some kind of a training on that. Another question is like, since the TSMC reached a 2 nanometer, how small IC can be reached? So I think people are talking about reaching 1 nanometer. Intel is talking about doing 1 nanometer, etc. So I think I talked about it yesterday also. There is an end coming to a Moore's law, but we still are not sure like how much smaller a transistor can become. But still, the companies are doing their R&D and D and development to build more smaller and smaller transistors. Okay, I think these are all the questions till now. Okay, I think I yesterday shared one link with you if you want to join a Slack channel. I have sent the invitation also to whoever filled that form, but some of you might not have still joined the Slack channel. So whoever has received the invitation, please join that Slack channel. Whatever slides I am sharing, I will be putting these slides on that Slack channel. And for somebody who are new today, who might not have got that link, please, this is the link. You can, I'm sharing it in the Q&A box. think you must have got this link. If you want to join the Slack channel, the slides will be put on that Slack channel if you want to access. I'm also putting it on a Slack chat box. Please fill this form to join the Slack. Okay, so let us take a break of maybe 5 minutes, and then we will start with our second lecture, that is the demo. Whatever things I talked about on the schematic layout, etc., etc., how actually these things are implemented on a EDA software, what is the flow, what all steps are done. I will be showing you a brief demo of a already built design. So let us join back after in 5 minutes. Okay, so welcome back everyone. So just confirm me whether you are able to see my slide before I start. Just chat yes or thumbs up in a chat box. Are you able to see? Just put yes on chat box. Someone. Okay, thank you. Okay, so now let us go a little bit into practical. Will just cover a few brief slides and then I will move to my actual tools where we will see how design steps are followed. Okay, so as I told, first we need to have some kind of target, like we want to have some design idea. So in this case, let us say we want to design amplifier. This is an operational amplifier, op-amp. This is something which you want to design. It consists of different kind of stages, differential stage, second stage, and different transistors and passive components. This is architecture of this op-amp, and this is something which we want to design for our purpose. And these are the specifications. These are target specifications which I want to achieve from this op-amp. So this is what because whenever you want to design something, you should have some idea, like you should have some task before you, like this is the what I want to achieve. So this is how definition is done. This is a small design, but if your design is very big, then you need to basically divide it into sub blocks, and then there might be big teams. There may every block will be assigned to a separate team member. He will do his part, and then finally you need to integrate, and that the approach which is used is the same, the steps which are required. So these are the steps which I mentioned in the previous lecture. These are what we will be doing because we are talking about IC design right now. So these are the steps which we'll be following from design concept to specs and physical layout. Okay, so one thing which I mentioned in my last lecture of PDK. So this is what Foundry provides you, and we need that this PDK, and these are the different elements of this PDK. I think for now you need not go into detail and need not understand everything, but there are different kinds of files inside a PDK which are shown as part here on the bottom end. Symbols, callbacks, netlister, spice model, pieces. All these things are used in different tools which are used to building your design, and this all these files and information are provided by a foundry. So basically PDK is what it is, a collection of files and documents which are provided by a foundry, and it captures all the technical information of the processes happening inside a foundry, and it is required by a designer to build his design.
and it is the most important interface between a designer and a foundry. And then these are the tools which we'll be using. I mentioned it earlier also, Xscheme, etc., etc. And now let us start. This is how Xscheme looks like, and this is a schematic of my op-amp. So let me now move to my another screen. Okay, so one important thing before I start is, so most of the IC design activities which take place or the softwares which are used are they mostly run on Linux. So I think for most part of your daily activity or other tasks, you must be using Windows. But if you want to enter into an IC design domain, you want to build your career, it's very important and you must understand Linux. You need not be expert in Linux, but there are some basic commands, some basic steps which are required for your purpose, like how to create a new file, create a folder, copy, paste, all those things. Some basic knowledge of Linux is required if you want to, and that is why because all the softwares they are mainly built to be run on Linux because Linux is a more stable and solid operating system to run these complex softwares because these are very resource intensive and also you need do not want it to be unstable because you must be knowing it. Windows is a little bit unstable, it crashes a lot, but Linux is a very stable software. So most of the IC vendors, all the big players, Cadence, Synopsys, Mentor, and even all open source softwares, they are optimized to be built and run on Linux. So this is an Ubuntu installed on my laptop. You can install it is easy to install. This is a free version of Linux. So this is how our home screen looks like. So as I mentioned, the first step is to build a schematic, and schematic is built inside a tool called Xscheme. This is a schematic editor. So similarly, if you are having access to Cadence or Synopsys suites of tools, they will have their own software. But more or less, schematic is built like this. And these components, these elements, this is like PMOS, this is NMOS, these are part of capacitor and other elements. These are all provided by a foundry. So there is a PDK provided by a foundry. In our case, this is Skywater 130 nanometer. These components are being used from there to build this schematic architecture, and these are the wires which are used to make the connection between different components. So idea is to show you like this is how uh, a schematic of any circuit looks like. This is a small design and operational amplifier. It might be containing less than maybe 10 transistors, but if you have a big or huge design, it similar the way is similar. And another thing is like if you have multiple blocks in your design, then there is a kind concept of hierarchical design. So first you build the sub-level blocks, then you integrate that sub-level block into an upper level, and then those upper level blocks are integrated into a top level. So if in case our design is a big, you basically divide it into a small blocks or small parts, and individual designs are done, and then finally at top level that is integrated. But idea is like this is how our software looks like. So I think you must be knowing in case of NMOS, we need to define the width and length of a transistor. So this is how we define the width and length and other properties of a transistors, all that information. This is how a designer controls the properties of these devices. And then there are several other features you want to zoom in, zoom out, etc. This is how a schematic basically is built. So once a schematic is built, this is just like drawing, kind of creating a drawing. Now you need to basically simulate this design. For that, test bench, a separate schematic is created, which is called a test bench, where we need to connect a power source, input, output, and all the other elements to this schematic, and then simulate our design. And then for before building a test bench, I want to convert this schematic into its symbol. So I will this schematic is converted into a symbol, and this is how a symbol of an op-amp looks like. So it has these six terminals: input, positive, negative input, and output, and then two power supplies, and then there's a reference pin also. So all these pins are carried off from this schematic, and this schematic is converted into this symbol. And now this symbol is what will be used to build a test bench. And this test bench is created into a separate schematic, something like this. For example, this is a schematic, and this is that op-amp which added symbol. And if I want to go inside and see inside this symbol, this can be done like this. I can go inside this symbol one hierarchy down and see the full schematic of my op-amp like this. And now this op-amp is basically connected into a unity buffer configuration. Like this op-amp is used to build a buffer, and then power supplies are attached to it, VDD, ground, then input signals in form of sinusoidal signals, and then output is there is a 110 picofarad capacitive load attached to this circuit. And then reference current is given, like 100 microampere reference current is required to bias this op amp. So all these elements are attached, and then a complete test bench is created. Another thing is we want to simulate this design for a particular foundry and a particular model. In our case, we are using Sky Water 130 nanometer. And so these are the models which are basically pasted here. So I'm not going into detailed steps because it will then take a lot of time. The idea is just to give you a brief overview, like how our test bench is built and what all elements are there. So these are models which are pasted here. This is part of a PDK, which I mentioned. All these things comes from a PDK. And similarly, these symbols which I have used to build my design, these are specific to Skywater 130 PDK. So these all things are provided by a foundry through their PDK. So once this is done, a model is attached because we want to simulate these transistors for these particular SPICE models. We want these transistors to capture the properties of Skywater 130 nanometer transistors, and then only we want to simulate it. And then after that, there are some commands which needs to be typed. Basically, it is kind of you want to give the instructions to this test bench, like how it should simulate. You can say it is kind of coding, but it's not a very complex thing. It is easy to understand. These are the specific syntax from SPICE language which you need to give. For example, you want to save all the nodes from this simulation. You want to save the operating point, DC operating point. Whatever data is generated, it is saved into another output file. Then you want to print a specific voltage, and then transient simulation. So all these there's a specific syntax, and all that information is available in the manuals of the software. Okay, one more thing, the SPICE, there are different forms of SPICE simulation tool. The open source SPICE simulator is called SGSpice. Similarly, if there are commercial tools, then for Cadence, there is a simulator called Spectre. From Synopsys, I think it is called HSpice. From Mentor, it is Aldo. So all these are form of SPICE simulation, but in our case, this is NGSpice. So this syntax or the SPICE syntax remains almost similar, with some changes. But more or less, if you understand one kind of a SPICE simulation tool, you can understand others also. So this is how all the setup is done. I have created a test bench to test my op-amp. Once I have done all the sizing here, all the transistors, etc., then all the setup is done. Now I will run the simulation just to show you quickly, and then netlist. Okay, one more thing is all this information which I have put inside the schematic, like this, created this schematic test bench, this model, this SPICE. This is first converted into a netlist. So netlist is basically a textual format of your circuit. Ultimately, it has to run in a software. So software won't be able to understand this drawing. It will understand some kind of a code or some kind of a syntax. So that syntax is kind of a netlist. So this netlist is generated from this schematic. I will just show you once I press this netlist button. All this information will get converted into a netlist. So this is how a netlist looks like. So netlist is a syntax of all the electrical information of the circuit. Whatever things I have captured, like power supplies, resistors, reference currents, this model file, and all the SPICE syntax commands. And these are my transistors, all the information, their length, width, etc., etc. All this is converted into a syntax. And now this spice netlist is passed on to a simulation. So once netlist is done, this netlist is generated. When I press a simulate button, now a simulation will done. Then netlist will be passed on to a ngSpice simulator. So this is the window. So there is no like a GUI graphical interface for ngSpice. It was in a terminal window. So once netlist is compiled and it is run, it is just like when you are running a Python code. You are typing a Python command, and then behind it there is a compiler which runs that code. So similarly, in our case, a netlist is generated and it is passed on to a compiler, ngSpice, and then it runs the simulation. So once simulation is done, I want to see my waveform. So if I press this button, so this is how these are, I think, already generated. So this is how my waveform looks like. So this is a unity gain configuration. So the green waveform is my input and red is my output. So there is not much difference, like almost gain of 1. So that is what was expected from this circuit, but with little bit of offset between these waveforms. So this is how a waveform can be seen. This is a very simple circuit just for a demo purpose. Similarly, if I want to make a non-inverting amplifier or an inverting amplifier, those of you who are from like basic graduation of electronics domain, they must be understanding like operational amplifier has different functions. It can be used to build different kind of circuits like different amplifiers, integrator, differentiator, instrumentation circuits. So similarly, this is the basic form of a buffer circuit. If you want to build a non-inverting, inverting, you have to make those configuration changes here, and accordingly you can see the waveforms. So this is one kind of a simulation, transient simulation I have shown here. Again, then if you want to do a frequency dependent simulation, AC domain, so then I have to, similarly, I have created this another circuit. Just, sorry. And different configuration to run an AC simulation here. And again, different kind of an ngSpice commands I have written here. So like in this case, I was running a transient simulation. So I was using a transient command here. In this case, I am running an AC simulation. So I'm using a AC syntax to run an AC, like how my circuit performs with respect to change in the frequency of my input signal. Again, I run a simulation using netlist. A netlist will get generated. And this netlist will have a AC syntax here in space of replacing the transient which I was using earlier, and then run the simulation. And then I think this is how our waveform appears. So let me make some changes here so that I can show you some difference how it updates. Let me make it 1 picofarad and now run it again. So you can see this waveform is updated because I have changed some element of parameter in my circuit. So this is how basically idea is just to show you how circuit is simulated. So I am doing this very fast to give you just a brief overview. But if you are actually designing your circuit, all these things take a lot of time. And that too when you have a good amount of experience. But if you're learning, you will take some time to build those skills. You need to understand how to place my components here, how to make the wire connect different things, which element needs to be taken from which place, what kind of analysis needs to be run, whether need to run a transient analysis, AC analysis, and then there are different kind of complex analysis like RF analysis or harmonic balance, etc., etc. So all these things require some effort to build. And but this is way how this is the way. First, you build a schematic, you make it simple, then you create test benches, then you set up your test bench, and then run the simulation to see the waveform. So okay, so once everything is done, you are happy with your design, like whatever waveforms I'm getting, I'm okay with it. It is done, and I'm good enough to now go to the next step. So as mentioned, once this test bench simulation is done, validation is done, And so the next step is, let me move back to slide once again. So this was the X-Game simulation done ngSpice. I'm going back to slide. We build a schematic using X-Game, and then ngSpice, the simulation is run here. And then we need to move to layout. So let me go back to that slide. So this is the flow. We had some concept, we had some specifications of an op-amp, we built it schematic, then we run a simulation on ngSpice. So, and we are happy with whatever waveforms we are getting. So our electrical design stage is done. So the next step is IC layout. We need to convert that schematic into layout, basically masks, which are actually used to fabricate your design on a silicon wafer. So that step is next, which we will see. Okay, so this is our schematic. So this is what is our test pens. These are built just to verify our design, whether it is okay or not. But this is what actual our circuit is. And this is what we want to convert into layout and design it. But before that, one step is how will we know like what all elements need to be put in my layout and what are their dimensions and devices. So how it is done is all this information is captured inside a netlist. So let me quickly show you how that netlist looks like. So all the information which is basically put in this schematic, it is converted into a netlist. And this is the netlist which contains all the information about all the transistors and other elements like this capacitor. What are the type of these transistors? Like this is a PFET and these are NFETs, and these are the width and length and number of fingers of those transistors, and this is the value of capacitor, its width and length, etc. And also the nodes, how these transistors are connected together, and what are the pins, like what are the VDD, VSS, input, output pins. All this information is captured inside this netlist. And this netlist will be used as our reference to build our layout, because this netlist consists of all the information which is required. Only thing missing is like we would be required to place the components inside in our layout sheet and then make the connection. But the basic fundamental information which is required is available in this netlist. So now let us move to our layout part, and I will show you there how we start with a layout and what are the steps involved in it. Okay, so I will go to my place where I want to build my layout. With my magic tool, I mentioned about it like we are using magic to build our layout. I go and open my magic tool, and then this is a sheet where that information or the layout, final layout which I needs to do, and these are the different layers which are used to build my layout. When I move my pointer mouse from one layer to another, you can see the name of these layers are changing on the top. So this is like a vector layer used to build a vector. This is anti-fusion, and then these are the metal layers, etc., etc. So these all layers are used to build our design. But before that, we need to place our components here. So that component is available in netlist. So I will just import my netlist into this layout shield, which I created from my schematic. This is my netlist from op-amp which was generated. And when I import this netlist in my layout sheet, it will basically place all the components which are part of my netlist. So all these components like this XM1, PFET, capacitor, etc., everything is placed, and all these pins are also placed in this layout sheet. Okay. So let me zoom and just show you. So these are the pins of my schematic VDD, and these are actual metal layers. These are the masking layers which will get converted into mask and then get fabricated on a wafer. So now we are not talking about some virtual thing. We are talking about actual masking layers. This is what gets imprinted on your wafer. These are the layout steps which our layout designer does. Okay, so these are the pins, metal pins, and these are the NMOSes, different NMOSes which are available, which are present in my netlist. Okay. Yeah. But one thing is, this is the capacitor. So one thing is, what this step does is it only places those components here from this netlist, but it does not make any connections or make any basically placement of these devices. So that is a role of a design engineer or a layout design engineer. This step only gives you the components, and these are called P cells, basically programmable cells. These are all these transistors are pre-built. So Foundry has done a basic layout of pre-layout of this transistors for you. You just need to place this layout of this transistor as it is, and then make the connection. So how this transistor is built, what are the different layers used to build it, you need not worry about it. What is the diffusion layer, what is my gate, what is my drain source region, what are the gate connections, what are the guard ring, etc. These are pre-built by the Foundry as part of your PDK. Your job is just to make the placement of these components in this sheet, proper placement as per the concepts of IC layout, and then make the connections. So that is what I does. So let me show you just quickly how I can place these things here. Quickly, I'm just doing it randomly. For example, let me say, for example, one important thing is you want to make your layout as compact as possible, because ultimately silicon area costs a lot of money. So you want to, whatever layout is being made is, you want to make it as efficient as possible and as close as possible. Another benefit of this is, like, if you make a compact layout, it will also reduce your parasitics. All the parasitic resistance, capacitors, inductors introduced in your design. So this is like just a random placement of my transistor. And then next step will be to make the connection. And how you make the connection is based on this schematic. So in this schematic, you understand which is your M2, what is your M3, and how they are connected to each other through these wires. So all these things, obviously, a designer needs to understand which is my M2, M3, and which nodes needs to be connected to which other node. All that things are basically these are the skills or the actual effort or steps which needs to be made during IC layout. Okay, so this was just to show you the steps, but now let me move to actual layout, which is already being done. So, okay, so this is how our final layout will look like. This is an actual layout of same cells, which I showed in my previous window. So these are already placed. So you can see these NMOSes and PMOSes, they are placed near to each other so that your layout is compact, and these metal lines are used to make the connection. So example, if you want to see where all VDD net is going, you can highlight it. Similarly, if you want to see where is your input connection going or VSS is going, just you can highlight it. Okay. Similarly, what is this node? This is your input. So this is how our placement is done, and this is the capacitor. Okay, so idea is to show you, like, once the placement is done, the rest of the activities, like how to make the connections, where to place the pins, which metal layer to use. Like this is your metal 2 layer, these are metal 3, metal 4, different color of layer mean different things here. So everything, all this is what basically a designer needs to understand. So that's why I was referring, like, you should be well versed about the fabrication technology, how actually a design is fabricated, which kind of layer is used for which purpose, which color that layer is used to represent. Okay, so once this layout is done, Once it is done, now it is ready to be fabricated. But before that, one important thing is I mentioned, let me move again to my slides. Okay, so the last step captured this IC layout. So another step is DRC and LBS. So these are the verification steps for that. And then there is a parasitic extraction. So let me show you how we do this. Okay, so by DRC means, like, for example, let me quickly build one layer here. This is metal 2 layer. I am quickly building this metal, and you can see there is a DRC error showing 0 here. But if I try to move it nearer to this other layer, you see some kind of highlight starts appearing here, and the DRC error becomes 2. So this shows, like, as per the foundry, it does not permit two same layers. In this case, this is metal 2 layers should be near to each other. So there is some spacing which is required. So this spacing, if it is violated, like if I place two layers very near to each other, it violates my DRC, design rule provided by a foundry. So if I want to rectify it, I will move this layer little bit to the top, and you can see, maybe you can see here, the DRC error will disappear. Okay, so now it becomes green and DRC error is 0. Similarly, this is just one small example. This is related to metal 2, but then there are so many layers used here, and every layer has its own DRC rule. But it's not like you need to remember everything, but while doing your design and while placing the layers, you need to keep on checking whether my DRC errors are getting violated, and wherever it is getting violated, it's good practice to rectify it there itself. Because if you leave it for the later, then a lot of DRC error will creep up into your design, and it will become very difficult to remove it them later. So this is what a DRC check is like. So now I have, when I did this layout, I did everything according to the rule. So that's why DRC error is coming as 0. Okay, so the next step is LVS. So by LVS, I mean to say, so this was my schematic, and these are the transistors, and these are the connections made here. But when I am doing my actual layout, you can see like how complex it looks like. If I have to be very focused to understand which transistor here represent which particular transistor in my schematic, and apart from that, which node is connecting to which other node of a particular transistor in my layout. So all those things need to be remembered, or basically you get to learn these things by your experience. But ultimately you have to ensure this. So while making these connections, I may make some mistake here. So some metal which needs to be connected to some place, it gets shorted to some other metal, or some connection is missing. So all these things are very much possible here because everything is being done manually here. So it means, like, if some connections is wrong, or it is being mistakenly opened or short, it will violate the design which you did in your schematic. And then this is something which you need to check whether whatever layout you have done, whatever connections you have made between different transistors, are they same as being made in your schematic, because this is your actual design which you have simulated and validated in your front end design. You want this, your layout should replicate this schematic. So this is what LVS is. Basically, this is what LVS check is. So how it is done is, basically a netlist is extracted from this layout, and then you already have a netlist for this schematic, and basically we compare those two netlists together. So let me just show you how a netlist extracted from this layout looks like. Okay, so when I do extraction on this LBS netlist, so this is a netlist extracted from my layout, and this is a netlist extracted from a schematic. Okay, so in LBS, what we do, because we cannot physically compare this schematic with this layout, because these are two different domain of software, different kind of files. But electrically, everything done in this schematic is captured in its netlist, this one, and everything which is done in this layout, it is also extracted in this netlist. Okay, so what we can do is, because these electrical netlists are being generated from their respective design files, we will compare them, and that is done using software called NetGen. Okay. And NetGen is again not a GUI based software. It is basically a terminal based software where we will run a specific command. For example, this is a specific command to run LVS, where I will take a netlist from my layout and then netlist from my schematic, and then I will compare them and run them, compile it in a NetGen software. So once I do it, it will generate a specific file .out. This is the output of this LVS run, and it will show me while comparing those netlists, like this is the all the elements of layout netlist, and these are all on the left hand side are the elements of layout netlist, and on the right hand side are the elements of a schematic netlist, and it will mention and compare them. It will tell me, like in my layout netlist, there are so many number of transistors, 4, 5, and 1, and there are 10 devices, there are 10 nets in my layout netlist, and in schematic netlist, similarly, there are 10 and 10 devices here, and it will compare the pins. And if everything is okay, like electrically, if my both the netlists are same, then it will give me this kind of a final message, like your circuits are matching uniquely, like these both the netlists are matching uniquely. It means like my layout and schematic are both same electrically, so there is no need to worry, like if everything, the connections which I have made in my layout, whether they are as per my schematic or not. So that's why this check is required. This is just a small layout, but just think about if you have a very big layout which might consist of hundreds or thousands of transistors, and then definitely there is a scope of making error there. That's why this LVS step is required to verify, because if you have some kind of an electrical error, if your nets are shorted or they are opened, and you send this design for fabrication, then obviously this won't work. And there is so much effort, time, and cost involved in doing your design and getting it fabricated. So everything will be wasted. So that's why these verification checks are very important, DRC and LVS. Okay. And then last step is parasitic extraction. Okay. So as you can see, these are just ideal. These are not ideal, but these are the actual PDK devices used here, and there are electrical properties behind them for their simulation. But these nets are ideal nets. These are just like visual lines used to connect those things. But when you convert it into actual layout, so for example, let us say this is just an ideal line here in that schematic, but here it is a very big metal line uh, from here to here. I think this is a metal 4 metal line. So actually, when there is a metal connecting between these two nodes, it has its some resistive properties in it. It will be having, if there are two nearby metals to one another, there will be some coupling between them, uh, capacitive coupling, and it will reach to a capacitance. If there is some high frequency signal involved, and there can be some inductive properties which will be associated with this metal line. So all those things are not captured in my schematic, but actual while doing a layout, these things do matter because they are part of my design now. So what we do is we do an extraction on this layout. By extraction means like we want to extract all the layers in this layout and also associated resistive, capacitive, or inductive values to this layout, to these metal connections or different layers in this layout. And again, that thing is captured in another netlist. So let me just show you how that netlist looks like. So this is that netlist after extraction. So as you can see, there are a lot of elements which are introduced in this netlist. So these are all parasitic elements, capacitance and resistance, etc., etc. So this kind of, these are very small numbers, but when you are talking about a big layout, even small capacitance values can combine to form a big number, and it can basically change the electrical behavior of a circuit. So purpose of parasitic extraction is just to validate whether after doing a layout, after adding these metal layers, whether any kind of deviation is happening in my design because of these parasitics. So that is the idea behind doing a parasitic extraction. This is extracted in a netlist using this netlist. But now how to validate it? So then comes again the part of a simulation. Okay. So here what I have done, this was my test bench where I did my front end simulation like the schematic. So behind this actual schematic is associated with this test bench symbol. But then I copy this test bench, I place a new symbol, but I change some of its properties. Okay. So now with this symbol, I associate this parasitic extracted netlist. So now there are all the non-idealities or the parasitic values which are in this netlist which get associated with this parallel test bench. This is my parasitic PEX test bench for simulation, and this is my ideal schematic simulation. Okay, and when I run simulation, I plot both the outputs from these both the test benches parallelly and together on a same waveform, and I can see just after running the simulation like there is some deviation in gain or phase value happening at very high frequency. So in this case, this is not very important because this there is not much deviation in my phase and gain properties of this op-amp. But if there are significant number of parasitic values associated, so there can be some deviation in the gain of your op-amp, or there can be some degradation of phase margin or gain margin values of your circuit. So the purpose of parasitic extraction and doing this post layout simulation, so this is called post layout simulation because we are replacing ideal schematic, ideal op-amp with its post layout extracted parasitic netlist and then running the simulation. So the purpose is just to validate whether after this parasitic introduced in my design, are they creating any trouble or are they leading to any deviation in the specifications of my design. So this is how a parasitic extraction is done and the post layout simulation is run. Okay, so this completes all the steps, and the last step is if everything is okay, you are happy with your front end design, your layout is okay, then now you need to send this design for fabrication. And this process is called tape out. And how do you do it? Basically, you convert this design into a GDS file format. Okay, write GDS. I will give it a name. It will convert this all this information into a binary file, which is called a GDS file. Okay, and this file gets saved in a specific location. This one. So this is your all this layout information gets converted into a GDS file, and this is a binary file. Could not be opened here, and you cannot understand this file. But this is what is required by photomask team. They take this file, they all the coordinates, all the information about the masking layers in this layout is available in this GDS file. They use this GDS file to convert it into photomask. All the layers available in this layout are converted into their respective photomasks. Those photomasks are then transferred to a foundry, and then foundry uses those photomasks to imprint, like pass light through that photo mask and get it imprinted on your wafer. And then that in that way, your design from this layout gets basically transferred on the silicon wafer. And there are several steps involved, different processes involved to build a complete stack of layers and final IC. Okay, so this is, I think this completes all the steps I wanted to share with you. Let me just quickly move to my slides. So this is what all I talked about. After parasitic extraction, there is one step of post layout simulation. When you're happy with your design, you send your GDS file for fabrication. After fabrication, again, ATMP steps take place. Okay, so these are all the steps which I verbally talked about in my presentation. From schematic, a netlist is generated. This netlist is used to run the simulation and also used to run a layout and generate layout pixels, and then those pixels are used to create a final layout. And what is an IC layout? Basically, it is an arrangement of all the components which are available from your schematic front-end design. These are converted into physical layers, and then those layers are placed and connected using metal layers. And then obviously designer needs to follow some rules which as per the foundry requirement. And all the information of layout is basically transferred from schematic via a netlist. Okay, so this is how our layout tool looks like. In our case, we are using Magic. This is the window of Magic tool. We place our components here and try to build all the layout elements and complete our layout. Once layout is done, then DRC is run. This is a very verification check. You want to basically check whether all the layers placed in your layout are as per the foundry requirements. Then from the foundry PDK, you get a DRC rule file. So this is the file where all the rules provided by foundry are there. And then DRC rule tool gets both these files, and then it runs the DRC check and gives the final output. If there are any errors, as I showed in the layout sheet, it will highlight and also mention like there are two numbers of errors, you need to rectify it. Okay. Then layout versus schematic. Again, there is a IC layout. There is a netlist generated from layout. There is a spice netlist generated from schematic, and then there is a LVS rule file which interprets information in both these files, and all this is passed on to LVS tool. All these things happen behind the scene. You need not worry about these things, but because these are all the databases which are passed on to a tool, and it runs the respective steps. So we ran a NetGen tool on these databases, and then it gives you finally an LBS error. If there is any error, if there is no error, then it gives you that your circuit matches uniquely. If there is an error, then it becomes a little bit difficult, because LBS errors are very difficult to debug, because you understand there are so many layers. You don't understand where that signal, which net has been shorted or which net has been remained open. So LBS errors are very sometimes become tricky. The best approach is like whenever you are doing your layout first time, try to be very meticulous and precise, like how you are placing the different components and how you are making the connections. So you should be very focused while doing a layout. Okay, once layout is done, you are happy with your layout, then you need to validate your parasitics, whether parasitics are playing any role in degrading the performance of your design. For that, an IC layout is basically extracted using the PEX rule file. So all these rule files which I'm mentioning here, like PEX rule file and this LVS rule file and DRC rule, these are all part of a PDK. A foundry provides all these things to a designer. So this is passed on to a PEX tool. In this case, Magic runs the PEX also. It generates a PEX netlist, and then this PEX netlist is used in a test bench to run a post layout simulation to validate our design. Okay, so this is my final slide for this demo purpose. So there are these different tools used. For the Xscheme tool is used to create a schematic and also to generate netlist. ngSpice is a simulation tool which is used to run a circuit simulation. Basically, you want to validate your design, different kind of analysis. You need to run operating point, DC, AC, transient, to validate your design. Once this is run, you're happy with your design, then you move to Magic to do the layout. And Magic tool plays different roles. Like it is used to do a layout. It is used to run the extraction, PEX netlist, and also it is used to do the DRC validation, DRC check on your layout. So all these steps are performed using Magic. And then there is a fourth tool called NetGen, which is used to run LVS, layout versus schematic check. So these are this I am talking about open source EDA tools. If you are doing your design with commercial tools, Cadence, Synopsys, so they have equivalent tools there, and they have different tool names and licenses. But basically the step remains same. You create a schematic, run the simulation, do the layout, do the verification checks till you are happy with your design, and then do a tape off. Okay, I think that was my last slide for today. Thank you very much. So let us see if you have any queries. So we can quickly look into those. So if anybody has any queries, you can please put it in the chat box or Q&A box. Okay, so there is question from Mohammed. How much impact do parasitic elements have on digital IC design and layout as opposed to analog IC design and layout? So Mohammed, generally what we have seen, if your digital design is very large, by large I mean it uses a lot of transistors, it becomes very dense, compact design. So obviously, if you try to place your lot of transistors very near to each other, then they do play significant role. So your timing analysis will get degraded. So there are different kind of timing issues that can creep in your design, and then there can be IR drop issues. So it all depends on the complexity of your digital IC design. If it is very compact, very big design, obviously parasitic can play a role there. Okay, so if you're talking about Mohammed specifically about sky water, so it's just not like you will directly get it in a mail. So in open source ecosystem, there's a company called eFabless in between. We send our design to them. They compile all the designs into a masking setup, and then that basically final processed designs from all the customers compiled into a single mask are sent to a foundry. They do the processing, they generate the wafer, and those wafers are sent to eFabless, and then they send those designs to the final customer. Yeah, ultimately it will be sent through the post to you, but then there's a intermediary in between foundry and a user customer. So eFabless plays a role in between to handle all those logistic issues. Okay, so I think we can conclude for today. And if anybody still has any question, you can please put your queries on Slack. Please join that Slack. I think I have sent invitation to a lot of people who have still not joined. So in order to basically become member of that Slack channel, you have to join that invitation, and we can discuss any further queries there. And I will be putting the slides for viewing on Slack channel itself. So if anybody wants to access those slides, please join the Slack. Okay, thank you everyone, and we will meet tomorrow same time. And bye. Good day. Okay, so I think I can start now. So good evening, everyone. So I think there is a small change in the schedule. So I think the fab lecture will be held tomorrow, and this is the post fabrication lecture, which was supposed to be held on 5th, but I am taking this lecture today. So I think let us start. So basically, in last two lectures, I gave you a brief overview of the semiconductor industries and the different domains and what kind of activities are done there and some career possibilities if somebody wants to make a career into this domain, there are a lot of opportunities available. Only thing is you need to focus on which is your strong point and which are the skills which you are having or the interest you have in, and accordingly you can target the field where you want to enter into semiconductor industry. It can be design, IC design, fabrication, testing, packaging, chemicals, materials. There are different kind of domains available. But specifically as part of these series of lecture, we are focusing on design. So that is what I covered yesterday in yesterday's two lectures. First, I went through some theory about what are the different design steps to be followed, and then I gave you a brief idea of how the design steps are performed. We need some softwares to build on our design, and after following different kind of steps, when our design is finalized, that design is sent to the foundry for fabrication, and foundry takes its own time. I told you 1 to 3 months is the normal time period which a fab takes. But what happens after the fab? We all, I think, in our day-to-day life and news, if you are looking at what are the development happening in world, I think the foundry or fab is something which is in limelight, because that is the most sophisticated or costly part of the complete semiconductor development cycle. But after that also there are few steps and very critical steps which needs to be performed, so that the final product, that is a complete IC or a packaged device, is built. And that is what is finally required ultimately to build all the products which we use in our daily lives. So all the smartphones or the automobile, the different kind of ICs which go into them, and all the defense equipment, anything, communication, laptops, etc. So all these are the final products. But inside those product lies the IC, integrated circuit. Inside an integrated circuit is a silicon. So idea is to give you a complete development cycle, like how from a concept to a final product is realized. Okay, so let us delve into today's slides, and I will discuss further with you. So this is what we discussed yesterday. These are all the different steps which are basically performed in order to for the complete development cycle of an IC. So we covered these VLSI design steps yesterday, and the foundry steps I mentioned you. This is all in all together a different process, and all the kind of activities which take place there. But this is the part which we will be focusing tomorrow. This is called ATMP. So ATMP is a separate, basically, kind of a it is not a manufacturing but a processing unit, where a processed wafer comes from a foundry, and then that wafer is converted into a final IC. But before that, there are different activities or steps which are required. So when a wafer comes directly to our ATMP unit, so full form of ATMP is assembly, testing, marking, and packaging. So ATMP is an abbreviation. The full form is assembly, testing, marking, and packaging. So these are different steps which take place in this kind of unit. So once a wafer comes to a ATMP plant or unit, first thing is to do a wafer level testing. So why is it is done? Because we need to identify which all dies are functional on the wafer. So although a uniform foundry tries to do a uniform processing of all the fabrication steps on a wafer, but there are some kind of it's not like everything can be perfect. So there might be some deviations during the manufacturing of fabrication, due to which some dies might not have been processed uniformly. And definitely, if they are not processed uniformly, there might be some issue with them and they might not work. So the first task is in wafer level testing to identify those dies. So once wafer level testing is done, then we go move to packaging. We need to separate those dies, and packaging is done. And after packaging, we need to check the reliability and characterization. So by reliability, we mean to ensure like these ICs which have been developed after so much sophistication and process, whether they are working properly or not. We need to ensure their performance, durability, how long those ICs run. So there are different kind of reliability check or tests which are performed. So these are some of the steps, and in further slides we will see these steps in detail. Each of these steps, like what are the different kind of activities or materials used in order to complete these ATMP steps. Okay, before that, I think this is also an important point. When we talk about a wafer, semiconductor wafer or silicon wafer, it's not like all the wafers of uniform dimension. So the wafers are basically defined by their diameter. So there are different diameter wafers. These can be 4-inch wafer, 6-inch wafer, 8-inch and 12-inch wafer. These are the common wafer sizes which are used for processing. And there is a specific reason or requirement why different kind of dimension is used for that purpose. And also, mind you, all the foundries which process these wafer, they also have a requirement there. They want all the equipments which are there inside a foundry, they are basically designed to process a specific diameter of wafer only. It's not like a 4-inch foundry can handle a 12-inch wafer, or a 12-inch foundry can handle a 4-inch wafer. So it is also a very critical parameter. Okay, so why different wafers are used is because of their requirement. So 4-inch wafers, obviously they are very small, and they are mostly used for some kind of semiconductor devices which are for R&D nature, or if you want to do some kind of prototyping, or you want to develop a discrete semiconductor device like a discrete transistor or discrete BJT or IGBT. So these are basically requirements which are not very complex in nature, and the quantities or amounts involved are very small. So for those kind of activities, small size wafers are used. And then there are 6-inch wafers. So again, the complexity increases a little bit. So what kind of applications they process are like MEMS design. If you want to do some kind of a MEMS sensor development, accelerometer, gyroscope, etc., different kind of sensors, or if you are building a power electronics or optoelectronic devices. So these are applications or devices which are of medium scale. These are obviously important, but these do not involve too much quantities which needs to be manufactured. So that's why 6-inch wafers are ideal to be used for these kind of application. And then comes 8-inch wafers. So these are suitable for when you are looking for high volume manufacturing, and especially for analog and mixed signal ICs or automotive chips. And so mostly the older generation technology nodes like maybe 90 nanometer to 180, 350, 0.25 micron. These kind of nodes are mostly used for these kind of applications. These are analog, mixed signal, automotive. So they are the one which basically use these kind of eight wafers. Okay, I think some people are facing issue in seeing my screen, so I will share my screen. I hope my slides are visible now. Okay. So 8-inch wafers are, I talked about, these are used for mature node technologies like 90 nanometer, 180, 250, 350. It's kind of the which are not like cutting edge technology nodes. So those are the applications of IC for which these wafers are used. And then comes the biggest or the largest diameter wafer, is that 12-inch wafer, and they are used for very high volume manufacturing, and which mostly includes digital kind of devices like kind of modern logic devices, CPUs, GPUs, memories, and other cutting edge semiconductor devices. So these are the wafers where the volume is very important. You want to get maximum number of devices from a single wafer. You want to have a good yield. So those kind of requirements are fulfilled by these dimension of wafers. Okay, so it is important because uh, whatever manufacturing setup or ATMP setup is basically developed by the organizations, the one very critical criteria of that is the what kind of wafers they can handle, what are the diameter of the, because based on that all the equipment and machineries are set up in those units. So it is one critical element. Okay, so now we move to semiconductor packaging. So why do we need semiconductor packaging? What is the basic concept or requirement behind it? Because, and more thing is like it is not a very glamorous area might be in semiconductor domain, because design, IC design and IC manufacturing, that is fab. basically gets all the limelight. But it's not like you can ignore this. It is also very important because ultimately you cannot use a raw die inside your product. You need to get it packaged. So obviously it might not be that complex, but it still have its significance. And we need to do packaging and all these activities because we want to make our devices more reliable. We do not want to them to expose to the external environment where they can get easily damaged. So that's why we need proper packaging and assembly of our dies into a suitable package. Okay, so in this single slide, I have tried to capture all the steps which are followed once a raw wafer comes out of a foundry. And now in following slide, I will describe all of these individual steps in a little bit detail. But to basically summarize, a wafer comes. Okay, so a wafer comes out of a foundry. This is a processed wafer where all the steps have been completed and there are different dies fabricated on this wafer. From this wafer, individual die is extracted. So this wafer is cut, basically diced into multiple separate dies. And then a single die is extracted from this wafer. Then this die is attached onto a lead frame. What is lead frame? Basically, lead frame is kind of a structure, metal structure, which has different metal leads which are used to make the interconnect or metal connection to this die used via bond wire. So this is a structure which holds this separated die in center of it in a cavity. So once it is attached, then a wire bonding is done because on the periphery of this die there are IO pads. Those IO pads are basically bonded to the lead frames, and accordingly electrical connection is made. But still, after this also the bond, this complete structure is exposed. So we cannot keep it exposed. So basically, it is covered with a molding material, and this molding material can be mostly like a plastic or a ceramic based on the requirement. So after that is done, the device looks like this. So, but there is still no identity given to this device. So how can we know like what this device is, or like what function it performs, because all the ICs look same. If we do not have a specific part number over it or the company name, or there is other information like some code assigned to it, there can be different versions of a device, or there are some specific codes put on the top of a IC by the companies themselves because they want to identify what lot or what location those devices were manufactured. So all that information is basically imprinted in form of a marking. So I mentioned you there is that this complete activity is called ATMP activity. So that were assembly, testing, and marking. This is that marking and then packaging. So after this logo is done, so this basically lead frame is kind of a copper metal, and it is prone to the oxidation and getting corrosion. So that's why it's basically implanted with tin so that the corrosive properties of copper can be restricted and there are no side effects or due to of corrosion on the electrical properties of these leads. So after that, this all the pins which are slotted in this lead frame, these are separated and accordingly, and the shape is given to individual pins, and then a final package to device goes to testing. So this is all the steps. Now let us see these steps in little bit detail. This is basically shows you what all steps are performed on a raw semiconductor wafer. So that's why I was emphasizing it's not a simple activity. There are a lot of steps and a lot of specialization involved in it. And again, there are a lot of good career opportunities in this domain also. If you want to enter into field, there are a lot of scope because each of these steps requires specialization and there are dedicated engineers or technicians who handle this. Okay, so now let us go into a little bit detail. So once a wafer comes out of a fab, so first thing is done to do a wafer level testing. So what is wafer level testing is like you place a wafer on a basically probe station or there is a chuck which holds that wafer. There are vacuums which are applied to a wafer from the back, so that the wafer gets stuck on a uh, uh, chuck of a probe station, and then there are probes, metal probes, through which the signals are applied directly on a wafer. It's not like we are doing testing on a package. So there are IO pads on different dies. So connections are made through these probes. These probes are very thin, and they are you and they on these probe arms, the appropriate signals are given through whatever equipment you are trying to give signal to this structure on a silicon processed wafer, and then basic testing is done. And what is the purpose of this testing? As I told you, after processing on a wafer, it's not like everything gets processed uniformly. There might be some deviations. Some particular process might not have been properly processed on a wafer. So for that purpose, some dies might not be functioning properly. So it's better to do that testing of those dies which are not working at the wafer level, because uh, at some stage you want to know like which die is working, which IC which has been manufactured is working or not, because you do not package it and then send to the customer, and then customer comes back to you like this IC is not working. So but also you do not want to spend a lot of time and also cost involved in packaging and all these steps which I have mentioned in this slide. So just before performing all these steps on individual die, you need to identify at the wafer stage itself, like which die is working or not. So that's why a basic or preliminary test is done on a wafer itself using probe station and probes. And while doing that testing, a marking is done on individual dies. So how that marking is done? It's like this: there is a wafer map is prepared, and all the individual testing of each die is done. And this testing is done very fast because this is all automated. It's not a manual. You give the basically coordinates of dies feed to the computer and the automatic tester equipment, and it handles everything and give the location of probes, what kind of signal needs to be applied, and everything happens automatically. So the probe moves from one die to another and keep on testing. And if a test result is failing, there a wafer map will show you like this die is not working, and at that time only a drop of ink is placed on that particular die. Like this die is not working, it's not functional, so it can be ignored after dicing. So this kind of wafer map is prepared. Like if ink is dropped on a die, like this black dot, it is defective. It cannot be used. And on a wafer map, it is marked as red. And all the good dies which are passing the basic test, they are good dies, and they can be further processed in for assembly, packaging, and other activities. And one other thing is all because this is the wafer is round, and then there are some peripheral dies. And the issue with these peripheral dies are like they are partially processed during all the manufacturing, like litho, etching, everything. So these are, since they are partially processed, obviously some of the structures which are required to be fabricated on these dies, they are not manufactured properly. So obviously they are not working. So all these partially etched dies are also marked, so that after dicing, these dies can also be ignored. So this is what all happens after wafer level testing and defect marking. And as I again mentioned to you earlier, like why we do this? Because we want to discard all the defective chip. We do not want to take them and consider them for further packaging and other activities. So this saves a lot of resources and also time and also cost for the company. Okay, so once wafer level testing is done, the ink is placed on all the defective dies. So the next step is to segregate individual dies from a wafer. So this is a complete wafer. There are a number of dies which are imprinted on this wafer, and there is a spacing between these dies, individual dies. So this spacing can be anything from 100 to 200 micrometer, and this spacing is called scribe line. So this spacing is specifically kept on a wafer surface so that our cutter can move, and these dies can be cut and these individual dies can be separated. So this is how a cutter will move, and this cutter can be a diamond plate cutter, or there are laser or plasma cutter also available. So whatever the technique or technology is available, these cutters are run and this on this wafer, and these individual dies are extracted. So after extraction, each individual die will look something like this. And then there are some technical consideration while using this dicing, like what kind of a die size is, what is the material of that size, what is the thickness of the wafer, and during dicing, a lot of debris are generated. So how to clear those debris, and there are other specific equipments which are used for this activity. Like I mentioned, there are saws, laser machines, or plasma systems. So based on the requirement of die or wafer, these all individual equipments are used specifically for this cutting purpose. And this step is called basically in our terminology dicing. Basically, you are dicing and you are segregating dies from a fixed wafer. Okay, so once our die is extracted, now comes the next step. Like we want to convert this die or place this die into a package. So how that starts? Then there is a lead frame. Okay, so as I mentioned, this lead frame is a structure, metallic structure, which is basically designed in such a way like it provides the structural support and electrical connections from a die pads to the external world. So this metal structure, it is generally made of copper. There is a basically die attached pad in the center, and this is the place where a die is placed. But obviously when you are placing your die and die is very sensitive, you do not want it to basically be loose and move on that surface. So basically there is a material epoxy used. It is a sticking material which is used to stick your individual die to this die frame. Epoxy material is placed and a die is put and pressed a little bit. The appropriate amount of pressure is applied so that that die gets stuck on this landing pad. And after that, this some of this epoxy material, it also gets basically spread over this die pad frame, and a small layer kind of forms on the periphery of a die called epoxy fillet. And this epoxy material also has some significance because this material not only provides a mechanical support to die, but it also enhances thermal and electrical properties. Because when a die is actually, well, like all the circuits on your die is working, like a lot of heat is generated. So this epoxy material is has the properties which helps to basically take that heat from back of a die and basically helps to reduce the thermal exposure to the die, and it helps in increasing the performance of your die. Not increasing, but it helps not the performance should not get deteriorated due to the thermal issues. Because if a temperature of your die or package increases too much, so that semiconductor properties of a material on that die will get deviated from its performance. So that's why this epoxy plays a role in basically taking away the heat from a die material. So this is what a die after placing a die and sticking it on a lead frame, it looks like. Okay, so once a die is placed, but still because this die is not electrically connected to this die frame, so all these metal pins which you are seeing, these are individual pins, and there is some kind of electrical connection needs to be made to your die form this metal pins. So this is how it is done. So as highlighted here on the periphery of your die, there are bond pads or IO pads. So these are the metal structure which are they have a significant area, generally is anything from 50 micrometer by 50 micrometer to 100 by 100 micrometer. So these are landing pads, thick basically white metal exposed on the periphery of dies, to which all the internal connections are made to this structure. So there can be different kind of processing happening inside this die based on the design which has been made. And but then we need to give some kind of input signal, so that input signals are also given through these pads, IO pads, and these metal structure. And similarly, if output signal needs to be taken from this die, and again this that has to be taken from this bond patch. But then how to connect this bond patch to these leads? So this is how it is done. It is done using metal wire. So there is very thin metal wire. Its diameter is almost as big as the area of these pads. Generally, it varies from 1 mil to 2 mil. That is 1 mil is around 25 micrometers. So you can think about 25 micrometer to 50 micrometer diameter of these bond wires. These bond wires are basically pasted from the bond pads to these leads of the lead frame. This is how a metal connection is made between your die and to the lead frame of a package. In this picture, I think it's not visible, but there are these bond wires shown, in yellow color. So that's how electrical connection is made from die to lead frames. And then whatever external connections need to be made to this pin, that we will see in next slides. Okay, so one important thing is this bonding, generating this bond wire from bond pad to leads. It is done using a specific machine. These are called wire bonders. These are again a complex set of machinery, and then there are different parameters for building this. It's not like it is very simple because you are talking about diameter or dimensions of micrometer, and then it also depends on the number of pads. There can be small number of pads, or there can be hundreds or thousands, not thousands, but maybe 100 or 200 or maybe 400 bond pads for a complex chip. So it means like let us say if there are 400 bond pads, 400 bond wire connections need to be made. So you can understand how complex it becomes. So there are specific machines to which all this information which is required, like which bond pad needs to be bonded to which lead, is put, and based on the material of your die and the lead and also the material used to create this bond wire, appropriate amount of heat, pressure, etc. is applied by that bond wire, and automatic bonding is done. So this is again a complex set of equipment and step which is performed inside an ATMP unit. Okay, so we have seen that bonding is done and a wire bonder is used. So what kind of material is used for wire bonding? So I think yesterday I mentioned the bond pads or the metals which are used for a die in a die are generally aluminum and copper. So obviously when these materials are used for die, so obviously these are the preferred material for bonding also, but there are some other materials. So let us see what are these materials and what are their advantage and disadvantage. So gold is one of the best material for bonding because it has very good conductivity, and also it is not uh, corrosive, like it is resistant to corrosion. So these are good properties, but obviously disadvantage is like it is very costly. You cannot, but mind you, like whatever ICs which are used in our mobile phones, they do have like significant amount of gold. Some of those ICs in them because they do use some of the complex ICs. They do use gold for bonding purpose, which require the excellent, like good conductivity, and they want a long duration of reliability. So they do not want corrosion to happen in them. So those kind of application do use gold. And nowadays, since a lot of semiconductor waste is getting generated, I know for sure like this is also kind of a good business, scrapping business. Like a lot of companies are working around the world who take old and obsolete ICs and they try to dig out gold from those ICs, because you can think like how much semiconductor waste is getting generated in the world. Even if you are able to extract small amount of gold from one IC and the amount of ICs you are processing or scavenging to extract the gold wires. So this is becoming a good business nowadays to extract gold from obsolete ICs. Okay, so the next preferred material is aluminium. It has good conductivity and it is also not very costly. But issue with it is like it is susceptible to corrosion and its bond strength is less. So sometimes the bonds, wires or bonds made using aluminium wire, they are susceptible to get break down, and that is what something which you do not want, because you want, once a bonding is done, a package is done, you cannot do anything. You cannot repair a bond wire which has broken. So that's why if you want high reliable ICs, and you do not, for example, if you're using some IC for space mission or something, on those kind of places, you might not prefer aluminum kind of bond wires. And then comes copper. So this is the best material because it has the highest conductivity, it is cost effective, it has good mechanical strength also. But it is again susceptible to oxidation, so there can be some corrosion caused in copper wires. But most important thing is like copper is very difficult to handle in fabrication or in semiconductor manufacturing. So copper has its own challenges if so sometimes that's why it is not preferred, because it makes the bonding process, and also when a copper is used as a metallization in fabrication, the manufacturing process a little bit complex. So that's why copper is not preferred. But still, if there is a requirement of very good conductivity, definitely it can be used. And another material which is used for bonding as a bond wire is silver. It again has a high conductivity, but again it has high cost, and it also degrades with time. So it's not like one material is preferred for other. Each of them has its own advantages and disadvantages. So it all depends upon your technical requirements, which material helps meet your technical requirement best, and how much cost you are ready to pay for this activity. So all these are the considerations which are taken in review while finalizing the bond wires or the material for that purpose. Okay, so once we see, like, this was our last stage, our IC has been pasted on the this landing pad of lead frame. Bond wire is connected, bonding is done. So this is how our structure looks after this stage. So next step is, but still this die is exposed, bond wires are exposed. So next thing is to cover this. We do not want this setup to be exposed, so we will cover it. So this is the next step. So this exposed die area is basically molded. These are molding material. Again, this material can be plastic or ceramic based on the requirements. So this molding step is done, and it helps to basically protect your die, inside die. It encapsulates it, shields it from various environmental factors or any physical damage. And this molding material also helps to dissipate heat from your core of your ICs. And as I mentioned, the typical material used for molding is plastic or ceramic. So, what are the advantages and disadvantages? Plastic is obviously very cheap, so that's why it is preferred in low cost applications or applications which are not very like quality stringent. But if there are very quality stringent applications, mostly like in defense or space applications, because there the systems they need to last for long. It's not like if you have sent something in space in satellite and a system is exposed to outside world and it starts like package is dysfunctional or it doesn't saves your core IC. So those are the applications where a ceramic material is used to do the molding of your IC. And ceramic material is much costlier than package IC. So it also impacts the overall cost of your final IC. But then for critical applications like defense and space, even with extra cost, you do not want to take risk of your IC getting damaged or failing while working in outer world. So once molding is done, this is how a final, not final, but processed device till this stage looks like. And this is a side view. This is if you tilt this IC and see it from side, this is how it will look like. Okay, so once molding is done, as I mentioned, if you see it from naked eye or outside world, it just look like a black IC. You cannot make out like what is the function of this IC, or what is the which company it has manufactured, or any other information. Specifically from a designer's point of view, or the PCB designer or system designer, he wants to know the part number of that IC, because companies, along with a packaged device, they provide their data sheet, and data sheet consists of all the information which is required for that particular device. So ultimately, you need to check an IC and see which that IC is, which is that part number, or if you are worried about the company, like different companies manufacturing similar kind of ICs sometimes. You want to understand like this IC is from Texas Instrument or this IC is from ST Microelectronics or NXP. So all that information is marked or printed on the top of this IC. And apart from that, some information even companies put from their side. They like you can see on the right side, this analog device IC, lot of some codes are put there because they want to, in case something when this IC goes into a field and it is not performing or it is failing, and our customer is complaining like your IC is not working or something bad has happened. So they will send this IC back to the company, and but they need to understand like in order to debug the issue or do kind of a failure analysis of IC, they need to understand like where this IC was manufactured or what all happened with this IC, because it could there are different fabs, similar kind of fab. It could have been manufactured in any of them. So all that information is coded in some company specific codes so that companies later on can do some kind of tracing of this IC in order to do failure analysis. Okay, so what are the ways of putting this information on like this marking on this IC? There's a simple way of using some kind of a ink. So like it is kind of a stamping done on the top, or then there are some laser markers also available. So these are two ways using which are the all the marking information or the related information for that IC is imprinted on top of the IC. So again, you can see like how these are small steps, but then altogether they form a long chain of steps which needs to be performed before your IC is ready to be delivered to customer for embedding it in their product. These are small steps. Okay, so the lead frame which you are seeing till now, it is a copper lead frame. And as I showed you, copper has some corrosive properties. So, but we do not want it to be exposed to the direct environment where it can get corroded, because corrosion will definitely affect its electrical properties and also degrade its performance. So in order to avoid that, what is done is all the lead frames on the periphery of this device are plated with tin so that rusting can be prevented, and that this will ensure the long-term reliability of this IC. So that, because ultimately you don't know where this IC will be used, in which kind of environment. It can be used in high temperature or dusty environment, or it can be used in cold temperature. So we do not know. But the task of a company or manufacturer is to ensure from his side to ensure the maximum reliability for that IC. So one way which it can get basically degraded or its performance can be lowered is due to corrosion of these pins. So to avoid that, tin plating is done. And another thing is you must be knowing the solder wires which are used, they are also made of tin compounds. So when the pins of these ICs are basically plated with tin, and when this IC is assembled on a PCB using soldering wires, soldering material, it will ensure a good soldering or good bonding of these IC pins to that PCB. So this is also one of the reasons for doing this. So I was talking about lead frames, how all the different steps are done, dies placed on the landing pad, and all different steps, bonding, etc. performed. So this step which is happening is not happening for individual lead frames. So there is a big lead frame strip, like here you can see based on the size of your die. If there is a small die, then on a single lead frame, different in single strip multiple lead frames can be accommodated. If your die is big, so you can see there is the area of this strip is same, but lesser number of frames are accommodated here. So all these steps which I was discussing in previous steps, they are happening simultaneously on this single strip. So in single strip, like let us say there are 7 or 14 lead frames on this single strip. So 14 dies will be put, and all the steps will be happening in parallel to all the dies on this lead frame. So till this stage, when molding is done and marking is done, all these packages are still jointed together on this single lead frame, because obviously this gives you benefit of parallel processing. If you try to do these steps on single lead frame, then it will obviously take a lot of time, and there are cost and economics involved. So it's better to do. It's something similar to how manufacturing of so many dies are happening simultaneously on a single wafer. So similarly, in ATMP steps, a lead frame strip is there, multiple dies are put on it, and all the steps are happening in parallel. And once it is done, after the tin plating step, you need to extract, or you similar to something of dicing. These individual packaged ICs are extracted from this lead frame, and this is how a final device will look like. But one thing is, like, these leads from this extracted lead frame or from this strip, these will be straight, and are also connected with this metal line. This is because we want to give a kind of a solid structure to these lead frames while all these steps are taking place. But now we need to separate these pins. So accordingly, when this single lead frame is separated from this strip, after that leads are bent like this, and then we are singulating each package from this lead frame. So these steps are called trimming. We are trimming these leads. We are cutting them into separate pins. After that, forms like this kind of, there are different kind of pins like J pin, S pins, and different packages have different kind of pin shapes. So accordingly, what kind of a pin shape is required, that shape is given. So this is called form step. A trim step, separating the pins. Form step, like giving a specific shape to the pin so that it can be placed on a PCB, and suitable soldering can be done. And this step is called singulation. So you are singulating an individual package device from this uh, like combined lead strip. So these are small steps, but again they have their own significance in this whole activity. Okay, so this is your package device, and now this is something which is ready to be tested. This thorough testing will be done by test engineers. There will be a test plan, what kind of evaluation needs to be done. Then this activity takes place in testing unit. Once testing is done and it is cleared, like now this package device is okay, it is sent to a final customer. And what happens to this package devices? Like, this is your packaged IC, and this is an example of a smartphone PCB which I have taken. So this is how sophisticated PCB of a smartphone looks like, and there are a number of ICs in it. So this IC will be part of this kind of a PCB. Uh, it can be any PCB. It can be a PCB for power electronics, automobile, or other devices. But since we know, like, some smartphone is one of the most sophisticated electronic device, I have taken example of that. And not only this specific IC, but there will be several other such IC. Each one will be performing its own functionality into it. So this is how a piece, I package IC is placed. It is soldered, and a final PCB takes form. But then inside any device or any system, there are several other functionalities. Like, these are all the electrical functionalities which are required to be performed in this smartphone. Accordingly, ICs are taken and assembled. But apart from that, you need different other devices like camera, battery, and there are the ribbon wires which are used to connect. So everything is assembled, and this is how a smartphone will look like if you tear it down it from back, and then this forms gives shape to your final product. So this is how a journey looks like. We started from yesterday. We saw from design stage how a concept is taken. Some concept is taken. Design needs to be done. And then the design involves different kind of steps which needs to be performed. Then design is sent to a fab for fabrication. Once wafer comes out of fab, and then different kind of activities which we saw today, starting from wafer level testing, and then doing dicing of your wafer, then putting dice on a lead frame, then doing bonding, then encapsulation, molding, and tin plating, everything. And then a final package IC comes into form. And then this IC gets integrated into a PC, and then a final product is delivered to you, which we use in our daily lives. So you can understand how complex this whole process looks like, but it's not like a single company or single small team is able to do. So at every stage or every step, there are specialized people who are involved. There are specialized teams, specialized equipment, specialized setup required. So there's a lot of requirement of skilled manpower to perform all these semiconductor development activities. And that's what was the purpose of this lecture series, was to show you top level overview, like how a semiconductor development looks like, and try to, if you want, you to enter into this industry, choose your area wherever you want to get into, and accordingly benefit from whatever revolution is happening in the world in field of semiconductors. Okay, thank you. I think that was all from my side for today. If anybody has any questions, please put them in chat box or Q&A. Someone is asking, why do we choose circle wafer instead of square? So I think last time also I mentioned you, it's when a wafer is placed on machinery. So different kind of on inside fab on equipment, different kind of processing steps are taking place, and those steps need to be uniformly processed on a wafer. And it's inside a fab, it's very easy to handle if a wafer is in square. Like you can rotate it on a chuck, or different kind positioning can be done on the equipment, but it's not very easy to handle a square wafer. So that's why because all these things have evolved over a lot of years. People have tried to do different kind of experiments on different shapes or sizes of wafers, and that's how all the modern things have evolved. So the short answer is like it is easier to handle and process circle wafer inside a fab rather than a square wafers. So any other questions? We have some time. Or you can also put your queries on Slack, any technical queries related to these lectures which I have delivered, or any other topic related to semiconductor domain. If I am able to answer, I will definitely answer the queries on Slack. Okay, I think if no more questions, we can see. Okay, yeah, I sent a link for Slack in last two lectures. I will once again share it here. For people who have not joined it, you will get a invitation. Fill this form, and you will receive an invitation to join Slack. Those who have already filled this form, please do not fill it again. You might already have received the invitation to join Slack. Okay, thank you everyone. If we can conclude for today, and tomorrow there will be the next lecture on introduction to Fab, and we will meet tomorrow. Thank you. Bye. Have a nice day.
السلام عليكم ورحمة الله وبركاته. أسعد الله مساءكم جميعا بكل خير، وحياكم الله في اليوم الرابع والأخير من دورة مقدمة عن الرقائق الإلكترونية من التصميم إلى التصنيع والاختبار. في اليوم الأول أخذنا فكرة كاملة عن الرقائق الإلكترونية، كيف عملية التصميم والتصنيع، وش هي أشباه الموصلات، كيف ممكن نستخدم أشباه الموصلات في حياتنا اليومية، التطبيقات المختلفة من السيارات، الأجهزة الإلكترونية، إنترنت الأشياء، الذكاء الاصطناعي، التطبيقات المختلفة لأشباه الموصلات في حياتنا اليومية. تطرقنا لها في اليوم الأول وشفنا Semiconductor value chain, Semiconductor market. That was within the first day. The second day, engineer people has provided actually information about the IC design, how we can design the IC, the flow chart of the IC design, starting from the idea till the design. And also yesterday, engineering people provide more details about the testing of the fabricated IC design, IC chips. So today, inshallah, الدكتور عدنان زمان راح يقدم لكم نظرة عامة وشاملة عن تصنيع الرقائق الإلكترونية، خطوات تصنيع الرقائق الإلكترونية في المختبر. فراح يكون عرضه خلال تقريبا من ساعة ونص إلى ساعتين إن شاء الله. بيعطيكم فكرة عن طرق تصنيع الرقائق الإلكترونية، مراحل تصنيع الرقائق الإلكترونية، وكذلك كيف ممكن ننتقل من الديزاين إلى ما يكون عندي يعني تشيب أو رقائق إلكترونية يتم تصنيعها بالكامل. طبعا قبل ما نبدأ في محاضرة الدكتور عدنان، أنا حريص أني أتيح فرصة للجميع إذا في أي أسئلة، أي استفسارات، أي ملاحظات. فالchat I believe it's open, so if you have any questions just don't hesitate to write it. لا تتردد إنك تكتب سؤالك في الميتينج شات. الآن زميلنا عبد المنعم راح يزودكم كذلك برابط للاستبيان. أشكر كل من شارك بالاستبيان. الاستبيان هدف منه تعزيز وتفعيل دور الحضور في تجويد وتحسين مخرجات هالبرامج التدريبية في الرقائق الإلكترونية. فأطلب منكم بشكل آخر أو بشكل ثاني أنكم تشاركون اللي ما شارك في الاستبيان. عبد المنعم ممكن الآن تحط الاستبيان في الشات، رابط الاستبيان في الشات. فاللي ما شارك يكرمنا بمشاركته ويعطينا ملاحظاته حتى نطورها للبرامج التدريبية القادمة. جدير بالذكر أنه إن شاء الله الأسبوع القادم في برنامج تدريبي عن تصنيع الرقائق الإلكترونية. البرنامج التدريبي راح يشارك فيه 5 من نخبة الزملاء اللي حاصلين على شهادة الدكتوراه في تصميم وتصنيع الرقائق الإلكترونية. البرنامج راح يكون مدته تقريبا 15 ساعة تدريبية في واقع 3 ساعات يوميا لمدة 5 أيام. نستهدف في البرنامج القادم اللي هو تعزيز مفاهيم التصنيع بشكل أكثر تفصيلي عن الرقائق الإلكترونية، كيف ممكن أصنع الرقائق الإلكترونية، الخطوات المختلفة، الأجهزة اللي أستخدمها في التصنيع، وكيف ممكن إني أطور فكرتي حتى أطلع بجهاز أو semiconductor device. أنا بترك المجال 5 دقائق للأسئلة. إذا في أي سؤال ممكن تتفضلون فيه، تكتبونه بس على الشات وأنا موجود للإجابة. Engineer people will be available to answer any questions as well.
So good evening, everyone. If anybody has any questions, you can please put it on Q&A box or chat box. I will be happy to answer to any questions related to my lectures.
السلام عليكم.
عليكم السلام، تفضل.
أيوة، بس أنا عندي استفسار عن البرنامج القادم، اللي هو تصنيع الرقائق. لأني أنا جيت شاركت فيه وانقبلت، لكن ما أقدر أخش على التيم نفسه، الجروب. يطلب مني إنه يكون عندي إيميل من منظمة أو كذا organization. وأنا خريج يعني، ما عندي إيميل زي كذا.
طيب، أنا أعتقد البرنامج راح يبدأ إن شاء الله الأسبوع القادم. فإذا كان في خلل تقني يمكن معالجته إن شاء الله قبل الأسبوع القادم. فبإذن الله الأحد القادم أو قبل الأحد القادم إن شاء الله راح تقدر تدخل على البرنامج. أنا بتأكد مع الزملاء في الآي تي إنه ما يكون فيها الإشكال إن شاء الله. شكرا يا عبد الله.
عفوا.
عبد المنعم، أنا ما أعرف، يمكن الشات مسكر، تقدر تفتحه من عندك أو تركي.
أتوقع صحيح مقفل، يمكن الإخوان في الأكاديمية لو يفتحون لنا.
السلام عليكم.
والسلام، حياك الله دكتور. بس احنا ننتظر لو في أي سؤال قبل، بس لو تعطينا بس إلى 4:15 لو سمحت يا دكتور. بعدها إن شاء الله نبدأ، بس ممكن you can start to share your screen يعني. لو في أي سؤال خلال 3 دقائق الجاية.
طيب تقدروا تشوفوا الشاشة عشان أتأكد إنه كل شيء
واضحة
تمام؟
دكتور، واضحة.
دقيقة بس أتأكد. الآن فل سكرين واضحة عندكم؟
واضحة دكتور.
ممتاز. طيب نبدأ إن شاء الله خلال 4 دقائق.
عبد الله إذا عندك سؤال تفضل.
أيوة معلش، بس إنه الشات مقفل لحد الآن. صوتي واضح؟ ألو؟
واضح يا عبد الله. طيب خلاص، واضح إن شاء الله.
أي بس معلش، استفسار سريع بعد.
تفضل.
على السؤال اللي قبل سألتك عن البرنامج القادم، بس إنه مين اللي أقدر أتواصل معاه، أو أي إيميل أقدر أتواصل معاه عشان
على ال SSB support.
SSB support. تمام.
شكرا.
السلام عليكم.
السلام ورحمة الله.
بالنسبة لتسجيل المحاضرات هل يمكن نشرها؟ لأنه مع كثرة المعلومات في أشياء تفوتنا. تفضل.
طيب، عبد المنعم مسجل المعلومة هذه أو النقطة هذه. إن شاء الله راح يتم إرسال الرابط للمحاضرة للجميع بإذن الله. لكن أهم شيء تكونون within السلاك. اللي ما سجل بالسلاك أو ما انضم للسلاك ينضم.
تمام جزاك.
أهلا وسهلا. طيب، في أي سؤال ثاني؟ دكتور عدنان تقدر تبدأ. الله يعطيك العافية وتمنياتي للجميع بالتوفيق.
طيب الله يعطيك العافية دكتور سلمان. حياكم الله جميعا. دكتور سلمان، اليومين الماضية إيش كانت محاضرته معليش؟
في أول يوم كان عن أشباه الموصلات بشكل عام. Second and third day it was about IC design and testing of IC chips.
يعني ياخذوا كاركترايزيشن ما يحتاج اغطيه.
Yes.
ممتاز. فابريكيشن اليوم ممتاز، الله يعطيك العافيه. المحاضره عربي ولا عربي عادي ولا انجليزي يبغوه؟
It's up to you.
طيب نكمل عربي، ما مشكله، بسم الله. طيب حياكم الله جميعا، معكم الدكتور عدنان زمان. محاضره اليوم حتكون عن المايكرو فابريكيشن، حندخل فيه in details كيف يكون تصنيع اشباه الموصلات في بشكل عام في نقدر نقول مصانع السيمي كوندكتورز. اشهر المصانع الموجوده طبعا شركات كثيره اخذت محاضره عليها في اليومين الماضيه، ولكن اشهرها TSMC في تايوان، هي المسيطره على اشباه التقنيات الدقيقه في اشباه الموصلات. حنعرف السبب بحكم عمليه التصنيع في الليثوغرافي بشكل خاص. طيب حنغطي اليوم الليثوغرافي بروسيس، الاتشنج، الديبوزيشن، اوكسيديشن مع الدوبينج، الكاركترايزيشن بالاخير حنتجاوز عنه. ممكن يكون بترتيب ممكن بغير ترتيب حسب التسلسل بالمحاضرات. اللي عنده اي محاضره اذا كان الشات موجود او اي سؤال عفوا اذا صلحوا الاخوان ممكن تسالوا فيه. طيب نبدأ بسيطة عني. خلصت البكالوريوس في جامعة الملك عبد العزيز في جدة، الماجستير والدكتوراه في جامعة يونيفرسيتي ساوث فلوريدا في تامبا أمريكا، كانت عن المايكرو إلكترونيكس بشكل خاص الراديو فريكونسي اند مايكرو إلكترو ميكانيكال سيستم الميمس. الكلين روم اشتغلت فيها فترة 7 سنوات خلال فترة الدكتوراه. طبعا ما هي كافية بشكل عام، عالميا اللي يعتبروا نفسهم خبراء بكلين روم يكون قضى على الأقل 20 إلى 25 سنة، ولكن كافي إنه واحد يقدر يشتغل على أي بروجكت أو ينفذ أي مشروع ممكن إذا كان اشتغل في الغرف النقية. الغرف النقية عالم كبير، التصنيع فيه عالم ما ليه حدود، الواحد يتعلم فيه كل ما يشتغل، ولكن يقدر ينجز فيه أي مشاريع إذا كان تمكن من الأجهزة الموجودة. طيب المايكرو إلكترونيكس بما أنه أخذته مقدمة عن السيمي كوندكتورز، هي لها علاقة بالشيبس كبداية والتي فيز والكمبيوترز. كل الشيبس اللي بالداخل هذه عبارة عن تقنيات نقدر نسميها أشباه الموصلات السيمي كوندكتورز. كيف يتم تصنيعها؟ طبعا تمر بمراحل كثير في عمليات التصنيع، أغلبها تكون في الغرف النقية لأسباب حنتحدث عنها، ولكن فيها خطوات معقدة إذا عرفناها نقدر نصنع أي شيء موجود. طيب عمليات التصنيع المايكرو فابريكيشن، سمول ستراكشر طبعا، وفي بعض الحالات نقدر نقول النانو سكيل، خاصة في بعض التقنيات اللي هي في المعالجات بشكل عام. طيب هذا استراكشر للميمس، هذا يعتبر فلتر. ايش يعني فلتر؟ هذا موجود في جوالاتنا سواء نفسه او شيء مشابه له. هذا بالمايكروميتر اصغر من شعرة الانسان. هذا
دكتور
فائدته قطع
دكتور
ورجع.
سمح. لا دكتور، أنت في السلايد رقم 3 في الشاشة الآن.
ما بيتحرك معي، غريب.
الآن تحرك، الآن في السلايد رقم 7.
اوكي طيب دقيقة بس اقفل
ممكن كحل دكتور تحطه PDF في أسرع بالحركة.
الان ماشي معكم كويس؟ يمكن قطع نت
الآن
لانه عندي وريد.
الآن سلايد 5.
او ما يتحرك. اوكي خلينا نسوي ستوب شيرنج بسرعة، احوله افضل. اعطيني دقائق بس. دقائق بس دكتور سلمان بيتحول لبي دي اف. هو المشكله ملف 200 سلايد، ان شاء الله ما نكملها كلها، طويله عشان كده بيعلق، فبحوله بي دي اف.
ممتاز، الله يعطيك العافيه دكتور، شكرا جزيلا.
طيب واضحه الان؟
واضح دكتور.
طيب احاول اسويها فول سكرين. هذه اوكي، هذا بالنوع غريب عليه البي دي اف. هنا اوكي في
تحت.
يس فول سكرين. طيب تتحرك معانا ولا لا؟
واضح الان في سلايد رقم 6.
7 الان. طيب
الان 7 صحيح.
طيب هذا ستراكشر للميمز. هذه فلتر موجود داخل الجوالات. طبعا هذا النوع او هذا الديفايس الميمز مصنوعه من السيليكون. السيليكون فيه ميزه، فيها خصائص ميكانيكيه خاصه يصير لها فايبريشن بناء على الكهرباء اللي تجيله الاي سي سيجنال. فبالتالي اختلاف مقاس او السايز الدايمنشن الويدث واللينث حق هذا الفلتر يغير الفريكونسي. طيب يفيدنا في ايش؟ هذا بالجوالات، لما عندنا الجوال يحول من 5G الى 4G الى 3G الى مستقبلا الجيل السادس وغيره، لازم يكون عندنا اشاره معينه يرسلها الجوال، يكون في تصميم معين للريزونيتور. طبعا هذا جهاز سيمي كوندكتور يعتبر. هذا الشيء لازم يكون بالمايكروميتر مصنع، يصير سويتش بين الجهاز هذا والجهاز اللي جنبه الموجود، طبعا بتصميم معين انه يستقبل اشاره معينه. كيف يتم تصنيع هذا الجهاز؟ هذا اللي حنتكلم عنه اليوم بدون ما ادخل في ديتيل كيفيه عمله. هذا يحتاج يعني بروسيس معينه. حنتكلم عن الديبوزيشن، كيف نستخدم ماتيريالز معينه نسوي لها ديبوزيت ترسيب، والاتشنج كيف نزيل هذه المناطق سواء كان بالدراي او بالويت، زائد انه عمليه الليثوغرافي كيف نختار الاماكن بالمايكروميتر اللي نشيل منها هذه الاشكال. هذه برضو بعض الاجهزه زي البريشر سنسور وغيره، او الماس سنسور برضو بالمايكروميتر، يدخل في التطبيقات الطبيه، كيف بالدم نقدر نستكشف الامراض. هذه كلها يتم تصنيعها برضو عن طريق المايكروفابريكيشن. مايكروفابريكيشن ديفايس يتم تصنيعها برضو عن طريق خطوات التصنيع. هنا صورة للويت والدراي اتش، كيف يكون في تعقيد في الستركشر عندنا، نحتاج نستخدم فيه كيميكالز معينة حنتكلم عنها. واخيرا عندنا الاجهزه باشكال وتصاميم معقده بالمايكروميتر، كيف نقدر نوصل لها؟ ما نقدر نسويها غير عن طريق الليثوغرافي بالمايكروميتر سكيل. هذا البريشر سنسور موجود في تطبيقات مثل كفرات السيارات، كيف نقدر نعرف انه الضغط قل؟ جهاز صغير جدا يقدر يسوي سنس للبريشر، لازم يكون مجوف، يكون باك سايد ريليز، نقيس البريشر فيه. طبعا يعتبر الكتروميكانيكال ديفايس لانه في خصائص معينه. ممكن يكون في مواد بيزو الكتريك او بيزو ريسيستيف، هذه نتكلم عنها في محاضرات ثانيه، ولكن اليوم عمليات التصنيع، كيف هذه السنسورز الموجوده في التطبيقات يتم تصنيعها. طيب البروسيس بشكل عام لتصنيع اي حاجه، اي شيء يخص المايكرو فابريكيشن او السيمي كوندكتور يدخل في المايكرو فابريكيشن بروسيس. دائما يكون عندنا ويفر، ممكن تكون سيليكون، دايموند، سيليكون كاربايد، جاليوم ارسنايد، ايا كان، تمشي في عملية تصنيع. إيش هي العملية؟ بشكل عام يكون في أوكسيديشن، مو شرط تكون مرتبة هذا الترتيب. ثم يكون عندها ليثوغرافي، هنتكلم عنها بشكل شبه تفصيلي إنكم تكونوا إن شاء الله فاهمينه اليوم. ثم عندنا الإتشنج اللي هو الأكل أو إزالة الأطراف اللي نبغاها. ثم الدوبينج إذا احتجنا. الدوبينج هي عبارة عن مواد تكون غير موصلة نحولها لشبه موصلة، هنتكلم عنها. آخر شيء الميتال ديبوزيشن في الويفر، ثم الويفر تكون كاملة نسوي لها باكيجينج أو كاركترايزيشن. طيب انسايد الشيب نتكلم أول شيء عن الديبوزيشن. داخل أي شيب هذه تعتبر طبعا مواد عازلة حماية لها، لكن في الداخل في مواد. تشوف الماوس اللي تتحرك صحيح؟
صحيح دكتور، واضحة.
داخل المواد أو الشيبز الموجودة في مواد تتصنف تصنيفات كثيرة، ممكن تكون ميتال أو غيرها. طيب هذه التصنيفات مهمة جدا عندنا في مجال السيمي كوندكتور. تمام؟ المواد بشكل عام تصنيفاتها يا تكون موصلة، إذا واحد مسك شوكة أو سكينة حطها في الكهرباء حيتكهرب، أو تكون عازلة، إذا استحط خشبة ما يصير له شيء، أو شبه موصلة. هذه اللي تهمنا. في مواد ممكن بطبيعتها تكون شبه موصلة، في مواد نحن نخليها شبه موصلة في عملية الدوبينج، زي السيليكون. السيليكون عبارة عن رمل أساسه، نقدر نحوله لمادة شبه موصلة عن طريق عملية يسموها التطعيم بالعربي أو الدوبينج أو ديفيوجن أو لها أسامي كثيرة، أيون بلانتيشن وغيرها. نقدر نطعمها بمواد، يعني زي لو فكرتوا فيها بطريقة ممكن بسيطة جدا، زي بالطبخ الكيكة. لو عندنا كيكة وحطينا فوقها شاكلت ودوبناها حتدوب جوا، هذا اللي يصير عندنا. تدخل جوا بالكامل وتتغير خصائص السيليكون، تصير مادة شبه موصلة لها خصائص كهربائية أو ميكانيكية نحن نحتاجها. طبعا الجدول الدوري لو طلعنا عليه نلاقي تصنيفات المواد الموجودة في جدول الدوري حسب المادة ونوعها. يهمنا بشكل عام نحن المواد في جروبات مختلفة. ال 3-5 ماتيريال هي أحدث التقنيات، ما حتكلم عنها اليوم، في يمكن محاضرات أو تريننج متقدمة. مواد لها خصائص خاصة غالية جدا، تعتبر حاليا غالية لأنه طريقة تصنيعها مو زي السيليكون رخيص. لها طرق معينة بالديبوزيشن، ممكن أتكلم عنها اليوم بشكل بسيط، أو يمكن أخذتوها من المحاضرتين اليومين الماضية. لها خصائص قوية، يعني أهمها نقدر نقول في الفاست شارجينج باتري. ليش زمان كان عندنا البطاريات تنفجر في حالة الشحن؟ لو يقول لك شواحن أصلية مو أصلية، صحيح، صح إنه في شيء أصلي غير أصلي، لأنه السيليكون أو بعض المواد ما تتحمل الكرنت العالي، فما تسخن. إذا سخنت فتسبب حرائق. ولكن في مواد تستخدم جاليوم أرسنايد أو جاليوم نايترايد وغيرها ممكن تتحمل درجة حرارة عالية، يستخدموها في محطات الشحن الكهربائي تكون فاست شارجينج. هذا شيء يدخل في تطبيقات كثيرة، أهم التطبيقات المكلفة زي الإلكتريك كار بالسبيس أبليكيشن. بس بدأوا يستخدموها في السولار سيل، ولكن ما تسوى، يعني غالية جدا، يستخدموها فقط في محطات الفضاء. وعندنا مشاريع في المدينة بهذا الخصوص. طيب الماتيريال ديبوزيشن. الديبوزيشن في الماتيريال طبعا يكون غالبا بالنانو أو المايكروميتر سكيل، يعني جدا شيء بسيط، يعتبر مو زي الديبوزيشن العادي، زي لما نيجي عند جدار نبغى نطلي بويا أو نرسم، هذا يكون بالمليمتر. ولكن احنا نتكلم عن شيء أقل من كده بكثير، بالنانومتر أو المايكرومتر. ليش يهمنا؟ حنتكلم عنها لما نروح جزئية الترانزستور. يكون غالبا عندنا التصنيع على أو الدراسات اللي نسويها بالR&D على ويفر وجلاس في بعض التجارب، اللي مستقبلا ينضم بواحدة من التريننجز اللي هي فيها عملي حيتعامل معاها بنفسه في الغرف النقية. طيب عملية التصنيع هذه حتشوفوها كثير، تمر في هذه المراحل، تحفظوها دائما أو تعرفوها. اللي يعرفها يقدر يصنع أي شيء ممكن: فوتو ليثوغرافي، دوبينج، إتشينج، ديبوزيشن بين الويفر، تختلف ترتيبها على حسب الابليكيشن اللي تسويها. عندنا بكاكس أو باسم المملكة أكثر من غرف نقية، ولكن أكبرهم نقدر نقول اللي معترف فيها يعني إمكانيات كثيرة كاكس وكاوست. إيش يعني غرف نقية؟ يعني عندنا البيئة اللي حولنا فيها بارتيكلز بالآلاف، 100,000 200,000 300,000. الغرف النقية فيها أنظف من غرفة العمليات، يتراوح فيها عدد البارتيكلز الموجودة في الجو تنقص من 100 إلى 300,000، تنقص إلى أقل من 1000، توصل ل100 وبعض الأحيان في حالات 50 و30. فيها فلتر ينظف الهواء أول بأول، عشان يكون في لبس خاص أكثر من هذا. لما ندخل الغرف النقية أو في الشركات العالمية عندهم إجراءات معينة يدخلوه الغرف النقية، يصير عندهم يهتموا بعملية التصنيع. طيب الديبوزيشن بشكل عام يمشي بخطوات. طبعا عندنا هنا السيليكون مثلا على ويفر معينة فوقها سيليكون اوكسايد. طبعا الديبوزيشن يكون لهدف معين نبغى نسويه. في الحالة هنا مثلا عندنا سوينا اوكسايد، بعدها أزلناه من منطقة معينة حنتكلم عنها. ليش؟ بهدف معين، ولكن صارت عملية الديبوزيشن وبعدها اتشنج. تفاصيلها حنتكلم عنها لاحقا. طيب أجهزة الديبوزيشن، إيش الأجهزة الموجودة بشكل عام بالغرف النقية أو كتكنولوجي بشكل عام؟ تتفاوت كثير، ولكن أهمها نقدر نقول 3 أو 4 أنواع. الBVD Physical Vapor Deposition. الفيزيكال بشكل عام يستخدم نقدر نقول قوة فيزيائية أو نقول ايونز بمبارب تضرب السورس عندنا ويصير عملية تبخر معين حنتكلم عنها، أو كيميكال عن طريق غازات، أو ثيرمال حرارة. لو جينا عند الBVD عندنا أكثر من نوع. عندنا بشكل عام أكثر نوعين مشهورين عندنا أو معروفين، الإي بيم والسباترينج. أوكي، الإي بيم عندنا نسخن، عبارة عن ميلتينج، تصير عملية تسخين لميتال معين لدرجة حرارة الانصهار إلى ما يتبخر، وتطير جزيئاته على الويفر اللي نحتاجها كسامبل، ويتكون عليه يترسب بالنانوميتر الماتيريال اللي نبغاها. بتكون جولد، نيكل، كبر، أيا كان. بشكل عام يستخدم الميتال لأنه فيه توصل لدرجة الانصهار. بهذه الطريقة إذا عندنا سيليكون فوق أوكسايد نقدر نحط عليها ديبوزيشن بأماكن معينة الميتال اللي نحتاجه. طيب الحالة الثانية السباترينج. السباترينج يستخدم أكثر من التسخين، لا يستخدم الغازات. يصير عندنا تفاعل أيونات، نستخدم الأرجون كغاز مع بلازما، يتفاعلوا ويضربوا السطح حق التارجت اللي نبغاه، تطير فيه جزيئات اللي نبغاها للميتال إلى الويفر. السباترينج يتميز بميزة نقدر نستخدم فيه بعض المواد زي الدايلكتريك، زائد نقدر نسخن الشامبر لدرجة حرارة عالية. هذا الشيء نقدر نستفيد منه في بعض التطبيقات زي البيزو إلكتريك ماتيريال، إن نحول المادة لمادة كهرو ضغطية. يحتاج يكون الشامبر أو يكون في طريقة معينة لعملية الديبوزيشن تحتاج حرارة، فبالتالي ما نقدر نسويها إلا في السباترينج. طبعا لو جينا عند السباترينج من مزايا أو عيوب حسب الريسيرش، إنه يصير عندنا السايد وول تتغطى بالكامل، فيكون عندنا اتصال بالعكس كهربائي. في بعض الحالات نبغى يكون متصل ما يكون مقطوع. في حالة الإي بيم غالبا يكون عندنا فقط المنطقة السطحية هي السيلا ديبوزيشن. هذا فرق جوهري بينهم. الليزر بنفس الطريقة، ولكن نستخدم فيها الليزر في عملية ضرب التارجت ثم عملية الديبوزيشن. طيب الكيميكال فيبر ديبوزيشن عبارة عن استخدام غازات أو مواد كيميائية يصير فيها تفاعل، تتفاعل مع الويفر. من أشهر ال CVD tool عندنا ال ALD. طبعا هنا الغازات اللي تتفاعل في الابليكيشن حقتها سواء في الباتريز أو غيرها ككيميكال، تحتاج طبعا تفاصيل بمحاضرة خاصة في الديبوزيشن، ولكن نمشي عليها بشكل سريع. هنا عندنا ال ALD. ال ALD متميز بميزة وعيب. العيب إنه بطيء جدا، لأنه عندنا ما نتعامل بالنانوميتر ولا بالمايكروميتر. يعني مثال لو جينا هنا عند السباترينج نقدر نسوي جروث ل 40 نانوميتر بربع ساعة إلى نص ساعة. 40 إلى 50 أو يمكن توصل ل100 نانومتر. ولكن هناك 100 نانومتر، عندنا في الحالة هذه ALD إذا نبغى 100 نانومتر تاخذ منها يمكن يومين. عندنا عبارة عن سايكلز في ALD، تفاعل غازات، ما نسوي ديبوزيشن بالنانو، لا بالانكستروم. الانكستروم 1 من 10 أجزاء من النانومتر، والسايكل تقريبا تاخذ ممكن 10 إلى 20 ثانية. فنحن نتعامل هنا بالانكستروم، فبطيئة جدا ولكن دقيقة. فبالتطبيقات اللي نحتاجها في الترانزستور نحتاج الدقة. لما نروح لقيت نبغاها ب 3 ولا 10 نانومتر، أكثر طريقة دقيقة عندنا ال ALD، لأنه يعني يصير بالتفاعل الكيميائي أكثر من الفيزيكال، فبالتالي more controllable. الحالة الأخيرة لو عندنا ريسيرش يحتاج thick material بالمايكروميتر، طبعا صعب جدا نروح للإي بيم ولا للسباترينج ولا للALD، لأنه ممكن ياخذ ساعات أو أيام. طيب لو نبغى نسوي عملية ديبوزيشن ل very thick material، أفضل تطبيق لي هو الإلكترو بليتنج. طبعا الإلكترو بليتنج لي مواد كثيرة نقدر نسوي فيها بليتنج، أشهرها النيكل والكبر والجولد. زي المثال اللي بالاكسسوارات، لو تلاقوا أشياء مكتوب عليها بلاتينوم بليتد أو روثينيوم بليتد، وبعضها ستيل بليتد أو أيا كان، هذه بهذه الطريقة يحطوها في محلول كيميائي ويطلوها. نسويها عندنا في كاكس، يكون طلاء دقيق جدا بالمايكروميتر. السرعة تقريبا فيه إذا كان الجودة تهمنا في الأبحاث، كل دقيقة 6 مايكروميتر، لا عفوا كل 6 دقائق 1 مايكروميتر. ف10 ساعة نسوي فيها 6 مايكروميتر، بيكون بجودة عالية. إذا ما يهمنا الجودة إنها تكون الرفنس حقها عالي، نقدر نسويها أسرع من كده. عبارة عن طريقتها 1 مايكروميتر each 6 minutes، هذه الجودة العالية. هذه تجربتي الشخصية إنه يعتبر جودة عالية. يعني نسوي DC باور سبلاي، نسوي أبلاي كرنت، يكون عندنا الويفر والتارجت النيكل، وعن طريق فلتر نسخنها لدرجة حرارة بين 40 و60، ونسوي عملية الديبوزيشن. هذه مثال على نيكل بليتد فيري ثيك ماتيريال، هي توصل تقريبا ل 12 مايكروميتر الثيكنس، سموث جدا. هذه في حالة تحكمنا في الجودة، إنه شلنا البيتنج وغيرها عن طريق الريسيبي. كل مادة كيميائية نستخدمها لهدف معين. أهم شيء عندنا كوندكتيفيتي، نتأكد إنه ما فيها بابلز أو عيوب بالسيرفيس. طيب هذه جزئية الديبوزيشن في عمليات التصنيع لأجهزة المايكرو إلكترونيكس. طيب نيجي الآن عند الليثوغرافي. ترانزستور كثير منكم درسوه. ترانزستور باختصار هو نقول سوى ثورة بالصناعة لما اخترعوه قبل تقريبا 100 سنة وأكثر، 60 سنة نقدر نقول. لما هو عبارة عن موجود في الجوالات وفي الكمبيوترات بعدد كبير، إذا نقول بالملايين أو المليارات، ويسمح بمرور التيار أو يمنعه، زي ما يصير معنا بحنفية الموية، يسمح أو يمنع حسب الحاجة. بكل أمر كل ديجيت في السيجنالز يكون عندنا 1 ترانزستور. أول جهاز صنعوه عام 1947 كان ترانزستور بهذا الحجم كبير جدا، ولكن كان يدي أمر واحد on or off، زي سويتش المكيف أو اللمبة يعطي on or off. بعدها بدأوا يصنعوه بأجهزة بمقاسات صغيرة، بس still جهاز واحد قيمة يعني السايز حقه قريب من الأطفر، ما زال كبير. طيب لو يبغوا كمبيوتر فيه أوامر كثيرة، كيف حيربطوها كلها مع بعض؟ صعب طبعا يكون عندنا بهذه الطريقة. لما بعدها ابتكروا طريقة الليثوغرافي أو التقنية، كيف يقدروا يصنعوها عن طريق التصميم، زي ما محاضرات تقنيات التصميم ندرسها بالسيمي كوندكتور، كيف نقدر نصممه إنه يكون عندنا مو ملايين مليارات ترانزستور بهذا الحجم. ما يقدر يسويها بدون الليثوغرافي. الشركات العالمية تتنافس وجودتها دائما بالليثوغرافي. الغرف النقية عندنا أول سؤال يسألوه في أي غرف نقية يسألونه هو كم الفيتشر سايز اللي تدخلوها او تقدروا توصلوا لها. عندنا في الغرف النقيه نقدر نوصل قريبا 300 نانومتر. الشركات العالميه وصلوا الى 7 و8 نانومتر، هذا في مرحله التصنيع. في الار ان دي انف اللي واصلينه. ليش؟ لانه عندنا التقنيات اللي حنتكلم عنها في السلايدات تعتمد دائما على السايز للترانزستور، لان كل ما ينقص السايز او التقنيه بالليثوغرافي يزيد عندنا عدد الترانزستور. طيب ايش هو الليثوغرافي؟ هو طباعه بعض يسميها حجريه، يقول ضوئيه. كيف نقدر نكرر عدد الرسومات او الصور ببترن واحد باكثر من طريقه. نفس المثال ترى الموجود عنده هي التصوير، اللي لحق على التصوير زمان لما كانوا يسووا عمليه يسموه التحميض نفس اللي عندنا الديفلوبر او الديفلوبمنت، هذا يسميه التحميض. كان عندنا افلام نغطيها ما يصير لها تحميض الا في غرف مغلقه عشان الضوء ما ياثر عليها، لانه فوتوليثوغرافي يتاثر مواد خاصه تتاثر بالضوء، اذا جاء الضوء في اماكن معينه يغير خصائصها الكيميائيه. فهذا اللي نحتاجه في عمليه الليثوغرافي، هو عباره عن نستخدم مواد حساسه للضوء. طيب عندنا مور لو هو بدأ ب أو ابتكر ومور قال القانون، قال إنه عدد الترانزستور يتضاعف كل سنتين، يقول لك كوست. تقريبا ماشيين بنفس الطريقة من عام، بدينا من عام من يوم 1947 اكتشف كل سنتين يتضاعف الرقم. طيب نحسبها هل ممكن ولا لا؟ نحن نوصل من 1 إلى 1000 كل 20 سنة. عندنا 1 بعدين 2 بعدين 4 16 32 64 تقريبا كل 8 سنوات نوصل للرقم. فالحين تقريبا 30 40 سنة وصلنا. لو تشوف التقنية بدينا بال فلوبي ديسك بالكيلو هرتز. لو شفنا التقنية هذه بالميموريز الموجودة، ثم انتقلنا للميجا ثم الجيجا، لأن هارد ديسك الموجود بالتيرا هرتز أو بالتيرا يعتبر بالتيرا نعم. فوصل التيرا بايت، فبالتالي هذا تضاعف عدد الميموري، عدد الترانزستور الموجودة فيه للتخزين. احنا ماشيين بهذا النسق تقريبا. طيب عدد ترانزستور تزيد كل ما يصغر نقدر نقول الجيت، المساحة هي بالنانومتر، وصلوا تقريبا إلى 5 نانومتر. المشكلة الأجهزة، كل تقنية نسويها، يعني مثلا ناخذ مثال الدي ان اي. الدي ان اي كان في جرائم تصير، ما يعرفوا الدي ان اي، ما يعرفوا مين سواها، ما كان في اكتشاف اسمه الدي ان اي لين ما اخترعوا جهاز الاي سي ام. الاي سي ام حنتكلم عنه وموجود في جزء الكاركترايزيشن. نقدر ندخل بالمايكروميتر نشوف الجزيئات المواد. لما وصلوا لهذه التقنيه يقدروا يشوفوا ما بداخل الدم. في كثير جرائم انحلت، عرفوا طابق الدي ان اي كان مخزنه، عينات دم وغيرها. يعني نحتاج نحن الاجهزه التولز التقنيه اللي تساعد في عمليه التصنيع. ففي حد معين عندنا ليميت لما ننزل النانوميتر. فالشركات الآن وصلوا لليميت جدا صعب، تسارع كبير في النزول، حتى يمكن بدأوا يتجاوزوا قانون مور. فبالتالي بدأوا يفكروا باستراكشر جديد، بدل ما يروحوا للتصغير يروحوا 3D أو يستخدموا مواد أخرى، يروحوا مواد اللي تكلمنا عنها اللي لها خصائص معينة، سواء قالوا ميرسنايد أو نايترايد أو غيرها 3-5 ماتيريال. فهذه من التقنيات اللي ممكن يدخلوا الليثوغرافي، ولكن طبعا هذه إيش عيوبها؟ التكلفة، التعقيد. كنا زمان بالليثوغرافي نصنع فقط هذا الجزء، الآن بدينا نبني 3D. هذه جزئية كلها تحتاج more lithography steps. كل ما نسوي more lithography steps تزيد الأخطاء، فأخطاء الفابريكيشن تؤدي إلى تقليل الجودة، تقليل السرعة. هذه من عيوبها. طيب لما نتكلم عن الفيتشرز أو التقنيات، كل تقنية لها تطبيقات. يعني مثلا نيجي عند الأوتوميتيف ما يحتاج ننزل لهذه التقنية الغالية بالنانوميتر، لأنه السايز ما يهمنا. سيارات البريشر سنسور مو لازم يكون صغير، لحد معين عادي it can fit. نفس الشيء في السمارت فونز مهم طبعا. عندنا الجي بي اس وغيرها، فلاش ميموري. مو لازم ندخل في نغلي سعره وننزل في التقنية. لكن يجي عندك جوالات يهمنا نشيله معنا كل يوم، يهمنا التقنية تكون صغيرة عشان يزود السرعة ويقل السايز. الشاشات وغيرها مو لازم يكون عندنا في هذه الرينج تقريبا. كل ما ننقص كل ما تزيد التكلفة، يزيد تكلفة الريسيرش، يزيد تكلفة التصنيع، تزيد خطوات التصنيع. طيب ناخذ مثال سريع. عندنا الابلز، الايفون 12 كان يستخدم تقنية 7 نانومتر، كان عندنا 7 بليون ترانزستور بتكلفة معينة. طيب ايش الحل؟ عندهم حل، يا يسوي الشرينك للسايز اصغر من كده، او يقللوا العدد الحجم، فبالتالي حيزيد العدد. اذا زاد العدد 7 مليون ل مثلا 14، راحوا من ايفون 12 ل 14، يقدروا يصغروا بس يزودوا العدد احسن. اذا زاد العدد تزيد السرعه وتقل التكلفه. هذا موجود تلاقوه في موقع ابل على التكلفه كيف تقل او تزيد، بالعكس التكلفه ويقل السايز ويزيد عدد الترانزستور الموجوده. طيب نبدا الان جزء في عمليه التصنيع. عندنا الشيب هذه عباره عن طبقات، كيف نقدر نوصلها بهذا الشكل؟ كيف يكون عندنا سبستريت، نبني سيمي كوندكتور ماتيريالز ايا كانت، نحط دايلكتريك، نحط ميتال، نحط جيت. هذه تحتاج عمليه ليثوغرافي. او في فيديو هنا اذا يعرض، خليني اشوف. don't think so. اوكي، الويفر كيف تتصنع؟ تصنع اصلا من الرمل، يتم تسخينه ينصهر لدرجه حراره عاليه. او هذا بي دي اف، اوكي مو مهم. ثم يتم تقسيمها الى شرائح بالمليمتر، يصير عندنا ويفر، سيليكون ويفر، نصنع عليها كل شيء نبغاه عن طريق عمليه الليثوغرافي. الليثوغرافي بشكل عام زي الكيتشن، طبقات نبنيها، ولكن ما نقدر نتحكم فيها بيدنا، مستحيل بهذه الطريقه لانها صغيره ولا ترى في العين. نحتاج نستخدم اجهزه تول تصميم معين، ننزل بالمايكروميتر، ما نقدر نرسم اي رسمه نبغاها، لازم يكون عندنا تصميم معين بالمايكروميتر. ادوات تولز زي الموجوده عندنا في الغرف النقليه. بشكل عام ينقسم لقسمين الليثوغرافي. دائما اي الليثوغرافي بروسيس يتبعها واحد من اثنين: يا عمليه اتشنج، قالب نزيل اشكال معينه زي هنا عندنا، او بناء ديبوزيشن. ما يخرج اي ليثوغرافي بروسيس يتبعها واحده من هذه الخطوات. نفس فكره البينتينج نستخدم الماده، نقدر نقول ساكريفيشال لاير، ماده مؤقته عشان نبني او نسوي بينت لمكان معين ثم نزيله. نفس الفكره نسويها بالليثوغرافي، نحط ماده الفوتوريزيست في اماكن معينه بحيث انه نسوي ديبوزيشن للمنطقه اللي نبغاها او اتشنج للمنطقه اللي ما نبغاها. طيب الليثوغرافي بشكل عام هو يستخدم تول فيها ضوء، تمر على فوتو ماسك يتم تصميمه، يمر الضوء من اماكن معينه يروح للويفر اللي فيها ماده حساسه للضوء. الضوء حيجي لاماكن معينه تتغير خصائصها الكيميائيه، فبالتالي حيكون عندنا ايش؟ حيكون عندنا ديفايسز تم تصنيعها. خليني اروح الفيديو لو شفتوه مفيد. دقيقه. الظاهر عندكم الشاشه دكتور سلمان؟ الظاهر الفيديو دكتور سلمان او واحد يسمعني؟ شوف لو في شات. يس تمام، يعني ظاهر اذا افترضنا انه تمام، حاطين رافعين يدهم. اوكي طيب، الفيديو مهم، لازم نرجع للباوربوينت. هو عبارة عن ساند يتم تصنيع الويفرز منها. كيف الساند يتاخذ؟ يتم تسخينه لدرجة حرارة عالية، بعدها يتحط في قالب يتكون بشكل معين، طبعا يكون بخصائص معينة، يكون بيور دائما. طبعا هذا اللي يعتبر غير موصل، نحوله نحن لشبه موصل. بعدها يتم تقطيعه إلى ويفرز. الويفر واحدة تتباع تقريبا ب$10 إذا كانت سيليكون عادية. هذه الويفر تاخذها المؤسسات البحثية والمصانع، يوضع عليها فوتوريزيست، ثم يصير عملية التصنيع. هذه الليثوغرافي تتعرض للضوء أكثر من مرة. طبعا هذه الخطوة تتكرر كثير، يتبني طبقات ويصير لها اتش لطبقات. هذه الويفر يطلع منها معالجات كثيرة، من ضمنها بشركة انتل. لو سوينا زوم ان حيطلع عندنا بروسيسورز، يصير بناء. هذه خطوات كثيرة للثوغرافي، يتبعها اتشنج وديبوزيشن.
معذرة دكتور عدنان،
تفضل.
لكن الشاشة عندنا طالع سلايد أبيض بس.
اوكي، ما يطلع عندكم الفيديو. والآن
الحين ظهر.
طيب، هنا الساند يتحول لقالب بشكل معين، بعدها يصير له عملية اتشنج، أو نقدر نقول سلايدنج، تتقطع لويفر معينة تتباع للشركات والمصانع. بعدها يصير عملية الليثوغرافي اللي نتكلم عنها اليوم. طبعا خطوات كثير للليثوغرافي. لو سوينا زوم ان لل الويفر اللي فيها عدد كبير من المعالجات، توصل في حالات ألوف أو الملايين، يصير فيها بناء. هذه كلها معالج في طبقات كثيرة، يتم بنائها في عمليات ليثوغرافي وديبوزيشن. يصير عندنا معالج، هذه من شركة انتل. بعدها يصير له عملية دايسنج، تطلع من عندنا من كل ويفر مئات أو آلاف الويفرز، مئات تقريبا في حالة انتل، يطلع منها معالج. هذا المعالج يكون يستخدم في الجوالات أو الكمبيوترات، ويتباع طبعا لنا. كلها تمشي في عملية الليثوغرافي عن طريق مصانع بنفس الخطوات اللي شفتوها بالفيديو. طيب، نرجع للبي دي اف. طيب، واضحة عندكم السلايد الآن بي دي اف؟ هذه نفس الطريقة. الليثوغرافي ينقسم أنواع. النوع اللي عندنا في كلين روم، الويفر تروح على الضوء يروح على كامل الويفر. في حالات معينة عند الشركات ينزلوا بالنانوميتر، عندهم جهاز يسموه الستيبر، ستيب باي ستيب، يروح لمنطقة منطقة. طبعا هذه جودته عالية ومكلف جدا، قيمته بالملايين. بنحاول نوفره عندنا في كاكس، ولكن تكلفته عالية. هنوفره بالمستقبل إن شاء الله. طيب، في حالة الليثوغرافي تول أو اللي نستخدم الماسك اللاينر، نحتاج فوتو ماسك. الفوتو ماسك يتم تصميمه إنه يمر من خلاله الضوء في أماكن معينة. في عندنا نوعين، نوع كلير فيلد ودارك فيلد. دارك فيلد نفس الشيء، ولكن صنفوه بهذه الطريقة إنه الضوء يمر مناطق صغيرة أو مناطق كبيرة، بس بالأخير هو يؤدي نفس الغرض. هذا مثال على الفوتو ماسك اللي يمر منه الضوء، عبارة عن مواد مصنوعة جلاس، فيه ميتال في أماكن معينة، كروم، تعكس الضوء، تمنعه يمر من خلالها. بهذه الطريقة يمر الضوء في أماكن معينة فقط. الماسك يسمح لمرور الضوء، يمر على الويفر يكون فيها مادة حساسة للضوء. أي منطقة تتعرض للضوء تتغير خصائصها الكيميائية. هذه مثال على فوتو ماسك يعتبر كلير فيلد. الضوء يمر من أغلب الأماكن ويحجب فقط في الأماكن السوداء. طيب، مكونات أو الليثوغرافي نحتاج أهم مادة عندنا هي الفوتو ريزيست. هي مادة حساسة للضوء، تتغير خصائصها عند تعرضها للضوء. طبعا ايش الخطوات اللي نمشي فيها؟ هي عمليه وضع الفوتوريزيست في جهاز سكوتنج، يمكن مر عليكم في بعض الجامعات زي جامعه جده عندهم منه. بعد يصير اكسبوجر، بعدها الديفلوبينج زي التحميض اللي قلت لكم عليه، تحميض الافلام. اللي حيصير في عمليه التحميض هي الاماكن اللي تعرضت للضوء تغيرت خصائصها الكيميائيه، يتم ازاله او بقاء الفوتوريزيست منها فيطلع الشكل اللي نحن نبغاه. هذا جهاز سبينر كوتر نسميه، نحط فيه الويفر وتدور زي فكره نشافه الملابس، تدور بسرعه عاليه، كل ما تزيد السرعه يقل عندنا الثيكنس للفوتوريزيست. طبعا احنا الفوتوريزيست نحطه يختلف حسب التطبيقات الابلكيشن. في حالات نبغاه يكون ثيك نقلل سرعه الدوران، في حالات نبغاه يكون ثين، لما نروح للمايكروميتر سكيل او النانوميتر سكيل يكون ثين، يعتبر الخطوه اللي بعدها تتبعها تكون نحتاج فيها مايكرو سكيل. فهذا يعتمد على سرعه الدوران في السبين كوتنج. طيب ما حدخل ديتيل في الليثوغرافي لانها محاضره عامه، ولكن الثيكنس اللي نحتاجها بالفوتوريزيست تعتمد بالداتا شيت نلقاها اونلاين حسب سرعه الدوران. يكون عندنا الثيكنس حق الفوتوريزيست بهذه الطريقه. طيب هذا جهاز الماسك الاينر موجود في كثير جامعات، في الغرف النقيه لازم يكون في منطقه نسميها المنطقه الصفراء. هذه المنطقه الضوء اللي فيها الويف لينث ما ياثر على الفوتوريزيست اللي يتم تصنيعه. مجرد ما ناخذ الفوتوريزيست برا الغرفه هذه يتعرض للضوء يصير بالكامل يصير يوزلس بالكامل، يتعرض للضوء بالكامل حيتم ازالته ما يستفاد منه. لانه ليش؟ لانه عندنا زي ما قلت لكم الليثوغرافي بروسيس الضوء يمر في اماكن معينه هي اللي يتم ازاله بالعمليه الديفلوبمنت الفوتوريزيست من الاماكن. هنا طبعا تعرضت هذه المنطقه للضوء، كان عندنا بوزيتيف فوتوريزيست، ازيل الفوتوريزيست من هذه المنطقه. طيب هنا عندنا مثال لبروسيس صار فيه عمليه اتشنج هتكلم عنها. كان عندنا سيليكون ويفر حطينا عليها جولد everywhere، بعد استخدمنا فوتو ماسك غطينا بالفوتوريزيست اماكن معينه بالمايكروميتر صغيره، سوينا الديفلوبمنت هذه الاماكن راح منها الفوتوريزيست. بعدها سوينا اتشنج حطيناه في ماده كيميائيه، هذه المناطق كانت محميه، هذه المناطق أزيل الجولد والكروم منها، بقي عندنا هذه الاماكن فقط فوق السيليكون. طيب عمليات التصنيع فيها مشاكل تصير كل ما نزود عمليه الستبس الموجوده يبدا يصير عندنا اخطاء في التصنيع. مس الاينمنت نسميها مس الاينمنت، بدل ما تكون سنتر حرفت اللي تخصصهم كهرباء او فيزيكس يعرفوا انه هذه عباره عن شورت سيركت، بوزيتيف مع نيجاتيف، الفلتر هنا يعتبر شورتج، مقاومه تطلع فيه زيرو يعني كوندكتيف ما يدي سيجنال. هذه تصير اخطاء التصنيع باسباب كثيره، اهمها الستريس، الويفر تبدا تغير تتحدب شكلها زي الستيك يصير بهذه الطريقه، ففي بعض الاماكن اطراف الويفر تتلف. عشان كذا يستخدم الشركات العالميه الستيبر، يروحوا هنا منطقه يسووا لها يتاكدوا انها الايند. طب ايش العيوب هذه يعتبر يا اما تقل الجوده، في هذه الحاله مو شورت، تقل جوده المعالج او انه تلفه بالكامل. معلومه تلاقوها بشركه انتل موجوده احتمال، او انه تلقوها اونلاين. ليش عندنا معالجات i7 i5 i3؟ ليش شركه انتل ما تصنع فقط معالجات i7 i5 و i3؟ يعتبر من اخطاء التصنيع، تجاوزت الجوده، قلت سرعتها، فبالتالي يتم بيعها كi5. تجي اخطاء معينه في التصنيع سببت قله الجوده، فبالتالي بدل ما يتلفوها يبيعوها في توالف عندهم، ولكن اي شيء ما يتجاوز الستاندرد معين او اللي يحتاجوه يباع كi5 او i3. طيب عندنا نوعين من الفوتوريزيست. لما يتعرض الضوء للفوتوريزيست بعض الريسيرشر يبغوا يزيلوا هذه المنطقه، بعضهم بالعكس يبغوا يبقوا هذه المنطقه، بعضهم بغلط اخطاوا بدل ما يخلوا الفوتو ماسك يحمي هذه المنطقه يحمي هذه بالغلط، او بدل ما هذه يحمي هذه. بالتالي عندنا بوزيتيف ونيجاتيف فوتوريزيست. البوزيتيف فوتوريزيست اي منطقه تتعرض للضوء تزال، whatever get exposed will be removed. اي منطقه اي شيء يتعرض كمنطقة للضوء حيتم إزالة الفوتوريزيست منها بالديفلوبمنت، حينتج عندنا هذا الشكل. النيجاتيف بالعكس whatever gets exposed will stay، أي منطقة تتعرض للضوء حتقوى حتبقى. فعندنا خصائص في الجامعات يستخدموا بوزيتيف أو نيجاتيف فوتوريزيست، حسب التطبيق نحتاج هذا أو هذا. طبعا ليهم مزايا ثانية، مثلا في الإتشنج ينصح في النيجاتيف فوتوريزيست، ننزل في النانو سكيل ما نقدر نستخدم إلا بوزيتيف لأنه خفيف، هنا يعتبر كثيف، يعتبر كثافته عالية، لازم نخففه على أساس يوصل للنانو سكيل. هذا مثال على البوزيتيف والنيجاتيف فوتوريزيست. إذا عندنا نسوي هذا الشكل وعندنا هذا الفوتو ماسك، نحتاج يكون عندنا بوزيتيف، لأن هذه المنطقة حتتعرض للضوء حيتم إزالتها. إذا نبغى نستخدم عندنا هذا الفوتو ماسك بالعكس، نبغى هذا الشكل، حنستخدم نيجاتيف فوتوريزيست. طيب زي ما قلت لكم أي عملية ليثوغرافي يتبعها دائما غالبا واحد من 2 بروسيس، يا إما ديبوزيشن أو إتشنج. الإتشنج مثال لو عندنا أوكسايد نبغى نسويه بهذا الشكل، هنسوي ديبوزيشن أول شيء أو الأوكسايديشن لكامل المنطقة. لما نحط الليثوغرافي نختار مكان معين بالليثوغرافي يزال، بعدها نسوي عملية الإتشنج سواء dry or wet etch، يطلع عندنا هذا الشكل. بالمقابل الديبوزيشن لو نبغى نوصل للميتال في هذا المكان، أول شيء حيكون عندنا فوتوريزيست، حنزيل الفوتوريزيست بالليثوغرافي من هذا المكان، بعدها يتم عملية الديبوزيشن بالإي بيم أو السباترينج، بعدها نشيل الفوتوريزيست لأنه هنا يعتبر قاعد فوق فوتوريزيست، هنا قاعد فوق الويفر، لما نزيله حيطير، حيصير عندنا هذه المنطقة فقط فوتوريزيست الميتال. فدائما أي فوتوريزيست أو الليثوغرافي بروسيس نحط فيها فوتوريزيست يكون لواحد من هدفين بالغالب، يا ديبوزيشن يا إتشنج، على أساس نبني المعالج في الطبقات الكبيرة، أو أيا كان السيمي كوندكتور ديفايس في طبقات لايرز كثيرة. طبعا هذه 1 لاير، البروسيسور والرامز وغيرها فيها طبقات كثيرة، هذه واحدة منها. هذا ملخص على الخطوات اللي تصير دائما في الليثوغرافي ما بين تنظيف الويفر، الكوتينج، وضع الفوتوريزيست، تعرضه للضوء، ثم بعدها البروسيس اللي بعدها ايا كانت سواء ديبوزيشن او اتشنج. البوزيتيف والنيجاتيف فوتوريزيست كل واحد له خصائصه الكيمياء المميزه، اهمها دائما قوه التحمل. الكوست غالبا ريسيرشر ما يهم كثير، يهم عندنا قوه التحمل. في الويت دائما النيجاتيف اقوى، بس في السمول فيتشر سايز ما نقدر نروح غير للبوزيتيف، النيجاتيف سميك جدا ما ينفع. هذا مثال ما حدخل فيه بتفاصيل على CMOS device، لو تلاحظوا كيف معقد جدا الستراكشر. Each one of these need to go through one lithography process، one lithography step لكل خطوة من هذه الخطوات. يعني كمثال عندنا هنا نحتاج نسوي اوكسايد، بعدها فوتوريزيست علشان فقط نتعرض للضوء، عشان فقط نفتح هذه المنطقة، بعدها حنسوي دوبينج أو امبلانتيشن اللي هو التطعيم، إنه نحول هذه المادة المنطقة لشبه موصلة سيمي كوندكتور، هي حاليا عادية يبقى نسويها شبه موصلة تحول لسيمي كوندكتور ديفايس، نسوي لها دوبينج أو ايون امبلانتيشن. هذه 1 خطوة. فإيماجن لما نوصل لهذه الخطوات how many lithography step نحتاج. هذه واحدة، ونحتاج هنا نفس الشيء نحط هنا عندنا الN برضو للجيت، نحط آخر شيء عندنا الميتال البوليسيليكون اللي هو يعتبر الميتال. فنحتاج خطوات كثيرة ما تقل عن 5 إلى 6 خطوات عشان نوصل لهذا الستراكشر. كلها تنعاد ليثوغرافي ثم إتشنج ليثوغرافي ديبوزيشن ليثوغرافي دوبينج. الليثوغرافي هو الأساس عشان نقدر نوصل ل جيت بالنانوميتر أو مساحة ما بين الترانزستور كجيت بالنانوميتر، نحتاج يكون عندنا advanced lithography tool تقدر توصل للنانوميتر. طيب آخر جزئية عندنا اليوم هي الإتشنج. الإتشنج هي النحت أو الإزالة. هنا بالمايكروميتر نقدر نسويها، بس كيف بالنانوميتر؟ بالنانومتر ما نقدر بدون الليثوغرافي تول. يكون عندنا تصميم لمنطقة معينة نزيلها بالمايكرومتر أو النانومتر 3 4 10 20 60 نانومتر، يتم استخدام مادة كيميائية أو غازات إن نزيلها من هذه المنطقة. طيب الاتشنج بروسيس هو استخدام البلازما في الدراي اتش or some chemical solution to remove unwanted area film. يزيله من أماكن نحن ما نبغاها بالمايكرومتر، سواء باستخدام الغازات أو البلازما أو الويت كيميكال لإزالتها. طبعا في حالة الدراي والويت اتش نحتاج، ففي حالة الاتش نحتاج واحدة من حالتين، الدراي أو الويت اتش. طبعا الويت اتش شيبر أسهل، بس فيه مشكلة hard to control، صعب جدا نتحكم فيه، لأن نتعامل نحن مع ووتر، لما نحط يدنا في موية ونشيلها حتبقى ويت، أنا أي تفاعل حيستمر. لكن لما نتعامل مع بلازما الضوء ضغطة زر يوقف التفاعل. ففي it's hard to control a wet etch، ولكن أسرع ونحتاجه sometime في مواد مثلا زي الأكسايد، لو نبغاه من شيء يسميه ايزوتروبيك صعب نوصل له إلا عن طريق الويت اتش. ففي حالات معينة نحتاج فيها الويت اتش حتى لو ما نقدر نتحكم. في حالات برضو صعوبة تكلفة لازم نروح للويت اتش. طيب في أمور لازم ننتبه ليها فاكتورز وقت نسوي الاتش. أهم شيء عندنا هو الاتش ريت. لو نبي نسوي اتش لمناطق معينة لازم نعرف كم الاتشنج ريت، كم الغاز أو الكيميكال أو البلازما خلال كم تقدر تشيل هذه المنطقة، لأنه لو زودناها حتتلف، لو أقل حنضطر نعيدها. هذه مهم جدا. الخطوة الثانية هي شيء نسميه البروتكتيف لاير، اللي هي الفوتو ماسك أو الماسك لاير، مو الفوتو ماسك، الماسك لاير حنتكلم عنها، اللي تحمي على أساس لو جينا مثلا لو عندنا ناخذ مثال، لو عندنا لوح شوكولاتة نبغى الشوكولاتة نبغى ندوبه في مكان معين، هل نقدر نجيبه زي ما هو نعرضه للنار؟ حيدوب بالكامل. لكن لو حميناه في أماكن معينة زي الشمعة تكون جوا كاسة تكون محمية، نشغلها في أماكن معينة. فهنا نحتاج نفس الشيء في الإتشنج، ماسك يحميه، لازم نتأكد إنه ماسك هذا أصلا يتحمل الغاز أو المادة الكيميائية. طيب الفيجر اوف ميريتس، الأشياء المهمة عندنا في عملية الإتشنج هي الإتش ريت، سرعة الإتشنج، يونيفورميتي، هل هو يونيفورم ولا لا، هل يروح لكل الأماكن بنفس الوقت أو لا، والسلكتيفيتي نتكلم عنه اللي هي الماسك، نتأكد إنه لو حطينا حماية ما تتأثر، تكون صلبة. وآخر شيء أوكي شيء اسمه أنايزوتروبيك وأيزوتروبيك، هنشوفها الآن اللي هي الأندركات نقدر نسميه. طيب ناخذ مثال عندنا هنا، استخدمنا كروم ماسك، نبغى نشيل السيليكون. الكروم صلب قوي يتحمل غاز ال SF6. لو جينا هنا نبغى نسوي اتش لهذه المنطقة واستخدمنا فوتو ريزيست ما يتحمل، ضعيف. لكن لو استخدمنا كروم يتصدى للغاز والبلازما، إذا نحفر all the way بس نخلص نزيله. لكن لو استخدمنا عندنا سيليكون فوق سيليكون حيزال بالكامل، هم الاثنين يتأثروا بالغازات. الكروم نتأكد عندنا سيلكتيفيتي، ما يتأثر بالغاز أو المادة اللي يتم تعريضها ليه، ففقط يتعرض هذه المنطقة المكشوفة، هذه المنطقة قوية تكون أو تتناقص بالتدريج، يكون عندها الريشيو 1 to 10 مثلا بهذه الطريقة. في عملية الإتشنج وعندنا الفوتو ريزيست أو المادة الماسك يتحمل. طيب الفوتو ريزيست بشكل عام لو أخذنا مثال، عندنا ديبوزيتد ماتيريال مثلا أوكسايد أو غيرها، وعندنا فوتو ريزيست حميناه. لما نستخدم الإتش ماسك أو الماسك أوبننج أريا نتأكد إنه يحمي طبعا، ثم نستخدم الويت أور الدراي كيميكال. هنا عندنا حاجة اسمها ايزوتروبيك، هذه تتم غالبا في الغازات. يعني احنا نزيل هذه المنطقة بشكل متساوي، ما ننزل للأندركت الانايزوتروبيك. هذه غالبا نسويها بالغازات، لأن يجي الكيميكال ما يقدر يتحكم، حيبدأ يزيل من الجوانب. فهذا الفرق بين الدراي والويت اتش بشكل عام. طبعا الماسك لو ما كان صلب وبدأ يفك من الأطراف، هنلاحظ إنه يختلف عندنا الحماية في الصور، يبدأ يزال، يعني عندنا مشكلة في الادهيجن يصير. طبعا تأثر في الستريس حق الماسك، يبدأ يفك من الأطراف ويزيل الحماية. هذه المنطقة كلها حتم إزالتها، تتأثر. هذه نتجاوز عنها هنا. طيب الويت اتشن تعتبر ممتازة لأشياء كثيرة، ولكن عيبها طبعا الكنترولابيلتي. لما جينا هنا بنزيل هذه المنطقة بمقدار معين، صعب نتحكم فيها بالثواني، لأنه المشكلة لما نجي لو دخل الكيميكال عندنا في هذه المنطقة، عشان نزيلها نحتاج ثواني، هذه الثواني تزيد التآكل، فصعب نتحكم فيها. الغازات غير، الغازات في شامبر تحت، جوا شامبر في فاكيوم تسحب كل الغازات. هذه من عيوبه أكثر شيء عندنا طبعا الكنترولابيلتي. طبعا مزايا إنه هو inexpensive، غير مكلف، إذا نستخدم 10 20 ويفر بنفس الوقت. الاتش ريت فاست، في حالات معينة نبغاه يكون سريع فاست. الدراي اتش يعتبر جدا بطيء، يعتبر بطيء بشكل كبير، زائد انه غالي تكلفته. نستخدم 1 ويفر بير تايم، ولكن من عيوبه التحكم. طيب هذا مثال على الايزوتروبيك والانا ايزوتروبيك. في تطبيقات نحتاج فيها ايزوتروبيك اونلي زي الرامز، في تطبيقات ما نقدر نستخدم فيها غير او نحتاج الانا ايزوتروبيك. طبعا اوكي نتجاوز عنه. هذه المواد السيليكون. طيب طبعا الويت اتش مهم بالسيليكون، في تطبيقات السيليكون، لانه السيليكون فيه مزايا. الكريستاليزيشن او ترتيب الجزيئات تختلف حسب طبيعه السيليكون او زي ما نسويه. ممكن يكون عندنا اتش بطريقه زي ما شفنا في بدايه المحاضره الصور، يكون في انجلز معينه، ففيه ميزه هي انه نقدر نتحكم فيه بالويت اتش بانجل معينه باستخدام الكي او اتش، انه يصير عندنا تشكيل معين. ولكن لو جينا نسوي ان ايزوتروبيك نحتاج فيزيكال اتشنج، وهذه ميزه موجوده زي الار اي او الدي ار اي، الديب رياكتيف ايون اتش. وطبعا اكتشافه سوى طفره في الرامات. الرامات تحتاج بيلرز، عواميد، طريقه تصنيعها للسيليكون، فنقدر نسويها بسهوله عن طريق الدراي اتش الار اي بهذه الطريقه. ما يسمى البوش بروسيس، ما حدخل عليها في ديتيل. طيب طبعا بحاله الار اي اي او الدراي اتش، كل ماده لها غازات معينه تزيلها. الاكسيد ميثان او الميثان، الاس اف 6 يشيل السيليكون، الالمنيوم يتشال بالكلورين، الاورجانيك بالاوتو زي الفوتوريزيست وغيرها. فهنا نختار السلكتيفيتي، كيف ايش الماده اللي بنزيلها. لو تواصلوا معنا مثلا طلاب من جامعات، عندنا ماده نبغى نسوي لها اتشنج، ايش هي الماده؟ اوكسايد، اوكي، هل الكلين روم عندنا متوفر فيها مثلا ميثان او اي الميثان ايا كان الغازات؟ نقدر. في جامعات ما فيها كلورين، على حسب الماده المستخدمه. يعني وقت الدكتوراه عندي ما كان عندنا كلورين، كنت اتجنب استخدام مواد معينه لانه ما نقدر نسوي لها اتشنج. فكل ماده اذا بنسوي لها دراي اتش لازم تأكد إنه الغاز اللي يزيلها متوفر وموجود. هذه بروسيس فلو لعملية اتشنج كاملة. بهذه الطريقة نقدر نزيل طبقات أو أشياء معينة لتصنيع رام أو أيا كان الديفايس. طبعا تمشي هذه ب ما بين خلط ما بين دراي ويت اتش، صعب أدخل عليها ان ديتيل في محاضرة اليوم. الجزئية الأخيرة أتكلم عنها اللي هي الأكسيديشن. تطبيقات الأوبتو إلكترونيكس مهمة، تصنيع الليزر والضوء. في صدى بسمعه خالد. طيب صوتي مسموع؟ تمام. اوكي. تطبيقات الالكترونكس من ضوء، من لايت، ليزر، دايودز، كلها يتم تصنيعها عندها بغرف النقيه في كاكس في تعاون مع جامعات عالميه. اهم المواد المستخدمه فيها طبعا نحتاجها الاوكسايد، نقدر نقول، او بعض 3-5 ماتيريالز. الاوكسايد بشكل عام عشان يتم تصنيعه فوق السيليكون نحتاج فيرنس. هذا طبعا بالنسبه للسيليكون او الاوكسايد عالميا وصلوا ل 18 انش، بس الاغلب يستخدم في المصانع هو ال 12 انش او ال 8 انش، انه تزود عدد الديفايس فيه. ولكن بشكل عام الاوكسايد مهم جدا في الالكترونيكس، انه نحتاجه في الجيت اوكسايد في الترانزستور. طيب كيف يتم تصنيع الجيت اوكسايد بالنانوميتر؟ هذا يتم طبعا عن طريق تحويل، نقدر نقول السيليكون، او يصير له ساكريفيكيشن، تضحيه من السيليكون لما نعرضه لغاز تآكل ويتحول لسيليكون اوكسايد. فيتحول السيليكون الى اوكسايد عن طريق الفيرنس في عمليه نسميها الاوكسايديشن. ما حدخل في ديتيل في الاوبتيكال بروبرتيز، روح عند الثيرمال اوكسايديشن. فالثيرمال اوكسايديشن يتم عمليه اكسده للسيليكون، بناء طبقه اوكسايد عن طريق واحده من طريقتين، دراي اند ويت. الدراي تتميز انها دقيقه جدا بالثيكنس اللي نحتاجه بالنانوميتر، 60 70 80 نانومتر، ولكن بطيئه. الويت سريعه، ولكن لازم تتحكم في الدقه بصعوبه، يعني تعتمد على الفيبر، يعني يعتمد على الغاز. طيب اللي يصير بعمليه الاوكسيديشن، نستهلك السيليكون بنسبه معينه، ايكويشن يكون عندنا سيليكون ثيكنس معينه، ونبغى 60 نانو، حيبدا يستهلك من السيليكون تقريبا هذا الريشيو 0.46، فناكل من السيليكون ونكون طبقه اوكسايد. هذا فيه ميزه، يكون عندنا الاوكسايد قوي جدا ويستخدم في التطبيقات الضوء وغيرها. احسن ما نسوي عمليه يجي البعض يقول اوكي لما ناخذ سيليكون نسوي ديبوزيشن فوق الاوكسايد، يس وي كان دو ذات، بس لما يكون مخلوط ويصير باوكسيديشن يكون اقوى. و يس هذه سيليكون سبستريت، هذه الاوكسيديشن كيف صار هنا تداخل بينهم وتكوين، يكون اقوى وصعب ازالته، وفي التطبيقات الخصائص حقته اعلى في تطبيقات الاوبتي الكترونكس. هنا مثال على الاوكسيديشن فيرنس، نحط الويفرز نتركها لفتره معينه بحسب البارامترز الموجوده، بناء عليها يتم عمليه التسخين، والويفر سواء غازات تتدفق او ووتر فيبر، بناء عليه يصير عمليه الاكسده. طبعا الاكسده بعد ما يتحط بدرجه حراره معينه توقف عن طريق الانيلينج مع النيتروجين عشان to stop the oxidation process. طبعا في فاكتور كثيره موجوده يزود او تنقص عمليه الاكسيديشن جروث. داخل فيها الحراره، ارتفاع الحراره يسرع العمليه بس ممكن يقلل الجوده، بس في بعض الاحيان ما نقدر نرفع الحراره، يكون عندنا مواد اخرى موجوده ممكن تاثر على هذه المواد، فمو دائما نقدر نزود الحراره لاي درجه نبغاها، ممكن تتلف. العامل الثاني هو الوقت، طبعا كل ما يزيد الوقت يزيد عمليه الاوكسيديشن. طيب في اشياء لو دخلنا في ديتيل تستخدم لانه بنكون عندنا نوع الدوبينج، هل هو بوزيتيف نيجاتيف بي تايب ان تايب، هذه حسب الانواع اللي نستخدمها، بورون ولا فوسفور ولا غيرها، بس هذه تدخل في عمليه الدوبينج. ان نحول الماده السيليكون الى ماده شبه موصله، نستخدم برضو الفيرنس ولكن بدون اكسده، نستخدم عمليه الدوبينج اللي هي التطعيم للويفر. طيب اخر شيء الاوكسايد المتكون، كيف نقدر نعرف لونه؟ او الثيكنس حقته عن طريق اللون. طبعا هذه الفكره نفس فكره الرينبو. الرينبو اللي في الجو ليش نشوف فيه طبقات؟ هي عباره جو. لما نشوف الرينبو يكون عندنا طبقات ثيكنس حقتها مختلفه تعطينا لون مختلف. هذا هو الرينبو اللي نشوفه. نفس الشيء اللي موجود عندنا في الويفر اللي نسوي فيها اوكسيديشن، لونها يعكس الثيكنس حقها، او نقيسها طبعا عن طريق طرق الكاركترايزيشن. هذه ما يتطرق عليها. فيكتيف توبينج مو مهمه. هذه 2 دي. اوكي، كاركترايزيشن غطيناه في الايام الماضيه، سي ام وتي ام وغيرها. هذا كل شيء عندي اليوم. اتمنى انكم استفدتوا من محاضره المايكرو فابريكيشن. اي اسئله او استفسارات؟ ما ادري اذا اقدر. في شات؟ ما في شات. الدكتور سلمان موجود؟ لا غادر. طيب شوف، ما عندي شات والله كاستفسارات.
دكتور عدنان، بس أنا عندي كم سؤال سجلت عندي أنا.
تفضل.
أول شيء المورز لو، أنت ذكرت أن المورز لو الحين يعني كان الموضوع أنه يصير عدد الترانزستور ضعف، صحيح؟
كل سنتين تقريبا، صحيح.
كل سنتين. أيوه، بس أتغير الوضع الآن، فهل صار
صحيح.
أنه أكثر ترانزستورز أكثر أو أنها صارت أقل؟
أكثر. صار في تسارع كبير، يعني شيء بشكل بسيط، يعني ما هو خارج عن السيطرة، ولكن صار أسرع. بس وصلوا مرحلة بسبب التسارع اللي صار لأن التقنية تزيد. لقوا إنه حيوصلوا مرحلة عندهم ليميتيشن، ما في أجهزة تقدر تقيس اللي هم سووه، يختبروا يتأكدوا ماشيين صح ولا لا عن طريق الاس ام وغيرها. ففي ليميتيشن، فعشان كذا راحوا بعض الشركات لا نروح لل 3 دي، نبني طبقات أحسن ما يكون عندنا 2 دي.
جميل. ايوه، السؤال الثاني انه انت ذكرت انه في ريكوايرمنتس هرجة الاي 3 والاي 5 انتل.
صحيح.
ايوه، بس الريكوايرمنتس تطبق على ايش؟ معليش.
طيب بشكل عام لما نبني طبقات معينة يطلع عندنا بروسيسور، المعالج هذا يقيسوه بالسرعة. السرعة الموجودة مثلا لما تشتري أي معالج 3.5 أو يعني كان جيجا هرتز وغيرها. هم طبعا الويفر لما يصنعوها ما هي دائما، بس في اماكن معينه بوسط الويفر تكون الجوده جدا عاليه حتى تطلع ريكوايرمنتس اعلى من اللي مطلوب. مثلا هم سووا تصميم ل ستاندرد معين، مثلا يكون السرعه شيء معين 3.5 2.4 ايا كان. ايام تطلع اكثر، تطلع دقه جدا عاليه، ايام تطلع متوسط، ايام اقل. ففي اشياء تتباع كاي 7، اشياء كاي 5، اشياء كاي 3. لو بحثت عنها في النت حتلاقي. انا اخذتها في دوره من شركه انتل قبل سنوات تكلموا عنها، ولكن بحثت عنها في الانترنت موجوده هذه المعلومه بالتفصيل. اخطاء التصنيع ايام في اشياء تتلف، في اشياء لا يقدروا يبيعوها كمواصفات اقل ولكن كسرعه اقل. السيليرون لا، السيليرون مختلف، يدخل في عمليه تصنيع مختلفه عن الاي 3 اي 5 اي 7. يتباع كشيء ثاني. الاي ال دي معالج مختلف، الاي ام دي عفوا الاي ام دي معالج مختلف يدخل في شيء ثاني برضو لهم انواعهم يبيعوها كاخطاء تصنيع وغيرها. في سؤال عندنا، هل تواجد الرمل بالمملكة تصنيع الويفر؟ يس. في كثير شركات أخذوا منها استشارة أنه يفتحوا مصانع لتصنيع السيليكون ويفرز. المشكلة فيها أنه الكاستمرز صح نقدر نصنعها بسهولة عندنا، ولكن لازم يكون عندنا زبائن يشتروا السيليكون. عندنا هنا كم أبحاث. نقدر نكون مركز يبيع عالميا يعني لغيرنا، بس في الناس ينافسونا كثير. بس يس، وجود الرمل في المملكة نقدر نفتح مصانع بسهولة تصنيع ويفرز، بس نحتاج ليها كاستمرز يشتروه.
يا دكتور عدنان عندي سؤال ثالث
تفضل.
معذرة. اللي هو بخصوص السيمي كوندكتورز نفسها، الامبيوريتي نفسها من متى بأي مرحلة تتم اللي هو الشوائب، إضافة
الشوائب
الشوائب
ممتاز. الشوائب السيليكون في البداية لو جينا عند تصنيع الضوء أو أيا كان، نقول الترانزستور سيليكون ما في شيء، لو جيت تقيس السيليكون. فنبدأ نشكل نحن لما يسمى الترانزستور عبارة عن 3 أشياء: الجيت هو اللي نسوي فيه الأوكسايد، ثم عندنا السورس والدرين، هذول نسوي فيه عملية التشويب. هنحتاج هذه نسويها يا بي تايب يا ان تايب. ففي المرحلة الأولى في البداية نسوي التشويب إن نكون السورس والدرين، وعندنا الجيت يصير فيه طبقة الأوكسايد. فكيف نقدر نسويه إذا كانت السيليكون غير موصلة كهربائيا؟ لا، لازم نشوبها، نسوي عملية الدوبينج، نحط فيها المادة يصير فيها التشويب. هي طبعا ديتيل مو محاضرتنا اليوم. محاضرتنا بشكل عام هي المايكرو فابريكيشن، بس في محاضرات تتم عن طريق أكاديمية 32 تدخل في ديتيل تصنيع الترانزستور، ندخل بديتيل في عملية الدوبينج، الأوكسيديشن. شفتوا سلايدات كثيرة تجاوزت عنها لأن صعب أدخل عليها إن ديتيل. هذه يعتبر بيسك. غطينا الليثوغرافي، الديبوزيشن، البعض يسأل كيف وصفها بالعربي، هي الترسيب، الاتشنج اللي هي الإزالة. هذه أهم الأشياء الموجودة في المايكرو فابريكيشن. أي استفسارات أخرى؟ المحاضرة الرابط غالبا حتشارك معاكم، هذه المنسقين البرنامج يتواصلوا معكم فيها. أو البعض سأل وايد ليش اخترنا سيركل ويفر؟ هي تتباع بهذه الطريقة، ولكن بشكل عام هذا ستاندرد نمشي فيه، يمشوا فيه عالميا. يقدروا يمشوا فيه البعض الريسيرشر يستخدموا، ياخذوا ويفر يقطعوها مربعات، فيها صعوبة، ولكن اللي يجرب الجزء العملي خلاص في الغرفة النقية الستاندرد هو السيركل، وفي أسباب معينة للألاينمنت إنها تكون سيركل. شوفوها بعدين الإيدج وغيرها تكون ألايند. يحتاج تدخل غرفة نقية بنفسكم تجربوا وتشتغلوا فيها، حتعرف السبب ليش أفضل الناس يركبوا. تقريبا غطيت كل الأسئلة، البقية كلها عن التسجيل. أي استفسارات أخرى؟ طيب، الله يعطيكم العافية جميعا وموفقين. أي استفسارات تواصلوا مع إدارة البرنامج بالإيميل ويردوا عليكم إن شاء الله. بالتوفيق لكم جميعا.